Yeah, I hope that, hello everyone, and welcome to this ISCA tutorial on real-world processing in memory systems for modern workloads. I want to thank you, all of you, for coming, for joining here physically and also in YouTube, because the tutorial is being live streamed, and good thing is that all talks will remain there in YouTube for whoever wants to watch them later. I'm going to very, very briefly introduce the tutorial and show you the agenda, and after that we will have Professor Mutlu, who is co-organizing the tutorial with me. My name is Juan Gómez-Luna. By the way, I didn't introduce myself. So we are both organizing this tutorial, and he will give the opening speech, the opening keynote, and after that we will have several hopefully interesting talks. As you can see, and as I said, the tutorial is being live streamed. The link to the live stream is there in the first slide. Let me just very briefly give you some motivation. I think that this must be clear for everyone, but just to set the stage, why are we working on processing in memory and why are we organizing this real-world processing in memory tutorial is because in computing systems, we have a big problem, and this big problem is called data movement, which dominates performance and energy consumption in basically all or most of applications, important applications that we are running today in our compute systems. Therefore, some motivation, you have some numbers, like 62% of the total system energy in consumer applications, for example, is spent on data movement. And this happens because in our compute systems, we have many different components, processors like CPUs, GPUs. We also have a memory hierarchy, we have accelerators, and we have an external memory, an off-chip memory. And there is a lot of data movement between all these different components. And this data movement, as I said, is dominating performance and the energy consumption. So one way to alleviate this bottleneck is to make compute systems more data-centric. And one way of doing that is what we call processing in memory, which basically consists of computing where it makes sense or where the data resides. This tutorial has been organized after several semesters where we are offering a course on processing in memory. This slide is about the edition of this spring 2023 that is just finalizing. As you can see in the slide, you can find the link to the website and also to the YouTube playlist. And the tutorial, it's right now in its third edition after the first one in HPCA this year. You can access the website and also the link to YouTube there. In ASP+, and end of March, we also organize it, and this is the current edition. There at the bottom, you have access to this website. In the website, you can access it over the course of the tutorial. We are going to upload all materials, the presentations that we are going to use, also the invited speakers. And now you can already access there the materials for the hands-on lab. That's already available there. And this is one more slide with the live stream link at the very bottom. Let me very briefly go over the agenda. After this short introduction that I'm giving now, Professor Mutlu will deliver his opening speech, memory-centric computing. And after that, I will talk about real processing near memory systems. There have been very interesting advances in the field in the last 2-3 years, and we are going to talk about these architectures. After the coffee break, we will have two interesting talks. These are real-world experiences with the real UPMEM processing in memory system. The first one is about sequence alignment. It will be delivered by Professor Izzat from the American University of Beirut. And the second one is about sparse matrix vector multiplication and will be delivered by Dr. Christina Giannoula from the University of Toronto. And then after the lunch break, we'll have a really interesting talk introducing the HBM-PIM architecture from Samsung. Is one of these first real-world PIM architectures, and I think it's going to be a really interesting talk. There was already a talk about this architecture in one of the workshops, the DOSA workshop by Dr. Kim, really interesting as well. Today we're going to learn for sure more details about HBM-PIM. And after that, we will talk about the other big trend in processing in memory. It's still being developed. There are no real systems yet supporting it, but this is what we call processing using memory. Our PhD student, Ataberk Olgun, is going to talk about the end-to-end framework for processing using DRAM that he has developed. And finally, after the last coffee break, second coffee break, I will talk first about a few more experiences accelerating modern workloads on real processing in memory systems, in particular on the HBM PIM architecture. One, let's say, final lecture about adoption issues, what needs to be enabled, still needs to be enabled, or needs to be done to enable the use of processing in memory in our compute systems. And finally, just the short introduction preparation for the hands-on lab. The hands-on labs, as you see, they are optional. You can do them after 5:30, or you can start doing them right away. As I said, in the website is already all the information that you need to access a real server from HBM. They are allowing us to access one of their servers today. I think we have access until tomorrow at 10 a.m. And all instructions are there. There are templates for the code that you need to develop in the labs. And I will be available today to answer any questions that you may have. And also after the tutorial, you can send me an email and ask anything that you may need to know. Finally, well, just a couple more slides. Here you can see the title, abstract, and bio of the invited talks. The first one, as I said, about sequence alignment on real processing in memory systems by Professor Hajj, and then we'll have sparse matrix vector multiplication by Dr. Giannoula, and finally the introduction to the HBM-PIM architecture from Samsung by Dr. Sukhan. Thank you again. Thank you everyone for joining. And now it's my pleasure to give the stage to Professor Mutlu and his opening speech about real world processing, about memory-centric computing.
Thanks, Juan. Now I know my video.
Yes.
And unmute.
Okay. That's also hide the video panels.
Okay, thanks everyone for coming. It's good to have a full room here. No.
Yes, I will need to do this as well.
Hope this works. Okay, well, that worked off the bat. Is it still working on Zoom and online? Okay, cool. Usually it doesn't work off the bat. That's why I'm surprised. There's always some issue. But okay, it's good to see people having a lot of interest in this. This is the third time we're organizing it, as Juan mentioned. We had it at HPCA first this year, and then ASPLOS, and then ISCA. We'll see if it continues. Hopefully it will. But every time we do something different, we have new invited talks and also new papers coming up at the cutting edge. So you will get exposed to some new stuff, even if you attended in the past. I assume no one here attended in the past one of our tutorials. Did anyone attend? Okay, that's good. It's always good to have a new audience. And it's also, this is FCRC, so this big community. How many people here are registered for ISCA? Okay, how many people for other conferences? Okay, that's great. So it's good to have the change. Of course, at HPCA, it was like that as well. The HPCA is also 3 conferences, but here we have 15 plus conferences. Okay, so I think without further delay, I would like to give an overview of memory-centric computing and why we are here today and what may come in the future. We don't have time to cover all my slides. I'll make this hopefully an overview of why we're doing this, but we will go into detail in a lot of the things that I'm going to touch on later during this tutorial. So if I skip something, don't worry, there'll be things covered. And also feel free to ask questions. So I don't want to make this a one-way thing if people have questions. As Juan mentioned, computing today is bottlenecked by data, and data is really key for many applications. Today, we have very interesting applications that are all data intensive. Machine learning is an obvious example, but there are many, many other ones like genomics, which we will talk about. Izzat will present a very interesting work on accelerating sequence alignment on processing in memory architectures. But essentially, these workloads require rapid and efficient processing of large amounts of data. And on top of this, data is increasing. I will show you an example from genomics, but essentially, we can generate more data than we can process today. And our computing systems are really bottlenecked by this. And we also need to perform more sophisticated analysis on the data going forward. This is an example from machine learning. Machine learning is clearly interesting, and we have very large models today. They're increasing in terms of complexity. You can ask the question, is this the right thing to do? We'll see that. Maybe in 10 years, we'll have much more efficient machine learning models, but we're not there yet. But essentially, memory requirements are growing, compute requirements are growing. Both of them are growing exponentially. If you look at the values on this chart, they're actually logarithmic, as you can see. And this is a beautiful talk that was delivered by Cerebrus's chief architect, Sean Lee. If you're interested, you can find it online on our YouTube channel. Because these folks are actually building huge chips, wafer scale chips, to tackle the growth of both compute power as well as memory requirements. We'll see if they're successful completely, because a single chip may not be enough actually for this, because the models are too large. But anyway, it's very interesting. So that's an example application, but that's not the only application. There are many, many interesting applications that we deal with in our lives today: databases, graph analytics, etc. They're all bottlenecked by data in the end. Data is a huge performance energy bottleneck. And if you look at the mobile end or the smaller systems, even these smaller systems, we're executing applications that are quite data intensive. I'm going to talk about some of these applications later on. And essentially, we are having a huge performance and energy bottleneck in these applications also. Let me talk a little bit about genomics. I think this is a fascinating topic for me. And our sister workshop next door is about accelerating genomics, actually. I will go there and give a talk later on in this afternoon about that topic. But essentially, this is an area where data is exploding. It's true for machine learning, but it's perhaps even more true for genomics, because we can actually have these sequencing devices that are extremely powerful. I'm not sure if you can see it from the back, but this picture shows essentially the cost of genome sequencing, and it's reducing exponentially through this curve. And the curve actually is extended to 2022 over here. Essentially, with the introduction of the devices that can sequence genomes at very low cost, at high throughput, the cost has plummeted. And this is the introduction of nanopore sequencing devices, a picture I will show you in a little bit. So basically, the cost of sequencing is reducing, so we can generate a lot more data today. Unfortunately, if you compare this to the cost of a transistor, which is depicted by this line over here, the cost of a transistor is not reducing as fast. So even though it's still following Moore's law somewhat, we're having difficulties toward the end. But basically, we can generate much more data than we can put transistors to process today. And I think this is a fundamental problem, basically. This is the reason why we're building accelerators. Essentially, we cannot throw more compute or general purpose compute at the problem. Okay, so I could talk more about genomics, but essentially we have very good sequencing devices today that can generate lots of data. But scientific discoveries and medical advancements, at least the speed of them, are really bottlenecked by how fast we can analyze that data. And clearly, there are many applications of genomics. We've seen this with the SARS-CoV-2 pandemic, because these devices actually, the genome analysis or RNA analysis has enabled us to really understand the pandemic and actually react to it relatively quickly, develop vaccines, etc. But there are many, many other examples, both scientifically and in the medical domain. And this is one example of a data generator. This is the nanopore sequencing device that reduced the cost a lot in 2014. And you can buy this for $1,000, for example. But in order to do the analysis of a genome, you can actually do the sequencing yourself if you're interested. There are high school students who are sequencing their pet fish genomes, which is also interesting. But basically, this is very, very low cost. Unfortunately, you cannot analyze the data as fast. So let me give you the general problem. Basically, you can put another sequencing machine over here. This is a Illumina sequencing machine, which is much more costly. But basically, we have these very special purpose machines that can generate data in genomics today. They're very fast and efficient, and we're moving the data a lot to some other machine to process the data. And this other machine is usually a general purpose machine. So there are two kinds of inefficiency here. There's huge data movements between the machines and within the machine also, which we're going to talk about later on. And then the machine where the data analysis is done is not as capable or as specialized as the machine that's producing the data. And I think this is a problem. This picture is actually very similar for many data generators and analyzers today. Replace that sequencing machine with a video, for example. We have video cameras all over the place. Even a single one is very specialized. But if you actually have a distributed system of video cameras, essentially we're doing the same thing over here. Okay, so you replace that with clicks on the web, for example. Again, we have a distributed system that's generating a lot of specialized data. Okay, so basically, this is the bottleneck we're trying to tackle. And I think in the end, we need specialization on this part. And we also need to reduce the data moment as much as possible at both macro scale as well as the micro scale, because there's data moments at the macro scale across the world, right? Whenever you sequence the data, you need to move to a cloud, for example, data center. But also within the machine, there's a lot of data moments internal. And we're wasting a lot of energy on data moments. So I'm going to focus a lot on the micro scale over here. But I think increasingly, we need to look at the macro scale as well. Okay, so if you're interested in genome analysis, this is a fascinating area. We've been doing work in this area for more than 10 years or so. And we were invited to write this paper to DAC, the Design Automation Conference, which is going to happen next month. And we're going to present it. If you're interested, you can take a look at this paper. It's already on archive. It's an overview paper. And we also write a bunch of overview papers. It's a bit old right now, but it gives you an idea. This is an area that I think we need more brains in, if you will. Okay, I'm going to skip some of these things. I'll give you one example of what we can do today in near memory computing. Of course, there will be more examples that are coming when we talk about near memory computing. But before those examples existed, we actually had near memory computing machines that we can configure customized. And we have a paper that's related to this. And essentially, it looks like this. So this is a general purpose CPU. And you could actually attach an FPGA to it. And this FPGA has clearly configurable fabric. And it has very high bandwidth memory, HBM, attached to it. So essentially, you have potentially customizable logic that can access memory at very high bandwidth. And this is near memory because this is nearer to memory compared to the processor is. So again, I won't go into details. The details are in the paper. But if you actually do the hard work to customize your application and put the important kernels and in specialized logic over here and enable high bandwidth memory access to them through this memory, you can get significant performance improvements and energy efficiency improvements. In this particular work, we look at weather modeling and genome analysis, pre-alignment filtering in particular. And you see the numbers. So this is from a real system compared to a CPU, IBM Power 9, pretty hefty CPU. You get up to 27x performance improvement and up to 133x energy efficiency improvement on specialized applications, which is great, I think. But this is not what we want to do in the end. We want to actually be even like more aggressive in terms of pushing computation on the memory side. But this is a good acceleration model to begin with, let's say. And this acceleration model is actually becoming really interesting going forward. At the time we did this work, this was the OCAPI interface. Today we have CXL type of interface, which is going to be even more, let's say, popular than what OCAPI was. CXL is essentially a let's say, descendant of OCAPI, in my opinion. But these are flexible interfaces where you can actually offload computation and have some coherence support, etc. So when we talk about when we talk about adoption issues, hopefully we're going to discuss some of these later this afternoon. Okay, so that's good, but you can do more. You can actually specialize the applications. So we've been developing approximate string matching accelerators near memory. And this is the paper that I'm going to present actually later today, the work that was done by my PhD student, Joel, that actually makes that prior work better. So if you're interested, you can actually take a look at a lot of works. So memory is not enough. So this workshop is about actually processing in memory, but we actually need to do processing everywhere. I'm going to motivate that a little bit more. So we've also been working on processing inside the storage. And I think it's going to be increasingly important because the data sets are growing in a way that memory is not going to be enough to house them. So does it really make sense to actually bring the data into memory becomes a question. And I believe in large scale applications like genomics, where you need, in some cases, terabytes, like hundreds of terabytes or even petabytes of data to analyze genomes, you really need to go to the storage. Okay, maybe we'll have time to talk about this. We'll see. Okay, so there's a lot more over here that I'm not going to cover, but a lot of these works try to reduce the data moment. For example, this work tries to reduce the data moment between two different devices by integrating them on a single device. And if you're interested, there's more. Basically, the future of genomics, I think, is very bright, but we need near data processing to enable this to be much more efficient. And if you're interested, there's a lot more information on this. And we have a genomics course. I'm not sure, maybe Juan mentioned the processing in memory course, but we also have a genomics course that you can take a look at. If you're interested, there's actually a lot of online material. This is an area that's not easy to get into. We recently organized a bioarts workshop at RECOM, which is one of the premier conferences in computational biology. I'd recommend you take a look at it. There's a lot of in-memory processing that we talked about over there. Okay, so why am I telling you all of this? Not that I want to convert you to people who work in genomics, which would be very good, no problem. If you're interested, I would definitely recommend it because it's a whole field that opens up a huge area, in my opinion. But this is an application, and this is a very data-intensive application that constrains our systems. And it really overwhelms our machines, along with other applications that we have, like machine learning. It overwhelms, this sort of applications create a lot of data movement and data access that overwhelms our storage and memory capability, communication capability, and in the end, computation capability. You may have a compute device that's extremely powerful, but if it's really bottlenecked by how fast you can access the data, then that compute device gets useless. And I'll show you some motivating results from the field to talk about that. And also, data really impacts robustness, energy, and performance and cost, as we will see soon as well. Okay, so let's go back to the fundamentals. If you think about a computing device, you need computation, you need storage and memory, and you need communication between both the compute units and the storage and memory and compute units. And if you look at how we designed the systems over many decades, we've heavily optimized the computing units. I'm going to use this one over here. We've heavily optimized the computing unit, and it's become extremely powerful, but we have not really, let's say, empowered the rest of the system. The rest of the system still serves the computing unit, meaning this is where the processing gets done. Everything else is really serving data to this computing unit. So is this the right way to build systems? We strongly believe that that's not the case, and hopefully I will give you some evidence as to why we believe that's not the case. Maybe we should really be thinking about all of these devices as compute units, and they may have different types of computation that they're capable of, but this could be a distributed system of computation units, and they can actually communicate with each other to get a large-scale computation done with minimal data movement as much as possible. So that's the key idea, basically, and that's what we see in our opinion, where computing systems should evolve going into the future. Of course, this is not easy going into the future, as we will discuss in adoption issues, but in a sense, there's nothing really special about the computing units. Why did we make it so special? Clearly, there are historical reasons that we don't have time to go into right now. But let me give you some examples of this computing unit. So this is my picture from 2008. I still use this picture. It's a nice picture in the sense that it shows a general purpose CPU, but you could also think about this as an SoC today. Essentially, you have cores, and computation gets done in the cores. Everything else is dedicated to data storage and movement. Caches, interconnects, other caches, other interconnects, other caches, larger caches, other interconnects, memory controllers, other interconnects, memory, other interconnects, storage, other interconnects, and then you have far memory, far storage, etc. Essentially, if you look at a single node over here, more than 95% of the real estate, including the memory and the storage, of course, is dedicated to structures that store and move data. And we call this a computing device, right? But most of it is not a computing device. And you would think if you actually gave this picture to a 10-year-old child and asked, do you still have a data movement problem over here? They would probably say no, but essentially this system is still bottlenecked by memory and storage. I will show you. So even though we're dedicating almost all of our resources to things that store and move data, we're still bottlenecked by it. Maybe this should actually cause us to pause and ask the question, are we doing the right thing? Okay, so if you don't like my picture, this is a real picture from AMD. It's not the state of the art, but it's a good one. You can see that that green box over here is L2 and L3 caches. And then there's a global memory interconnect and a bunch of IO and a bunch of L1 caches, etc. So if you actually keep adding all of these memory structures, it's most of the chip. And if you don't like that, add more. Essentially, we're adding more and more caches. This is actually beautiful technology. It's 3D stacking on top of the compute chip. You have a cache chip on top of the compute chip. But we're basically increasing the hierarchy by adding more complexity to our systems. If you don't like AMD, that's IBM, essentially the same thing. By the way, if you look over here, this is all about memory signaling, this huge area, and I/O signaling as well. So memory and I/O is all in the periphery, but it's a huge part of the chip also, if you think about it. So we're actually putting a lot of resources, as you can see, to make data communication better, but we're still bottleneck by it. So this is an SoC. If you look at the SoC chip, it's a lot of SRAM. And then there's a lot of DRAM, just to put things in scale. And then there's a darkness that I cannot plot over here, which is storage. So most of the system is not compute units. And most of the system is dark in the sense that it cannot do compute. So why can we not do compute over here, over everywhere? Okay, so let me give you some data. So Juan mentioned this in his talk, but we did the study together with Google on these workloads, which are interesting. And we're actually exercising right now. We're live streaming this on YouTube, and YouTube is exercising both of these over here. And online, if someone is watching, they may be exercising the website, and somebody is collecting your data and doing inference or training on it. So all of these workloads are being exercised as we speak right now in a mobile system or not a mobile system. But basically, we analyze these workloads. It's been some number of years. It took us some time to really analyze these in deep. And we found out that on average cases, not extreme cases, but on average cases, we see that most of the system energy is spent on data mode, more than 60%, assuming that everything fits in memory in a mobile system. If things don't fit in memory, if you need to go to storage, that number increases, shoots up. So this is not good, clearly. Our energy is wasted. Okay, we actually continued working with Google and did another study, this time especially focused on their edge devices, Google Edge TPU, and looking at their edge neural network models. These are proprietary models that Google uses or used to use at the time when we actually did the work. And we found out more than 90% of the total system energy is spent on memory in large machine learning models like LSTMs, transformers, etc. Some things that convolutional neural networks that fit, yeah, it's not 90%, it's smaller, but with large models, this number becomes much larger. So basically, this is a good question to ask. Are we, again, doing the right thing, spending so much energy on memory? Let me give you the bigger picture before we actually go into a little bit more motivation and maybe some examples, but I will try to leave the examples to the later talks because there will be a lot of examples that are coming. This will be more on motivating and giving you some data. So I think our axiom should be, going forward, we should really handle data. We want to design architectures that we're going to bet our lives on, actually. We're going to rely on them in the field, and they're going to make decisions for us in many, many cases. They're already doing that, but they're going to be even worse, or even, let's say, even more widespread. And if they're not intelligent, maybe we'll run into problems. So how do we handle data? I think there are three directions over here. This workshop is especially focused on this part and ensuring data doesn't overwhelm the components by designing intelligent algorithms, architectures, and system designs. We're going to talk a lot about that, actually. There will be a lot of talks that try to design algorithms and architectures together. But there are also two other directions that are extremely important, in our opinion, that are synergistic with the first direction. The second one, very quickly, is there's a lot of data that's flowing through our systems. And when we design our systems, both hardware and software, maybe we should actually take advantage of the data that's flowing through our systems so that these systems make intelligent decisions, meaning they can learn from the decisions they make. Let me give you a concrete example. So you have a memory controller. This memory controller sits in between the CPU and the memory, and it basically schedules requests from the CPU to the memory. Now, this memory controller that is here or in my pocket is making decisions, but right now it's making decisions that are dictated by a designer. A designer said, if the condition is this, and if this other condition is this, and if this other condition is this, make this decision. So it's very, let's say, hard-coded and heuristic-based. Now, wouldn't it be nice, actually, if this memory controller resembled us humans as decision makers? So we're more experience-driven, right? We actually interact with our environment and make decisions based on what we see in the environment. We're actually reinforcement learning agents and probably other learning agents. So we actually can adapt our decision-making based on what we experience, based on the rewards we get, and based on the punishments we get, or negative rewards we get from the environment. So this memory controller could make much better decisions if it was actually a machine learning type of agent. So I think this is something important. It could actually, this way our systems can improve over time, but this also requires some processing capability on the memory controller. So if all of your controllers are actually now intelligent agents, you actually need processing capability in all of your controllers. That's why I mentioned that it's synergistic with this direction. Okay, I don't want to talk too much about these, but this is, I think, fascinating also. So this third part is really how we are dealing with data. Since data is one of the most important things, or maybe the most important thing that we deal with in our systems, do we actually express its properties to the underlying architecture and actually make decisions based on that? So it'd be good if we design architecture that can understand, exploit properties of different data so that we can actually improve our algorithms and decision making. Let me give you another concrete example. I'll pick on the memory controller, since memory controllers we've been working on for a long time and I love them. And also it's the center of the world, right? If memory is so important, there's CPU, there's a memory controller, and there's memory. Why not actually put a lot of intelligence to the memory controller? So if you look at a memory controller today, if it's trying to make a decision between prioritizing one request over another, it makes that decision based on, again, heuristics and very much structural properties. It doesn't ask the question, oh, is this data more important from a security perspective, for example? Because it doesn't know that information. So the semantic properties of the data that may be useful in decision-making, in prioritization, scheduling, allocation, etc., those do not get communicated to our software. They don't even get found out in general. They don't even get annotated when we write our programs. As a result, when we make decisions at the software and hardware levels, like scheduling decisions, as I mentioned, we're kind of blind to the properties of data. But data is the most important thing, right? A lot of security problems actually exist because we don't know which data is more important or which data is security critical compared to which other data. So if you actually discover the semantic properties of data, communicate them, we can actually make much better decisions. And I think this is also very much synergistic in data-centric computation because this enables specialization of your data-centric system to the properties of the data that you're dealing with. And data has a lot of properties. I just gave you the security properties, but there are also privacy properties. There's approximability properties, error tolerance properties. There's locality properties, clearly, performance type of properties. There's compressibility properties. So you can keep adding to this. Okay. So I spent a lot of time on the slide because I think it's really important and it's good to explore the synergy. And I believe there is a lot of research topics in this direction. So basically, today's computing systems are processor-centric as opposed to data-centric. We're going to talk a lot about that. But today's computer systems also make designer-dictated decisions as opposed to data-driven decisions that improve themselves over time based on what they see and the feedback they get from the environment. And today's systems make component-based myopic decisions because they don't know much about the data and its properties. So maybe we should be moving more towards data characteristic-aware systems or data-aware systems. Okay, so all of these actually require rethinking the entire stack in the end. Even though in some cases you may actually do something small, I don't want to call them smaller, but impactful within each horizontal part. But I think we need to think both horizontally as well as vertically when we design better data centric as well as data aware and data driven systems. So if you're interested, again, we're writing papers about it, having lectures. This is a very short position paper that talks a little bit more about what I just said. Okay, now let me jump into the data centric part of this. Now, if you look at the data-centric part, even this is a huge part. So what are the properties of a data-centric architecture? This is what I could list. We're going to talk a lot about the first one, as I mentioned. But if data is so important, and if you want to be data-centric, we should also enable low latency and low energy access to data. And I believe we're not doing very well over here. We can enable low latency and low energy access to data, small amounts of data. But what about large amounts of data? Petabytes, exabytes, and I guess zettabytes, yottabytes, whatever those are, essentially, they're coming, and we need to enable better memory structures, in my opinion. So there's a lot over here. It's a hard area, but I think we need to look at this more. We need to do more low-cost processing and intelligent data management. I'm going to touch upon some of these. Let's jump into the first one. So I call this processing data where it makes sense, as I mentioned, not just memory, but also any type of place where data resides or where data is generated. So if you look at this simple system, SOC system, the data resides in storage, DRAM, SRAM, and it also gets generated through the sensors, right? So all of these places should be doing processing, in our opinion. And there's work going on in all of these directions. And even within the SOC over here, the data moves internally. So it makes sense actually to examine techniques that do the processing near the cache, for example. Okay, so this is not a new idea. There's some old papers. There's some smart people who looked at this in 1960s and wrote papers calling it logic in memory. This is going to be very similar to processing near memory, as I will define soon. And this is the earliest paper we could find. If you find other papers, please let us know. And there's another paper that's concurrent from Harold Stone, who has a beautiful computer architecture textbook. It's a bit old right now, but I think the last edition was in 1990, but I'd recommend it to people if people are interested. Okay, so And people have examined this idea over, let's say, many decades, but it has not ever taken off, let's say, in a broad way. So why is it interesting today? Why should we cook the beans again, if you will, right? So I think today we have nowhere to escape, in our opinion, at least. We're having huge problems with memory technology that we've never had before in the past, especially the DRAM technology, but also other memory technologies that we have. And we're having a huge demand from applications and systems to do something different. So our designs are essentially squeezed in the middle. So if you think about the technology part, that's at the bottom layer, devices, circuits, etc. If you think about application and system, that's about the top layer. They're both squeezing us to do something different in the parts of the stack there where we can actually design execute programs. So I'm going to talk about these relatively quickly, but I want to give you an idea because both of these are important in my opinion. Essentially, memory technology scaling is not going well. We're having issues like rope hammer, and these and other issues also. These scaling issues demand intelligence on memory side, so that your controllers need to be intelligent so that you can solve some of these problems. And once you have that intelligence, maybe you can do some other things about it with that intelligence too. And on the applications and system side, data access is a huge bottleneck. We have energy and power bottlenecks, and data movement energy dominates computation energy. We're going to talk about that. But also, I think our requirements have changed, meaning we want performance, we want energy efficiency, and we don't want a trade-off between them. There used to be a time in 1990s, 2000s, etc., where the game was, oh, I get a little bit more performance and I pay less energy costs. I don't think we should really shoot for that anymore. We should really shoot for, I want to improve performance and I also want to improve energy efficiency, and I'm not going to settle for less because we're having a lot of scaling problems. And also sustainability is in the picture today, which was not talked about, let's say, even 5 years ago as much. So essentially, I believe we can improve all metrics by minimizing data movement. So that's why we need to rethink our systems, our design. Okay, let me foreshadow what will come later. So processing in memory landscape today is actually very interesting, as we will see in later talks. Initially, it started with 3D stacking technologies in early 2010s. And people designed these 3D stacking technologies. Okay, I'm going to go back to this because it's not working. You have essentially a logic layer, compute layer, underneath memory layers. So you can actually do specialized computation inside that logic layer or general purpose computation. And Micron actually built this automata processing, which they're not building anymore, but this actually enabled a lot of interesting research that is still happening to some extent. But more recently, as we will talk a lot about, the UPMEM company actually produced real DRAM chips that have general purpose processors in them. And this, I think, has changed the game a little bit. Even though it has a lot of shortcomings, as Juan will mention, it actually can be programmed to accelerate important applications, as we will discuss. And if you're interested, you're going to program it also. And then after that, well, concurrently maybe, major companies have started changing their DRAM chips to include machine learning type of accelerators. We will also talk about that later on. Samsung actually has a talk about this particular prototype that they have designed later today. And SK Hynix also did something similar. We had actually a talk about this in the ASPOS workshop. If you're interested, you can watch it. And Samsung and Meta designed, basically these are all DRAM-based processing in memory architecture, because DRAM is the main memory. We don't have any other main memory technology that's dominant, let's say. And this is essentially a module where you can do processing inside the buffer chip, which is very interesting. And then Alibaba, we had a talk from Alibaba in our first workshop in HPCA. They're also designing their DRAM chips. So basically, they're feeling that, let's say, push so that they can actually accelerate things near memory. I believe this is actually caused by multiple things. And actually, if you think about DRAM, if you went to a DRAM designer, let's say, 10 years ago, okay, maybe 15 years ago, 10 years ago is also enough. And if you said, I'm going to put a huge processor inside your chip, they would kick you out of the room because they're so cost constrained, right? But today, all of these chips are DRAM chips, essentially. Basically, people are actually willing to modify something that's so cost constrained to improve performance. So I think this is a very good thing that's happening today. So if you're actually attending this sort of workshop or one of my talks in 2019, none of these will be here except for the automata processing, which was dying at that time. Okay, so why is this happening? Let me give you the technology perspective, which we're not going to talk a lot about in this workshop, but I think it's important. So we've been working on technology scaling problems on memory for a long time. And this is an invited talk that we delivered in this industry workshop, International Memory Workshop in 2013. And we argued that memory technology scaling is not going to get better. It's going to get much worse. As a result, we should really be thinking about system design to overcome the shortcomings of memory. This includes overcoming the reliability shortcomings that we will discuss, but also overcoming other shortcomings like the inability to process data or move data inside. So we're basically thinking of memory as a passive agent that cannot do anything, but we should really change that mindset. That's what we have been arguing for a while. So we said that there are a lot of reliability issues, and one of the interesting things in terms of scaling issues is row hammer. It's the fact that you can predictably induce errors in most DRAM memory chips. And in fact, we had a DRAM security workshop yesterday where we talked a lot about row hammer. Even though we wanted to talk about something else, everybody kept going back to row hammer for some reason, which is interesting. And this time it was the industry that was talking about row hammer, which was a different thing. Okay, how many people know about row hammer here? Okay, how many people do not know? Don't be shy. Okay, I'm going to give you a very quick introduction to it. I don't want to make this a talk about row hammer, but it's going to be different from what you will see in the later tutorial. Hopefully it'll be interesting. So this is a fact today. Basically, you can predictably induce errors in most DRAM memory chips. That's the row hammer phenomenon. So what's the problem? Basically, it's a technology scaling problem, meaning you have a DRAM cell, main memory cell, that stores 1 bit, right? And this is getting smaller as you increase the capacity of the chip due to scaling. And this is getting closer to other cells because you're trying to pack more cells in a given area. And this is causing reliability problems in our chips, many reliability problems, a lot of noise issues, a lot of disturbance issues. And row hammer is a particular one that gets exposed to the programming language, essentially. As a result, it causes a security problem. So essentially, if you think about DRAM or any type of memory, it has a bunch of rows of cells, and this is a two-dimensional array structure. If you want to access one word or one data value, you need to activate one row, apply high voltage to that row. Now, if you want to access some other row, you need to deactivate this row, apply low voltage. This is called pre-charge in DRAM. The first one is called activate. Basically, open, close, open, close. You can also think about it. Now, if you keep doing this repeatedly, which is a perfectly legal action in DRAM, high voltage, low voltage, activate, pre-charge, activate, pre-charge, activate, pre-charge, or open, close, open, close, open, close. It turns out in modern DRAM chips, some physically adjacent, some vulnerable cells and physically adjacent rows get corrupted. So if they used to store a 1, now they store a 0. You should be able to do this enough times before the cells get refreshed. And today, actually, you can do this very easily. Clearly, this should not be happening, right? I'm just accessing memory. I'm not even writing to it. I'm not even writing to this row. I should not be changing any value in memory. So this breaks memory isolation. We call this the hammer row. We call this the victim row. And we show that basically more than 80% of the chips that were manufactured when we did the initial testing, this is the original paper, are vulnerable to this effect. So this is the technology scaling I'm talking about. We're having a lot of difficulties, and this became much worse over time. Essentially, with these bit flips that are predictable, people developed security attacks. They basically were able to take advantage of the bit flips in a user-level program, and the user-level program was able to take over the Linux kernel. Okay, and then you can see very nice titles like this in popular Wired magazine. Forget software, now hackers are exploiting physics. I like this one. Okay, so these issues are real. And if you're really interested in row hammer, I don't have time to talk about it. This is a paper that we wrote earlier in ASP DAC in 2023. And we essentially argued that you need to make memory controllers intelligent. So what does that mean? Basically, memory controller or the DRAM chip, which will become part of the memory controller, detects this sort of thing, and it tries to overcome it in some ways. By refreshing the adjacent rows, for example, those are some solutions that we proposed. You can actually look at the original paper. So if you're also interested, there's a latest row hammer lecture that we have. Even this doesn't actually cover all of the new research. Okay, so this is an example of where intelligent controllers can be useful. And again, the interesting thing is, industry is finally writing papers about it. Our original paper was published at ISCA in 2014, 9 years ago. And this is a paper from ISCC, the top circuits conference, where SK Hynix discussed row hammer for the first time publicly in what I've seen, at least in writing, publicly from a major DRAM vendor. SK Hynix is the second major DRAM vendor. And they basically said they did a lot of things inside their DRAM chips to mitigate row hammer. And if you're interested, you can read the abstract over here. But what did they do? Essentially, they modified the DRAM chips. This was a big no-no, as I said, in the past. But now they're modifying DRAM chips to keep track of which rows are getting how many accesses. So if you actually have counters associated with rows and count how many accesses are happening to each row, you can try to mitigate row hammer. When a count increases above a threshold, you can refresh rows adjacent to it so that the disturbance effect that happened because of hammering that row can be undone, at least partially. That's the idea. So this is actually bigger than what even we were thinking of, because this actually adds a lot of complexity to the DRAM. Well, comparatively, right? So that's a good thing. Basically, this is essentially some computation that's put inside the DRAM to overcome the scaling issues. And Samsung also wrote another paper that's on archive. You can also take a look at it. A lot of the ideas that are here are actually initially proposed by us, but they also modified the ideas to try to make it work. Okay, so there are a lot of interesting things that I can talk about Rollhammer, but these issues are not going to get better. Let me put it that way. Solutions are being developed to actually put intelligence in memory, which is good. But these issues are going to get worse. And actually, we have a paper coming up. If you're attending ISCA on Monday, we're going to introduce another read disturbance mechanism in DRAM that makes things much worse. I'll leave it at that. And there's a premiere of the talk on that YouTube channel. So you can actually find the paper, I think, on ACM Digital Library right now. Okay, so you can say, okay, technology scaling issues are terrible. Maybe we should not be using DRAM technology. And you can say maybe there are other memory technologies. This is actually a very interesting direction, and people should be looking at it. And we've been looking at it for a long time. Unfortunately, DRAM technology is very strong. And the second thing is all other memory technologies have similar problems, especially when they scale to capacities that we are used to in main memory today. It's basically we have nowhere to escape, in my opinion, in technology. For example, you may actually use phase change memory, but phase change memory is also a technology that's not that has these scaling issues. So you need to actually have intelligent controllers to overcome these issues. Okay, so I think I could keep going with many examples, but I'll stop over here. Essentially, intelligent memory controllers can avoid many failures and enable better scaling. That's the technology direction. Now let's move to the top direction. So we were talking about the very bottom. Let's talk about the top. So if you talk about the top, meaning system and applications, basically we have data access, energy, and data moment energy. And these are really limiting us. In my opinion, maybe we should be thinking even bigger. Like, do we want a world that looks like this? Or do we want a world that looks like this? I think I will pick the first one. But I should still be able to solve problems in the first one, not just lie around and do nothing, right? So basically, I will maybe in a more refined way, we need the best of both worlds. We need high performance to solve important problems that we're going to face. We need energy efficiency and sustainability so that we don't die while we solve those problems. We want all at the same time. So the problem, I think, is data access is a huge bottleneck. On the current design principles, it causes great energy waste because we're moving data all around. And unfortunately, to overcome the performance effects of data movement, we cause even more energy waste. Meaning, we try to overcome this data movement because it takes some latency. And to overcome that latency, we make our systems even more complicated. As I showed you earlier, we add levels and levels and levels and levels of caching hierarchies, which is most of the system. We add heavy, sophisticated out-of-order execution capability, which is actually most of the core itself. We add prefetching mechanisms, and we had massive levels of multi-threading to tolerate that data access latency. So data access causes performance loss. We try to tolerate it. When we're successful, it may be good, but most of the time, either we're not completely successful. These mechanisms don't completely work. So if you look at caches, for example, there are many studies that show that most of the caches store dead blocks. Most of the blocks that are inside the cache are useless, most of them. So essentially, we're adding a lot of complexity to our system that's compounding the energy waste. And in some cases, these techniques don't work at all, like random access applications. If you have lots of random accesses, a lot of these techniques are useless in the end. Maybe multi-threading may work, but it also depends on how your access happens. Okay, so I think when you have a vicious cycle like this, where you keep expending energy, it's good to pinpoint the problem. I think the key problem is we're processing data only in the processor. We're very processor-centric. We're not able to distribute the data processing. So essentially, we're going back to this picture. We're doing this data processing inside the processor at great system level cost and energy costs, and also performance cost in the end. Now, let me give you some numbers also. So this is an article that was written by Dick Seitz. Dick Seitz was the chief architect of Alpha processors at the time. Alpha was the competitor to Intel at the time. And after they designed a flagship Alpha processor, which was actually top of the line, Dick Seitz wrote this article, which is titled, "It's the Memory Stupid." It played with the, let's say, running line of a candidate in US elections at the time, which was, "It's the economy stupid." It's all about economy, basically. In this case, it's all about memory. And this person basically said that we designed this processor. It's capable of finishing 4 instructions per cycle, per clock cycle. But on this important workload, which we believe we designed this processor for, a database workload, if you read the paper, you'll see that, it's finishing 1 instruction every 4.7 cycles. So it's operating at close to 5% of its efficiency. Why? It's waiting for data to come back. And he finishes the article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. I recommend people to take a look at this beautiful article. And again, we knew that memory is a bottleneck, basically. That's my point over here, but it's a growing bottleneck today. Okay, so this is data from my own PhD thesis. We published this paper with Intel in HPCA 2003, where we showed essentially the same thing. We analyzed all of the workloads that Intel used to design their processors with at the time, and we found out most of the time the processor is waiting for data to come back from memory. And this is the state-of-the-art processor at the time. Okay, if you're interested, you can read our paper also. Okay, fast forward some time, 10 more years. This is data from Google, since everybody believes Google, and I like this paper because they wrote it, and it's very nice. They basically showed essentially the same thing. In the state-of-the-art processor that they have in their data center, and this is according to them, all of their data center workloads, most of the time the processor is waiting for data to come back from memory. So I think these studies need to be repeated, but if you do the study today, you're going to see essentially the same thing. And that's what we actually showed in our papers that I mentioned earlier, the ASCA 2018 and PAC 2021 paper, where we worked with Google to show other workloads, not these workloads exactly. These workloads are actually very interesting, but they don't make them available. Okay, so that was the performance perspective. Let's take a look at the energy perspective. Energy perspective is even worse. So this is an old slide that I borrowed from Bill Daly, but it makes a point really well. If you look at the energy cost of a double precision arithmetic operation, is 20 picojoules with some technology at the time. If you look at a memory access, it's 16 nanojoules. So that's 800x difference. So a memory access basically consumes between 2 to 3 orders of magnitude the energy of a complex addition. Now, if you look at this picture, does it really make sense to bring 2 pieces of data to do a double precision computation from memory all the way to the chip and then write back the data? So you're doing 3 memory accesses to do a very simple, simple computation. Now, if you actually do the calculations to figure out how much locality you should have on all of these data elements so that you could amortize the cost of energy, that's going to be a lot of locality, meaning you actually need to be using those data elements thousands of times to actually overcome this energy differential. And actually, Wenmei Hu has a very nice presentation where he quantifies this. Maybe you can find it online somewhere. Anyway, so that's the point, basically. Energy is actually even worse. And this picture actually doesn't do justice to it. If you look at this, this is the energy for a simpler arithmetic operation, even though it's not simplest one, but 32-bit operation, 32-bit add. The energy differential is 6400x compared to a memory access. And today, we're actually trying to make the computations even simpler. If you look at the inference that we do in machine learning, we're trying to get to 4 bits and maybe even 1 bit at some point, right? You want 1-bit addition or 4-bit addition. That actually is even more costly compared to, well, even less costly compared to a memory access. Okay, that's why we see these numbers basically. More than 60% of total system energy is spent on data moment on real applications. And on real machine learning models, more than 90% of the total system energy is spent on essentially memory. So I would argue that hopefully I've convinced you by now that we do not want to move data. So data moment is really destroying our energy and performance. We do not want to move data. We want to change to a paradigm where computation is done with as minimal data moment as possible. And we want to compute where it makes sense. We want to have the ability to do computation in other parts of the system and not just the processor, especially where data resides and where data is generated. Essentially, this is a more data-centric system in the end. So in the rest of this talk, if I have time, and also the tutorial, we're going to talk a lot about memory and storage also. I think I generalized memory and storage. But this idea of memory-centric computing is not limited to just memory. Memory just happens to be very interesting because we have this memory and storage devices that are very capable of storing data. And we actually design our applications to fit memory, for example. So the idea is still processor is, let's say, the control unit that enables acceleration through memory. Maybe that needs to be also modified going into the future. So we're not as aggressive. This is still an accelerator model. Memory is still an accelerator. But basically, you offload some computation to memory. The processor asks, memory, can you execute this function for me? Can you execute this application for me? Can you execute this query for me? And the memory says, yes, here are the results after some time potentially. So there are many questions over here, which we're going to tackle in this tutorial. How do you design the compute-capable memory and controllers? I mean, we're not going to answer all of these questions clearly, but there's a lot of research that needs to go on to still answer these questions. How do you design the processors and communication units? How do you design the software and hardware interfaces to enable this? So we're going to hopefully talk about that in some of the things. You may actually ask the question to Samsung also, because it's good to discuss that probably. How do you design the system software, compilers, and languages to take advantage of this? And also, how do you design the algorithms and theoretical foundations to get the best of this memory device computation capabilities over here? Because the computation capabilities that are designed inside here may be different, right? As we will very soon see. So this is an across the stack problem. Maybe we can make progress, and it's not going to be solved overnight, but we need to do a lot of interesting studies to enable this, in my opinion. And I should also mention that theoretical foundation is important for those of you inclined with theory. Is there anyone from Stock here? Stock is a top theory conference. Maybe it has not started yet. That's the beauty of FCRC, right? You can talk to people from Stock that you normally don't see. But essentially, maybe the theorists should be looking into how do we actually develop a data-centric theory of computing. So if you look at the theory of computing, probably many of you have taken classes or are working on this. If you analyze the complexity of algorithms, you use the big O notation. What does the big O notation or big theta notation do? Essentially, you count operations. But I just showed you that operations are not important, right? What matters is memory access. Maybe we need a theory that balances them and that takes into account data. But we don't seem to have that theory. If anybody knows that theory, that'd be great. Everything I try to find doesn't really do it, essentially. Okay, so we have a lot more information on our processing in memory primer. If you're interested, you can take a look at it. We still have time, right? Okay. I'm going now go into a little bit more detail and give you a foreshadowing of what may come. But I'm going to talk about probably a version of processing in memory that's not going to be discussed a lot in the later parts of this workshop, except for one part. But there's a lot more information on our PIM course. This may not be the latest version of it. There's a new version of it. And this is all live streamed on YouTube. If you're interested in learning more, Juan actually conducts this course, and he has a lot of lectures over here. You can take a look. And we also have an SSD course where we increasingly talk about near or in SSD computation as well. And then genomics course, we actually touch these topics. And this is the tutorial that you attend. So let me give you some examples. I think as I said, processing in memory or near memory has been developed in the 60s. I believe we need to think differently from the past approaches going into the future. And we need to be more cognizant of the impact that these computation units may have. But we also need to, I think, define things more clearly going into the future. At the time processing in memory was developed, it was called logic in memory, which is actually a quite good term, in my opinion. But over time, the terminology got muddled. So I'm going to try to clarify it a little bit. I think there are two kinds of processing in memory, only two fundamental types. Now, processing in memory can be done in different places. That's not type, that's location, right? Location is different from the type. So in terms of type, I think there are only two fundamental types. And I like explaining this like this. So you have a processor or logic, and then you have a memory device. Now, today they're separate from each other. Why don't we put the logic or processor, accelerator, CPU, GPU, FPGA, whatever you have in logic, closer and closer to memory? It could be inside the memory controller, it could be near the caches, it could be inside the DRAM chip. All of this is called processing near memory. Essentially, you put logic near memory. But logic and memory are still separate. These are separate things that you design separately, except you get them as close as possible to each other in the extreme case. It could be 3D stacking, and you have some logic and memory that are extremely coupled with monolithic 3D architectures, for example. So, okay, that's interesting. And this is actually easier to do. That's why we have prototypes of processing near memory today. Now, processing using memory has been developed much later. At least we don't know of earlier works in 1960s that talk about this in the same way we're talking about this. Essentially, you have processor, logic, and memory. Forget about the logic and processor. You have memory. This memory device is designed for storage, right? But the realization is that this memory device can also do some computation. Essentially, the device that you have is also capable of doing, has analog operational properties that enable some sort of computation. And we're going to talk about some of that computation. And that's the idea over here. You're using the memory to perform computation without adding logic to it. So I think that's the fundamental distinction, because this really leads to a very different type of processing than adding logic. Of course, you can combine these two, right? You can add logic and also use memory to do the computation, to exploit the computational capabilities that memory has. And I think that's what should happen going into the future. But this is a bit harder. Processing using a memory is a bit harder because in the end, you're exploiting analog operational properties. And clearly, when you do computation in analog domain, even if it's done in a restricted way, you need to be much more careful in terms of the noise issues and the variation issues and the error issues, etc. So I think this is going to be longer term, but I think we have enough evidence from real DRAM chips that this is doable. And I'm going to mention some of these, and later on there will be a talk from Ataberk that will discuss a real FPGA-based infrastructure that we developed to enable some of this. Okay, so in both cases, we're going to talk about memory as an accelerator. So still, memory is an accelerator. It's not a compute unit by itself, but I will mention that we can specialize the acceleration capability to what memory can do over here. And this is a special accelerator because all of these other accelerators that we're designing are bottlenecked by memory, whereas this accelerator has high bandwidth, low latency, low energy access to large amounts of memory. And it can potentially be programmed as a conventional accelerator, but this is going to be a little bit different. You need to still adapt the programming to the type of computation that you can do, as we will see. Okay, let me start simple. But by the way, feel free to ask questions. Are there any questions? Is this all boring? Nobody has left yet, as far as I can see. That's good. And it's morning, so maybe everybody's jet lagged like me. Feel free to interrupt me. Okay, I'm going to start simple. I'm going to give you some examples. I'm going to start simple, something that you can actually do by violating the timing parameters in DRAM chips today, quite reliable. So data copy initialization. Many of you have programmed, and data copy initialization is something you do in many programs, as you can see. It's all over the place. And in fact, I'll just give you one data point. In Google, in the paper that I mentioned where Google wrote, where they analyze all of their data center workloads, according to them, approximately 5% of the execution cycles across all of their data center workloads are spent only in these two function calls, memmove and memcopy. That's amazing, I think. Two function calls accounting for 5% of execution cycles across many, many workloads averaged. So this shows the importance of data movement initialization. Now, how do we do data movement initialization today? Basically, data movement, let's say. Initialization is a special case of data movements, right? Essentially, you write some data into a row. That could be seen as a copy also. But basically, if you want to copy this page, let's say 4 kilobytes to this other page, what do you do today? You have to go through the processor chip. Now, basically, you need to move this source page byte by byte all the way to the L1 cache. If you're willing to heed the DMA overhead, at least to the memory controller. And then move this page byte by byte all the way into the L1 cache and do the copy and write back the data back. Okay, so this is expensive, clearly, in many ways. So why the idea of in-memory copy says, why not just do this directly inside the memory? And I think we should be thinking simple going into the future. Maybe if you give this picture to a 10-year-old child again, I think we should be thinking like people who have not seen all of this processor-centric paradigm with blank slate and fundamentally think about problems. I need to do this copy. Where should I do it? And if you actually do this for every single operation that we do on our systems, maybe we get to a much more data-centric and much more scalable and much more efficient system, as opposed to saying, oh, we do it in the processor. Where else can you do it? Because that's the processor-centric mindset, right? If you cannot imagine where else can you do it, you cannot do it somewhere else. But if you have a blank slate, you say, okay, I want to copy this page to this page. Well, why not just do this? Right? Why do you have to go through the processor? That's the idea over here. This is low latency. This is low bandwidth utilization on the most important system resource, perhaps, memory bus. And this causes no cache pollution, but you could eliminate that today with DMA overhead and no unwanted data movement on the memory bus. So I'm going to show you a mechanism that takes a 4 kilobyte page copy from 1,000 nanoseconds to 90 nanoseconds unoptimized and 3.6 microjoules to 0.04 microjoules. And later, Ataberk will introduce a system where you can do this in real FPGAs, as he will discuss. So basically, the basic idea is very simple. If you look at the DRAM array, it has a bunch of rows. And assume that a row is 4 kilobytes. There are some issues over there that Ataberk will discuss later on. But in the basic idea, if you want to copy one source row, row A, to another destination row, row B, you first activate the source row, which brings the data into what's called a row buffer. These are sense amplifiers, sensing structures in DRAM. They already exist. All of these already exist in DRAM. And then you activate the destination row in the second step, which implicitly deactivates the source row, but the data of the source row stays in the sense amplifiers. And then once you activate the destination row, sense amplifiers are so strong that they drive the data back into the cells that are connected to, which is row B in this case. So basically, we activate source row and then we activate destination row, and that achieves a copy between the source row to the destination row through a temporary buffer. So you move the data a little bit, but you don't move it all the way to the processor, right? All of these structures already exist in DRAM. So essentially, the idea is 2 consecutive activates in the best case, a negligible hardware cost. In fact, you can violate the DRAM timing parameters in existing DRAM chips, and you can get this effect almost completely reliable, which shows that the memory is already capable of this. And this buys you more than 10x latency reduction in a 4 kilobyte page copy and more than 70x energy reduction in memory for that copy. Ignore these bars over here. So you can always ask the question, okay, what if things are not in the same subarray? What if things are in different banks? We have solutions to that, and you can read the paper for more detail, but these are actually superseded by later papers that reduce those values to not as much as this one, but close enough. So basically, we can do memory copy today very efficiently inside a DRAM chip. Now, if you want to go from module to module, that's a different question. That's also interesting, but these works don't tackle that yet. And this is the original paper. Now, 6 years after this paper was published, these folks from Princeton showed that using the infrastructure where we actually did a lot of row hammer study, we actually made it public online, and these folks actually picked up the infrastructure, and they said, oh, we can violate the DRAM timing parameters to mimic this back-to-back activates. And they violated the timing parameters, and they showed that you can actually do row clone in off-the-shelf DRAM chips. So it's beautiful. You can take a look at it. And recently, we actually picked up on their work and developed our own FPGA-based infrastructure and open sourced it that essentially does the same thing and also solves a lot of system-level issues that I'm not going to go into this, but Tabark will give a lecture on this later today. But you can use this actually today if you're interested, as long as you can afford the FPGA, and if you're willing to do FPGA programming, you can actually see the effects of copy on a real application today. And Tabark will mention that. And we're happy to help. And according to our results, the system level benefits are even higher, as you can see, because you actually circumvent a lot of the software stack as well. So this sort of idea can improve both software and efficiency as well as hardware and efficiency. But if you have more questions, Atabark will be here to answer them. And there are also lectures on this topic. Okay, so maybe you say, okay, you cheated, and I've cheated. This is actually not computation yet. This is data copy and initialization. Data movement, it's still important, but it's not exactly computation. So essentially, we can support computation as well. We can support in DRAM majority function, not, and or, as we will see in a little bit, at low cost. And the idea is essentially the same, processing using memory, using the analog computation capability of DRAM, but the way you realize it is a little bit different. Essentially, you activate multiple rows. DRAM has multiple rows. If you actually activate 3 rows concurrently, you get the majority function, as we will see. And this leads to significant performance energy improvement, and this was actually detailed in this micro paper about 6 years ago. So I've also mentioned that new memory technologies enable even more opportunities. DRAM is the dominant memory technology, but people are looking at other memory technologies. I think this is actually very worthwhile research to do. And these technologies are fundamentally non-volatile. The reads are not destructive. Essentially, you may not even need to move the data significantly to enable computation. And also, they have some structure like the crossbar array structure that enables them to do matrix vector multiplication using Kirchhoff's laws, which you cannot do it in DRAM as far as we know today. So I'm not going to talk a lot about these new memory technologies. In the past, we had talks from IBM, for example, where they talked about how they're developing phase change memory technology to do operations. But we don't have that today, I think, unless Juan has arranged for someone. Okay. Okay, so let me give you how we do it in DRAM. Essentially, if you think about DRAM consists of rows of data, right? I'm showing you, so a row can be 8 kilobytes or 4 kilobytes. I'm showing you only 1 bit in that row. So imagine that you could do this operation on 8 kilobytes of data in 3 rows. And then you can actually do this on thousands of subarrays in DRAM. So you can actually do this on millions of bits in DRAM. But I'm going to show you 1 bit. Essentially, you have 3 DRAM cells over here. These are capacitors. If you can activate these 3 cells concurrently, you connect these capacitors to the bit line concurrently. And based on fundamental charge sharing and circuit level principles, if at least 2 of these cells are charged, you should get the charge state at the end. If at least 2 of these cells are discharged, you should get the discharge state at the end. So essentially, final state is a bitwise majority function. Now, bitwise majority function is a beautiful function, actually. If you read Donald Knuth's The Art of Computer Programming, I think one of those chapters talks about the majority and its importance of majority. And I actually agree with that. This is like majority function is used on quantum computing in very different ways. Now, this is interesting. You can do a bitwise majority of 3 rows, millions of bits in each of those 3 rows. Now, if you take C out, if C is 1, you get the OR of A and B. If C is 0, you get the AND of A and B. Now you have bitwise AND and bitwise OR, which is good. Now, what's missing is an inversion, which is a complement, which is a NOT. And actually, it exists. You don't need to add any logic to the answer because it's already here. the sense amplifier is an SRAM structure. Essentially, when you sense the value of one row over here, the complement of that value is over here. And the realization in our paper is that why don't you feed it to a subarray over here? So this requires some changes to the DRAM chips. You cannot actually do this in real DRAM chips by violating the timing parameters, but this exists. So the good thing is now we are functionally complete. And not is functionally complete, or and not is functionally complete. Majority and not are functionally complete together. Essentially, you should be able to, because of the fact that this is functionally complete, you should be able to redesign any algorithm so that it can actually be executed on the substrate. It may require a lot of rethinking of your algorithm, but there are some algorithms that are actually much more amenable to this. In fact, if you're from the database field, there are a lot of database algorithms that operate on large amounts of data in a block bitwise manner. People do bitmap indices, for example. In our original paper in 2015, we actually looked at bitmap indices a lot. People design databases to maximize the bitwise operations they're doing. In fact, I'm going to show you results of this bit weaving database that was developed in 2013. And Microsoft also has this web search engine that's actually block bitwise. And then there are a bunch of other applications that fit nicely. There may be other applications also that are not here. Let me give you some results in simulation from our paper. Essentially, we took this bit weaving database, and this is very good at column scans, etc. If you're a database person, you will understand what this is, but if you're not, don't worry about it. Essentially, we did a bunch of queries, we executed a bunch of queries, and we see significant performance improvements end-to-end on this workload, 4 to 12x performance improvement when you use this M-bit substrate, processing using memory substrate. And we didn't really optimize the system a lot. I believe if you optimize the system, you'll get even more. Okay, if you're interested in this, there's more in this topic. And we have actually also written papers. Now, before I move into this SIM-DRAM, this next work, essentially the paper, the compute DRAM paper from Princeton folks, they actually show that a small fraction of DRAM chips are actually capable of doing this operation. So by violating the timing parameters, they were able to mimic this triple row activation that we showed in simulation and in theory. And they showed that on some DRAM chips, they were able to get the AND and OR operations. This is fascinating. Meaning this DRAM chip is not designed for this. If you violate the timing parameters, you get the bitwise AND and bitwise OR. Now, this means that what we've shown is essentially real. And also it means that this chip is not designed for this purpose. And it's still able to do some of this. So why don't we actually rethink the chip design so that it can actually maximize this computation capability in a reliable way? Okay, so that's one direction, which is the device level direction. I think that's very interesting. But there's also higher level direction. How do we program this? And this is what we tackled in one of our works that was published in AskPLOS a few years ago, a couple of years. And essentially, let me give you the idea. The idea is to be able to accelerate any operation. As I said, this substrate should be capable of that. Essentially, user defines a desired operation. This could be a matrix multiplication, a convolution, or a simple division or multiplication in terms of gates and or not logic. And everyone should be able to do this, I assume. That's a good test question in computer architecture class or digital logic classes, clearly. And then we have a step which generates a majority inverted graph for this. We actually borrow from the design automation community. There's beautiful work that was done by Nani De Michele's group and that was published in DAC in 2014. That essentially is a translation mechanism to majority inverted graph. And then we optimize this majority inverted graph using that. And then the next step is to generate a sequence of DRAM commands that mimics the behavior of this majority inverted graph using triple row activations, row copies, activate and pre-charge commands, essentially. It's a micro program. And it also does some allocation of the rows, etc., but I'm not talking about that. In the end, you get a micro program that's associated with the operation that you're trying. Convolution, and you have a micro program, and this micro program is executing the convolution on the memory control. And then the output is essentially this micro program can be stored in storage and DRAM. So for every operation that you want to be able to accelerate using memory, you have a micro program and you have an instruction associated with it. So if you look at how the user uses this is the block bitwise operation new. And when this is called in a program, which is a sequential execution model, as you can see, so we're not modifying the execution model significantly. This is also a PIM-enabled instruction. We had an ISCA 2015 paper that talks about PIM-enabled instructions. Essentially, the idea is to incorporate an instruction into the sequential execution model that we have today, such that that instruction can be executable on the memory controller or somewhere else other than the processor. And essentially, that instruction gets shipped to the memory controller, and the memory controller executes this micro program, hopefully much more efficiently than you would do it on the CPU with minimal data moment. And that's the idea. Of course, there are a lot of details. You can find this in our paper. I'll give you the key results. Basically, now you can do complex in DRAM operations this way with a more or less programmable way. And we study 7 real-world applications where we see significant performance and energy efficiency improvements, as you can see over here. Again, I don't want to dwell too much on the numbers. You can find all of those numbers online. Any question? Okay. So what else can you do? Now, if the mindset is this way, maybe we should be adding more stuff to DRAM and also exploiting the analog computation capability. In micro, we introduced this Pluto lookup table-based execution in DRAM. This adds more cost to the DRAM hardware, but with lookup tables, you can actually do more complex computations. And I think going forward, we need to support more complex computations, especially in machine learning models. But I will leave it at that. If you're interested, you can actually do this. And this is also fully artifact available, so you can reproduce the code and you can build on it if you're interested. So what else can you do? I think there are other things that are quite fascinating. One of the things that we have been examining using our FPGA-based DRAM testing infrastructure is what else can you do in DRAM? And in 2018, we wrote this paper where we showed that if you reduce the latency to access data in DRAM, you cause some errors. Some of these errors are actually quite unique to the DRAM device, meaning those cells always fail and they form an identifier of the device. So this is essentially a physical unclonable function, which could be very useful in attestation, for example, in security, building trust. So essentially, you can add security functions to DRAM. And this is, again, processing using memory because you're really using the analog operational properties of the device to generate a function that is normally generated in some other way. And similarly, you can generate true random numbers in DRAM. Basically, we also realized using real DRAM chips that when you reduce the latency to access data, some cells you cannot read reliably. Some of them are flaky. They fail randomly, meaning, and they fail randomly pretty regularly. Whenever that cell fails, it always fails. But it could flip to 1 or it could flip to 0. Essentially, this is a good random number generator cell, and you can generate a random number by making it fail randomly many times. And this way, you can actually get true random numbers. So now DRAM is your true random number generator. Now, this is interesting because now you can actually build some security support on the DRAM side. And this was part of the discussion of the DRAM security panel that I was trying to discuss, where everyone was trying to discuss Rowhammer. Okay, so you can actually do this even more reliably, or more, let's say, reliably, of course, but also at higher speed. So there are a lot of interesting works in this area. And of course, you need to design the system end-to-end to take advantage of this. I don't think we have a lot more time left. Let me talk. I'm going to finish the processing using memory part and then talk about conclusion, and then I'm happy to take questions, and then we're going to continue. So just to show you that these operations is using memory is not unique to DRAM. We've been doing this in Flash, in real Flash chips. And actually, in this work that was also published in Micro 22, we showed that you can actually enable multi-operand bulk bitwise operations with high reliability. And you get significant performance improvements, as you can see. This is outside storage processing, which is today's systems across a number of applications. And this is Parabit, which is a prior work that does something related, but we do it much more reliably, let's say. Essentially, this is very low cost and requires no change to flash cell arrays. Essentially, the idea is very similar, except flash chip is more capable. Basic idea is you have, let's say, these operands, 32 operands. And if you actually activate all of them, you simultaneously sense all of them because of the structure of the flash chip, and you get a bitwise end of 32 operands, which is fascinating because now you can do a 32 input AND gates for each bit. Okay, so this actually minimizes the data moment because otherwise you have to move all of that data to the processor. Amazing, 32 operands. Now you do it actually with one shot. Okay, if you're interested, you can read the paper. Now, this actually can be doable in emerging non-volatile memories. This paper actually has shown that you could actually do row clone as well as other operations similar to what we have discussed in emerging memories. And also, there are other things that you can do in emerging memories that I'm not going to talk about. If this was a longer talk, I would be happy to talk about it. But if you're interested, you can actually, people have shown that you can do matrix vector multiplication due to the crossbar array structure of these memories. And there are a bunch of papers that are still coming up in many different conferences. Okay, as I said, I don't have time to talk about processing near memory, but there are a lot of slides. You can find these online. And there will be a lot of talks on processing near memory anyway, and Juan will pick this up soon. But let me, how do I? Okay. Let me go to the conclusion. So all of this part is processing near memory, but a lot of these materials will be covered. Okay. So I think, like pulling back, we want fundamentally energy efficient architectures, and I think that requires us to be data centric. I've given you some processing using memory examples that's actually most energy efficient, more energy efficient than near memory architectures that you will see, and high performance. I think processing using memory is again enabling that high performance well. But all of this is actually done by minimal data movement. Let me conclude. So I think we must design our systems to be balanced, high performance, energy efficient, all at the same time. This will lead us to much more intelligent systems. And I think we've talked about data centric a lot, but we also need to be data driven and data aware in the design of our systems. We need to enable computation capability inside and close to memory, and also everywhere where data resides and gets processed. This can lead to orders of magnitude improvements, as I've shown you with some examples, but you'll see more examples today, even with real systems, as I've shown one example of. Enable new applications and computing platforms. I actually strongly believe this. I think some of the computing platforms that we design are limited because of the fact that we have this cluster-centric paradigm today. If you actually do it some other paradigm, like data-centric paradigm, we can actually design platforms that are free of the huge downsides of processing-centric paradigm that doesn't fit the computation. Like in sensor processing, really, you have a huge amount of sensors. Cluster-centric just doesn't fit this distributed computation model. Genomics is another example. And this could also enable a better understanding of nature, in my opinion, because nature is not really processor-centric as far as we know, and who knows what else. So I think the future is truly bright, but we do need to do the research and design across the computing stack. And there will be a lot of interesting research questions that we will tackle. I will finish with this question, not question basically, but with this picture over here, because I like thinking about this picture. So there used to be a time when neuroscientists and psychologists were trying to use computers as a way to better understand psychology or human brain. They gave up on that because computers is in no way similar to this thing over here. This is a compute device, at least that's the way I see it. And this compute device is really not processor-centric. There are some principles that we're incorporating to our systems from here, but the fundamental way of operation of this, we still quite don't know. But what we know indicates that computation, communication, and storage are coupled in some way that we don't completely understand, but it's completely different from how we design our systems today. Okay, this is a good place to stop because I'm out of time, but I'm happy to take a couple of questions before leaving the floor to Juan. Yes, in the back.
That was an interesting introduction. And I'm wondering, so remember also the slides I want to have only no points with reliability points for every situation.
I couldn't quite understand it. Depending on the size, only row on what? Oh, okay. So, okay, in the PyDRAM FPGA. So you're going to have a talk about that. But basically, what we have enabled in that FPGA prototype, PyDRAM, is row clone. You could also modify that FPGA board to violate the timing parameters so that you can get bitwise AND and OR. We didn't release that yet. You can ask that question to Ataberk. We're actually looking into that right now, releasing it. But you can also do the random number generation. So you can actually have a random number generation call in your program that gets shipped to the FPGA, and the FPGA memory controller violates the timing parameters so that you can actually generate random numbers using the D-range mechanism that I mentioned. So this platform can be expandable also, and we're working on it, but if people are interested in contributing, we're also happy to get help and also provide help. Yes, please.
Yeah, I think that what about the memory compute file?
Yep.
Things like last or 3 or 5 directions, right? Where we have relatively small business memory, and then we invest it on making relatively small piece of memory. Is it still, in memory useful for this kind of direction?
Yeah. So that's a good question. In the end, I think we need to. All of our systems need to be heterogeneous, in my opinion. I'm not suggesting that we should get rid of the CPU, GPU, FPGA, compute-centric part. We should use the compute-centric part where actually it can be useful for that computation. So the type of computation you described probably is better executed on a CPU. But this also requires us to rethink the communication that happens after that computation, right? So I think certainly we need to think how we do the computation going into the future.
I want to ask that. Did you already make some computations by some principle operation? Okay, this is the kind of operation that you can do maybe in memory sense. Is there something different? You better do this CPU or you.
Yeah. I think you're asking this sort of question, maybe. Yeah, this is, I don't know if Geraldo or anyone's going to cover this, but basically we have been looking into this. This is one attempt. This is not the only attempt. And essentially we have the same question and we analyzed a bunch of applications and we tried to answer the question that you have. It's not as, let's say, it's limited, but I think this is a good start. So basically we try to identify the bottlenecks. Some bottlenecks are basically your compute bound, essentially, and you should execute in the CPU. Some bottleneck is basically your DRAM latency bound. And then the question is, where should you execute? It becomes dependent on your data set, etc. So essentially, if you're interested in this, I'd recommend looking at this paper, which is also fully open sourced. I will mention the paper. It's called DAMU. But we also have another paper that was recently published that essentially tries to answer a similar question. This is Nika's paper, Nika Mansouri Ghiasi, on essentially deciding what to offload. And this also takes into account some communication between different blocks, which this doesn't take into account as much. So I think this is work in progress, and I think this is a great research topic, spanning both hardware and software, in my opinion.
Thank you.
Sure. Yes.
Hi, thank you for the great talk. So I was wondering, like, you're computing using unlimited pattern, does eliminate all the data transfer overheads of power. But if you're in the service, you're using more power to actually do the computation. So does that like violate any power constraint or please that might cause problems?
Yeah, I mean, that's also an excellent question. We have a lot of excellent questions here. Essentially, it should not cause problems if you design the DRAM with the mindset that it's a compute device. Essentially, you need to design the DRAM so that it's not just serving the processor, but it's actually an active compute device, meaning that it needs to have more power and needs to have additional capability for that power. So especially if you want to enable it thousands of subarrays. In one subarray, you can do it in existing systems. But if you want to enable it in the large scale, I believe you need to rethink the power in DRAM as well. And also a reliable. Okay, who wants to go first? I think you raised your hand first. So.
Question is how we program this.
Yeah.
Have those all different components. Program things like
yeah.
I think the Hynix stand, one thing you know how to program.
Yeah. Yeah. I mean, I don't have a satisfying answer to you, but this is something that we will tackle in the rest of the tutorial. Feel free to ask again. I don't think we have a single way of programming these things at the moment. I mean, I will mention this is something that we were quite interested in also, if I can find those slides. There are different programming models, clearly. When we actually were looking at initial things, okay. For example, we've looked at message passing based programming models for a particular accelerator, and I think this has its place. How do you program processing using memory is a totally different question. I think basically the type of programming seems to depend currently on the type of computation that you can do. Near memory processing, you have general purpose cores. It's a distributed system of accelerators. I'm not going to talk about that. But essentially, we did a message passing programming model that's relatively similar to existing distributed system frameworks, which is nice. And we also envision that if you have PIM-enabled instructions, somebody can insert those instructions and the programming hopefully is easy. Now, which one is the best way? I believe it really depends on the type of processing, but the jury is really still out on this one. This is another area where people in programming languages and compilers and architecture can work together. I think that, but maybe I will liken this to GPUs. For example, if you think about GPUs, like 20, 30 years ago, people were trying to exploit GPUs, and they had actually very specialized ways of getting at the specialized hardware. And over time, a dominant programming model emerged, and NVIDIA was very successful in promoting that model, right? Is that the best programming model? Maybe not, but it's a very dominant programming model that's useful for many people. I think in PIM, we're not there yet. We may need still 10 years or so. But in the meantime, people can still exploit Okay, next. Juan, feel free to stop the questions if you're running out of time.
When it comes to big class operations, from my understanding, they are bounded bound in port-centric.
Yes.
I'm wondering what's the difference in the effective bandwidth that we can get even with memory and other memories.
Yeah, so that's a great question. It depends on how many subarrays you use, but it's easily at least an order of magnitude. And so an order of magnitude, you can actually multiply it with the number of subarrays, so it's actually very large. We covered that in our papers, but I don't know the exact number, of course. Okay, one more question. Sorry, could you say it again? There's a lot of noise in the back. So. Sure. I see. Yeah. So improvements in terms of the computation capability, right? So I don't know. I don't see that. I mean, even if we have technology scaling problems at the low levels, I think we can still get significant benefits because the benefits you get are going to be coming from something else. So even though capacity, let's say, may not scale as fast, that's, I think, more reason to actually push the computation over there because we're not going to get benefits just from technology scale. We actually can exploit the existing technology much better if we push computation to the device. Now, if things become more unreliable, then there's another issue. Of course, we need to find reliable methods of doing computation, which is actually part of the research that goes on in processing using memory today.
Can enable really high bandwidth, but when it comes to practicality, there are a lot of problems. How do you see the future?
Yeah, I mean, these are all great questions. I cannot predict, of course, the future. I think there needs to be research to enable these technologies. We're not there yet, no question about that. In fact, with phase change memory, when we were doing the research in 2007 and we wrote our paper in ISCA 2009, we believe that there would be, at this point, like today, we'd be in a better place, but we're not in that place. It's difficult. I mean, with emerging technology, it's always difficult. It takes time. And you need to find the right technology. You need to find the environment to take advantage of it. I think it's good to work on it, but I don't have a solid answer. That's why this talk is about DRAM and not emerging memory technologies and flash, right? DRAM and flash are the biggest technologies, and they're still strong, regardless of what they have. But that doesn't mean that, like, flash was an emerging technology in the 1980s. It didn't emerge until early 2000s, right? When iPods and other stuff became more popular. So essentially, it takes time for an emerging technology to emerge. And I believe that some things will emerge. The question is how good they will be. But regardless of how good they will be, I think they all will have similar issues in the end. So we will need computation next to that. Sure. Okay. I think I will now leave it to Juan to do the next talk. Thank you for the engaged audience. I'll try to.
Thank you, Onur, for the great talk, and thank you, everyone, for so many questions, so many good questions. I think, I mean, even though we are not going to have so much time for the next talk, for what we are going to, or what I'm going to explain now, but yeah, the materials are there. I'm also going to give you many references and links of second. I'm going to give you, as I said, many references and links of where you can find more information about the systems that we are talking about. Yeah. I guess I must be sharing my screen.
You're sharing the presenter view.
Okay. I was muted, so probably people couldn't hear me in Zoom and YouTube, but hopefully now I fix it. Okay, so yeah, we have extensively analyzed this system, and this is the paper that we wrote and published last year. But now I'm going to introduce some characteristics of this architecture, and after that, we'll briefly go over the other real PIM architectures that we are aware of. And next, I will start my introduction to programming this HB-MEM PIM system. As I said, this was, well, HB-MEM started around 2015, 2016, and they filed this patent that essentially in the abstract tells us what we have here is a memory circuit containing a memory array and a first processor. This first processor is what I just call DRAM processing unit or DPU, and there is a control interface for a central processor, which is the host, that is a regular CPU, to access it and control it. So the memory banks, the PIM memory banks, are going to become accessible to either the DPUs, the PIM cores, or the CPU, depending on the stage of the execution. And this is also from the patent, where you can see the CPU or a system on a chip, and then the DIMMs with the multiple chips, including their memory arrays and the processors. So this is another view of the system where you can see the main memory. There are still DIMMs of main memory, let's say DDR4 DIMMs, the host CPU, and the PIM-enabled memory. And we can take a closer look at each of the PIM-enabled DIMMs. As I said earlier, these have typically 16 chips in the current generation, 2 ranks of 8 chips, and inside each of the chips, there are 8 64-megabyte DRAM banks that UPMEM calls MRAM, and also the 8 processors or cores, DRAM processing units or DPUs. So in total, there are 64 DPUs per rank. Now, going into a little bit more detail about the DRAM processing unit, what we can see is that it's nearby the memory bank, and it has some instruction memory, a pipeline, and a local memory. In this other view of the DRAM processing unit, you can first see the control and status interface for the host to communicate with the PIN cores, with the DPUs, and the DDR4 interface for the regular access of the host to these 64-megabyte DRAM banks. And so, as I said, inside each chip, there are 8 of these, and these ones can be accessed through this DMA engine by the core pipeline. And in between, you can see an instruction memory and also something called, also an SRAM-based memory called WRAM, which is basically a scratchpad or a software managed cache. And then we have the pipeline on the left-hand side. A few more details about the pipeline in the current system, the one that you can access today. This pipeline runs at a frequency of 425 megahertz, and it's fine-grained multi-threaded. So it can run up to 24 hardware threads. And as you see, the pipeline has 14 stages, like typical stages like dispatch, fetch instruction from the IRAM, read operands from the register file, format them, and then perform the ALU operations or the access to the scratchpad. As I said, this architecture is fine-grained multi-threaded. I'm pretty sure that you all are familiar with fine-grained multithreading, but this is basically a technique that allows us to hide latencies in the processor by switching the thread every single cycle. So this one is an in-order processor. What is going to happen is that in every cycle, there is a thread selection. It goes to the next thread, and it goes to the next instruction for that thread, and it launches it onto the pipeline. So we are going to have as many thread contexts as threads we can run or we can execute on the pipeline, and each of them is going to have its own PC and registers. There are a couple of slides here about fine-grained multithreading, but if you want to learn more, you can watch, for example, this lecture by Professor Mutlu. But yeah, this is the pipeline. Again, just to summarize, fine-grained multi-threaded pipeline that can run up to 24 threads, and it has 14 pipeline stages. What are the type of instructions that these DPUs support? The ISA, you can find all information here in the SDK documentation, but basically it's a specific 32-bit ISA. It's scalar, in-ordered, and multi-threaded, and it allows compilation of 64-bit C code as well through the LLVM clan compiler. For you to just see some code, there are this example for one of our micro benchmarks for a 32-bit integer addition. At the top, you see the C-base code, and at the bottom, you see how we, you see the compile code. Actually, I don't know if the highlights can be seen here because they are in yellow. Now, probably you see something. But yeah, anyway, as you see, we have First of all, here we are allocating some memory space. This is in the WRAM, in the scratchpad. This memory allocation has to be explicitly done. And then there is a for loop here going over all the elements of this buffer in the scratchpad and performing some operation, in this case, adding some scalar. So this compiles to this instruction, first of all, for address calculation, loading from the WRAM, from the scratchpad onto a register, and then performing the addition, and finally storing the result back to the WRAM. I'm not going to continue talking about the architecture right now. You can watch some of the lectures that we have online where we provide many more details, or you can check our papers as well. But let me give you some important and interesting takeaways that come out of this work. The first one is that, well, we did some analysis similar to the roofline model in order to see, or in order to measure what's the maximum compute throughput that we can achieve for different values of operational intensity. As you can see, something from very, very low, like one operation every 2048 bytes accessed from memory, up to something relatively high of an operational intensity of 8 operations per byte. And as you can see, we can differentiate here. This specifically is for a 32-bit integer addition. We can differentiate here between a memory-bound region and a compute-bound region. And basically, in the memory-bound region, what we see is that as we increase the operational intensity, the compute throughput increases. In the compute-bound region, the throughput remains flat. And also, for each of these dots, they represent the different number of threads, or by the way, I didn't say that earlier, but they are called tasklets by UPMEM. These PIM threads or tasklets, because depending on how many of these threads you use, you will get more or less throughput. And then there is a point in between these two regions that we call the throughput saturation point. And as you can see, for the 32-bit integer addition, this throughput saturation point is as low as 1/4 operation per byte. So what does it mean? And it's even worse for other data types and operations. And what does it mean? What it means is that basically this architecture is fundamentally compute bound. So what we expect is that real workloads are going to stay on this part here in basically all cases, unless you are just moving data around. And this is an interesting observation, I believe, because it's something completely different to what we can observe in the usual processor-centric systems, in CPUs, GPUs, where most of the workloads are compute-bound. Our observation here is that most of the workloads will be compute-bound in this architecture. So the biggest problem that we have so far in processor-centric systems is wiped out. Now, if you are curious, because I'm pretty sure that you're curious about the comparison to CPU and GPU, let me show you some results. These are for some benchmarks that we developed, a benchmark suite of 16 different workloads. They are publicly available. You can use them. And in this presentation, there are links to the repository for sure. After our analysis, we were able to differentiate between more PIM suitable and less PIM suitable, or more UPMEM suitable and less UPMEM suitable workloads, as you see. And those that are on the left-hand side, which are more suitable for this system, have some common characteristics. First of all, they typically have streaming memory accesses, and that's the way of maximizing the memory bandwidth. That's a way of getting the most from the tight communication between the PIM core and the nearby DRAM bank. These workloads also have need no or little inter-DPU, inter-PIM core communication or synchronization. And that's important because even though you see that in each chip there are 8 DRAM banks and there are 8 processors, each of the PIM cores, each of the PIM processors can only access its own bank. So what this means is that every time that they need to communicate or access data that resides in another bank, this communication will have to happen through the host processor. That's why the best performing workloads here don't need or need very little inter-DPU synchronization. And even though I agree with you that this might be a big issue for many important workloads, but for other workloads, as we are observing in our analysis and in our implementations, is not that terrible. We are going to talk about workloads after the coffee break and even after the lunch break as well. And I will show you that, for example, for machine learning training is something that is relatively tolerable. And the last characteristic is that these workloads have no or little use of integer multiplication, integer division, and floating point operations. And why is that? Because the architecture only supports 32-bit integer calculations, but indeed, multiplication and division are also emulated, as well as floating point operations. And a 32-bit integer multiplication might take up to 32 cycles, basically because it's using that shift and add routine. And this is kind of an issue for some important workloads for sure. Apparently, this is a design decision from UPMEM because the type of workloads that they are mainly targeting don't really require 32-bit multiplication. Still, there is an 8-bit multiplier, and that's natively, so 8-bit multiplication is natively supported. It takes one cycle, and that's good, for example, in the context of machine learning or neural network inference, where quantization can be applied. And this is something that I will mention at the end of the, well, at the end, and in the lecture that we will have, the lecture that we will have at the after the lunch. Sorry, I was listening to someone here, so I don't know if someone was trying to tell me something. Anyway, let me continue. So with these three characteristics, a workload is potentially suitable to the UPMEM PIM architecture. Some more observations or some more takeaways. Well, no, this is just repeating what I just said, so I will skip it. And this is kind of a summary of the comparison that we did with the CPU and Intel Xeon CPU and a GPU in this work, and the first characterization work that we did, we compared to an NVIDIA Titan 5. And as you can see, for those workloads that are more PIM suitable or UPMEM suitable, we observe an average speed up of 2.54 over the GPU. Yeah, these codes, the codes that we develop and we use for analysis are all publicly available in our repository. But as I was saying, and also Onur said, this UPMEM PIM system is not the only one. The second one that appeared, according to what we know, is this Samsung FinDRAM or HBM-PIM is the one that we are going to cover in one of the invited lectures today. It was announced in 2021 with the purpose of targeting mainly machine learning inference or neural network inference. And as you can see here, it's based on HBM2 memory. There are some of the layers that are conventional layers of HBM2, but others have been modified to integrate some small processors, some small SIMD units that are called PCUs. And actually, as you can see here, there is one of these PCUs per every 2 banks. And this is how these SIMD units look. Well, nearby the cell array, the SIMD units are, they have 16 lanes and they operate on 16-bit floating point operands. I'm not going to say anything else because we have the talk this afternoon, but we also have our own lectures about FinDRAM or HBM-PIM, and this is one of them from the previous semester. Onur also mentioned this one from Samsung as well, called AxDIMM. In this case, the idea is it's a DIMM-based solution, and the idea is to use this AxDIMM buffer to integrate a small reconfigurable unit, a small FPGA that can be programmed for a specific application. And in the first work that was published by Samsung, what they did was placing there like a couple of near memory accelerators for recommendation system, mainly targeting the sparse embeddings of the DLRM recommendation system, because that's the most memory-bound part of those systems. And here is, you can see sort of a timeline or execution flow or how to perform the computation there. The very first thing to do is to write the embedding tables to the memory, and after that, the CPU needs to change the mode by writing in some configuration register here, and at that point the execution can start in the near memory accelerators, and in the meantime the host is going to be checking also one of the configuration registers to see when the computation has finished. We don't have time to go in detail over this, but here you can see also a link to one lecture. And from SK Hynix, there was also a very interesting talk about this architecture, also targeting machine learning and artificial intelligence, same as HBM-PIM. And we had also a couple of folks from SK Hynix presenting in our Plus tutorial. It's kind of similar to HBM-PIM, but instead of using HBM2, here is GDDR6 memory. But again, there is a small processing unit near each of the banks. And this processing unit, because of the type of workloads that they are targeting, neural network inference, contains an array of multipliers and then another tree in order to perform dot product operations. Something that I like from this architecture is that it supports also activation functions. It has some small unit here, and it also has the ability to play some reserve some rows for lookup tables that can be used for more complex activation functions. And they also have this supplementary SRAM buffer to move data between the DRAM banks. This is also covered in one of our lectures. And the last one that we are aware of, this real-world PIM architecture, actually is not the last one because I see that I have a couple more slides. But anyway, this one from Alibaba called HB-PNM that was presented by Dr. Deming New in the first tutorial in HPCA. This one is for recommendation systems as well. And it's fabricated using this hybrid bonding technique. There is a DRAM die and a logic die that are glued together. And as you can see in the logic die, there are different engines or accelerators that are specialized for different parts of the recommendation system. For example, the coarse grain matching stage runs on this match engine, and the fine grain ranking runs in this neural engine that is sort of a systolic array for the matrix multiplication, etc. But you can also learn more about this in one of our lectures. And there are more efforts. I'm also aware of this company from Israel called Neuroblade. They don't have, or I don't have many details about what they are doing, but apparently they also have a processing near memory system with some processors, according to what I've read in some posts, similar to GPUs, kind of SIMD units, I guess. But yeah, that have direct access to memory, and this is also specialized for data analytics, machine learning, etc. So as you can see, there are a variety of real PIM architectures. There are some differences between them because some of them are near bank or near chip. Others are more general purpose like UPMEM, while others are more specialized like DRAM or AIM or HBM-PIM, targeting more specific applications, different execution paradigms as well, fine-grained multi-threading, SIMD or systolic arrays, and they have support as well for different data types, especially depending on the applications that they are targeting, and different types of memory as well, DDR4, LPDDR4, HBM2, GDDR6, etc. But most interestingly, I believe, is that there are some common characteristics. The first one is that there is a host processor, either a CPU or a GPU, that has access to a standard main memory and PIM-enabled memory. The PIM-enabled memory contains multiple processing elements that have high bandwidth and low latency access to the memory. And these PIM processing elements are relatively wimpy. They run at a few hundred megahertz, and they don't have large register files or caches. And they may need to communicate via the host processor, especially if they are in different chips. So this is more or less how one of these real-world current processing near memory systems looks like. On the left-hand side, you see the host CPU, the standard main memory, and the PIM-enabled memory with whatever configuration they have. And this is just a summary of those common characteristics. Now it's 11 a.m., but I want to take, let's say, 5-10 minutes of your coffee break to introduce how to program the general purpose PIM system from UPMEM. We say that it follows the accelerator model, basically because it behaves as a conventional loosely coupled accelerator where we need to explicitly move data from the main memory to the PIM-enabled memory and then launch the execution on the kernel. This resembles GPU computing, right? You first have to move something from the GPU memory, from the CPU memory to the GPU memory, then compute in the GPU cores, and then write the results back. So this is the accelerator model, and that's also what the patent from UPMEM explains. After we launch the computation onto the DRAM processors, on the PIM processors, the host needs to keep checking when the computation has finished, typically accessing some memory map registers. Let me start with a simple example. The first programming example is vector addition. Vector addition, as you all know, the only thing that we are doing is performing the element-wise addition of two vectors, right? So how are we going to partition this computation over the cores, over the PIM cores or DPUs? Well, we are going to divide the arrays into equal size chunks, and we are going to send them to each of the PIM processors. And then inside each of them, we are going to have multiple threads running, tasklets, as I said earlier, that are going to take their chunk of the workload and perform the computation that they have to do. This lecture is introducing how to program the UPMEM PIM system, but the best reference is the UPMEM SDK documentation. And there, from that documentation and also from other documents, we gathered some general programming recommendations. The first one is to execute on the DPUs portions of parallel code that are as long as possible. This definitely makes sense as in any other accelerator, because if you have to pay the cost of a data transfer, you want to amortize that cost. Second thing is that we prefer to offload independent data blocks so that the DPUs, the PIM cores, can operate on the data that they have received in a completely independent manner, because otherwise they will need to communicate through the host processor, and that's going to be costly because it entails CPU, DPU, or CPU PIM and PIM CPU communication, right? Second thing is that if you need to maximize the parallelism, so use as many DPUs as possible. If you can use all DPUs, you have enough input size for all DPUs in the system, then just use them. And the final recommendation is that launch at least 11 tasklets or PIM threads. And this number, according to what we have seen in our analysis, is tightly related to the number of pipeline stages. If you have a fine-grained multi-thread pipeline and you are going to issue a new instruction from a different thread every cycle, you want to keep the entire pipeline busy, right? Especially for this architecture where we know already that most real workloads are going to behave as compute bound. So if you want to accelerate those workloads that are going to be compute bound on this architecture, the best you can do is to make the better use of your resources and by keeping the pipeline fully busy. So when it comes to programming these DPUs, the very first thing that, or this PIM system, the very first thing that we have to do is reserving the number of DPUs that we want to use, because we may have multiple applications running on the server, right? And all these applications potentially have access to the PIM cores, right? Then they may not need to use all the PIM cores at the same time. So that's why we need to allocate the DPUs, and that creates what is called a DPU set. You can do it with this simple DPU alloc. So, and also over the course of a program, we can change the number of DPUs that we use depending on the specific stage of the program. For example, one of the workloads that we implemented is Needleman-Bunch, is a sequence alignment algorithm, sequence alignment application. As you probably know, here we create a dynamic programming table that needs to be filled by anti-diagonals. And the size of these anti-diagonals changes over the execution of the program. In the very beginning of the execution, when we start in one corner, it's just one element, then two elements, and so on and so forth, right? And when we are in the middle, those are the longest diagonals. So the number of DPUs that we want to use in each stage, in each iteration of the algorithm will change. And that's something that you can definitely do by, in every iteration, you free the DPUs that you allocated in the previous iteration, and then you allocate as many DPUs as you need in this time. Next thing to do after the DPU allocation is to load the binary. We have to, the compile binary on the host processor, we have to send it to the DPUs and place it in that instruction memory, instruction RAM that I showed you in the beginning. And that's also pretty simple to do by using this DPU load. By the way, well, there are some considerations here. We can have different versions of this binary and send them to different DPUs, that they can be run in different parts of the program. And this way we exploit task level parallelism. And then remember, this is a loosely coupled accelerator, so we have to explicitly transfer data between the CPU memory, between the main memory and the PIM-enabled memory. We typically call them CPU-DPU and DPU-CPU transfers, or CPU-PIM and PIM-CPU transfers. And there are different ways of doing these transfers. Serial, when you target a single bank, a single DRAM bank. In parallel, when you target multiple DRAM banks, and also broadcast transfers. In this case, we are transferring a single buffer to all or to many of the DPUs. And these are the APIs for serial transfers, DPU copy to, DPU copy from, and well, they have their specific syntax that is explained here in this slide. And we also have the API that we need for the parallel transfers as well, and for the broadcast transfers, DPU broadcast too. Unfortunately, I don't have time to go into the detail of all of these, but you can watch our lectures if you want. It's obviously possible to use different types of transfers in the program, depending on what we have to do. This is just an example of an application or a workload that uses parallel and serial transfers. And understanding this understanding the data transfers is also important, because remember, there is no way of communicating DPUs directly. So everything needs to happen through the host processor. So that's why, yeah, we need to do this communication using CPU, DPU, or DPU, CPU transfers. We did some analysis of how fast are these transfers. Basically, what we observed is that they are, as you could expect, bound by the actual DRAM bandwidth, because the PIM DIMMs are in the regular memory slots. So at least they are DDR4 DIMMs. So let's say the peak bandwidth that you can get is basically limited by this 16.88 that we measured there is very close to the 19 gigabytes per second. That is the maximum theoretical bandwidth of DDR4 DIMMs. Maybe something that you are asking yourself here, because we have multiple chips in the DIMM, we need to change how the data is mapped in order for the PIM cores to access an entire value, an entire element, or an array of elements in their own DRAM bank. Well, the runtime system, the UPMEM runtime system handles this. They do this kind of transposition, or they arrange the data by software in the way that is needed in order for each PIM processor, each PIM core to have access to whatever the user defines as the data that they want to that PIM core to access. We did a lot of analysis. This is a link to one of our micro benchmarks. But more interestingly, after we have transferred the input data, what do we have to do? We have to launch the execution of the kernel with this DPU launch on the DPU set. Remember that the DPU set is the set of DPUs that we allocated earlier. And there are different ways of doing these transfers, either synchronous or asynchronous. If it's synchronous, the CPU, the CPU, the main thread of the CPU will stop here until the execution of the kernel finishes. If we want to do an asynchronous execution, as we do in CUDA kernel launches, in GPU kernel launches, for example, is also possible to do. And here you can also see one slide about how to pass the input parameters. It's again using the same data transfers, the same type of data transfers, but now in this case, we are just transferring, well, typically a smaller array. Remember that we are talking about vector addition, and this is an example of the vector addition kernel. In the end, it's pretty simple, as you see. It's basically C code with some library calls. We need it's an SPMD programming model, single program, multiple data. So here we are using scalar threads. So we write this for a single thread, and that's why the first thing that we do is using the or gathering the tasklet ID, the thread ID. And then this thread ID will have to go to the MRAM, which is the DRAM bank, and read data from there and bring the data from there to the WRAM, which is the scratchpad. Because all operands are usually or typically moved from the MRAM to the WRAM, and then the pipeline is going to access the data from that WRAM, from that scratchpad. So that's why we need to use these MRAM WRAM transfers that are called MRAM read, same as at the end, we will have to write the output results back to the MRAM using this MRAM write. And this is the, let's say the kernel itself is just the vector addition. This buffer A and buffer B have previously been allocated in WRAM, in the scratchpad, and the core, the pipeline accesses the data from there, performs the addition, and writes back. And I'm going to finish in a couple of minutes, because I also want to introduce the intra-deep DPU synchronization. The tasklets can synchronize in the same way as we do with P threads, for example. We can use mutexes, we can use handshakes, barriers, or semaphores. And this is useful for certain operations, for example, the parallel reduction. In a parallel reduction, what we will normally do, same as we can do in other parallel processors like GPUs, is dividing the workload or dividing the input array into the multiple chunks assigned to different tasklets. Each of them will obtain a local sum, and then we will perform the final reduction. We can perform this final reduction with just using a single tasklet. After using some barriers here, we can have one single tasklet performing the final reduction, or we can also implement sort of a tree-based reduction, right? As that can also be implemented with barriers, as you see. So in every iteration, half of the threads retire, and we will be able to perform this final reduction in log n. Right? And there are ways, different ways of implementing this as well. You can use barriers, but they are pretty costly in the current generation because these synchronization primitives are software-based. But you can implement them faster, for example, with handshakes. This is indeed one of the tasks that we are assigning in the hands-on lab that is available. And here you can see some results from or analysis, comparison of these different implementations. And this is also a link to another lecture on parallel reduction on GPU if you want to extend on that. And prefix sum as well. We have, that's also a very important parallel primitive. There are hierarchical ways of implementing the scan operations. So here we divide the input into the different tasklets, and then each tasklet perform their local prefix sum. And after that, we will need to communicate. There are different algorithms to do that. We don't have time for the detail, but for example, scan add. We would first do this per DPU inclusive scan after having assigned one chunk of these to each of the tasklets. The tasklets perform the local scan, then communicate internally inside the DPU. And after that, at some point, we'll have to return the control to the host for the host to perform this scan of partial sums, and in the end, finally update or add those offsets to the previously computed partial scans in order to obtain the final inclusive scan. This is an example of an inclusive scan. That just leave this for your own study. This is also some analysis of how many accesses we need to perform to memory, another implementation, reduce scan, It's typically more efficient when we have large arrays, and that's actually something that we have compared as well. And here you can see some plot with our results. I think I'm going to stop here because I don't want to take more time of your break. Here you can find the link to the documentation, and there are also a couple of links to lectures that I have delivered about programming this PIM architecture. If you want to take the advantage today and make use of the real system, you can directly go ahead and be brave and start using it. You can download some of our codes and just run them to have the experience and see how things go. But if you are, you are brave and want to really program, etc., another day, you can watch some of those lectures, because there is also the SDK comes with a simulator, and even if you don't have access to the real system, you can use that simulator in the SDK for your playground. Thank you very much for your attention. I don't know if there are any questions. Please go ahead. We can also continue talking during the break. And hopefully we will be back at 11:20 or 25 for the first of our invited talks. Thank you. Izzat, are you there?
Hi, Juan. Yeah, I'm here.
Can you share your screen?
Yes, 1 second. Can you see it?
Okay. Feel free to start your camera and speak as well, because I want to make sure that people can hear you.
Okay. Is the audience back?
Hello?
Hello. Yeah. Can you hear me? Hello. Can you hear me? Hello. Hello, Juan. Hello. Can you hear me?
Yeah, I cannot hear you well. I don't know if I might need help from someone.
That's weird. And I'm not doing anything different. Is this better?
Can you speak now?
Yeah. Hello. Can you hear me? Hello.
Yeah, I can hear you better now.
Okay.
Can you guys hear at the back? Okay, great. Okay, so then, yeah, I'm going to introduce you. Just give me 1 second. Yeah, it's my pleasure to introduce Professor Elak. He's a professor at the American University of Beirut, and he's going to present this work titled High-throughput sequence alignment on using real processing in memory systems. This has been very interesting experience. Professor Elak is an assistant professor in the Department of Computer Science at the American University of Beirut. His research interests are in application accelerator and programming support for emerging parallel processors and memory technologies, with a particular interest in GPUs and processing in memory. He received his master's and PhD degrees in electrical and computer engineering at the University of Illinois at Urbana-Champaign, and his bachelor's, the electrical and computer engineering at the American University of Beirut. So, Izzat, if you're ready, please go ahead.
Yeah, hi, thank you, Juan, for the introduction, and thank you all for attending. So I'm going to be talking today about a project we've been working on about high-throughput sequence alignment using real processing and memory systems. And this project, kind of the primary work has been done by my master's students, Safa Adyab and Amir Nasruddin, and of course, with a lot of collaboration with Juan and Mohammed and Onur at ETH. I'll start. The work that I'm going to present has been published at Bioinformatics 2023. It's a bioinformatics journal, and you can find also the archive preprint at this link, and also you can find the source code for the framework that I'll be presenting on GitHub. Okay, so just to summarize the talk before I start, the main points in this talk are the following. Sequence alignment is a memory-bound computation on traditional processor-centric systems, and because it's memory-bound, we look at processing in memory, which overcomes the memory bandwidth bottleneck by placing cores near the memory. So to be able to leverage processing in memory for sequence alignment, we propose a framework called alignment in memory. And this framework targets real PIM systems, particularly the UPMEM system, which is the first real PIM system that kind of has been put into the market, and also supports many different alignment algorithms like Needleman-Wunsch, Smith-Morton-Goto, JNASM, and WFA, the wavefront algorithm. Our results show that we can get substantial speedups over CPUs and GPUs, and kind of with that summary, I'll go ahead and present the work. So an outline of my work, it's going to be broken down to 4 main parts. The presentation is going to be broken down in 4 main parts. I'll start with a background on sequence alignment. After that, I'll give a brief overview of processing in memory. Then I'll talk about our framework for doing sequence alignment using processing in memory. Then finally, I'll present the evaluation of our framework on a real PIM system. So to start with background on sequence alignment, so genomes are basically the set of an organism's genetic instructions. So it's composed of, it's our DNA basically. It's composed of a lot of base pairs, which are mainly A, C, G, or T. The human genome, for example, has 3.2 million base pairs. And understanding genomes, analyzing genomes is very important, has all kinds of medical applications. So finding genetic variations, predicting the presence of microbes, monitoring disease outbreaks, personalized medicine, all of these, being able to analyze genomes is a very important thing. And one of the fundamental components of analyzing genomes is extracting kind of the base pairs. So you have sequencing machines that can extract the base pairs inside of a genome, but they can't extract kind of for humans the whole 3.2 billion sequence. They extract them in small fragments or reads. And depending on the sequencing technology, these reads can be small, ranging from 50 to 300 base pairs, or they can also be kind of very large with the newer technologies. Now, once you have these base pairs, you need, if you kind of sequence a genome of a human, for example, you have their reads. You want to go back and put these together. A typical way of doing this is mapping these reads to a reference human genome that you already have, and this act of mapping these reads to reference human genome requires sequence alignment. Taking these reads and then aligning them to different parts of the human genome to be able to find where the best match is. Now, there's a lot of algorithms for doing sequence alignment out there. You have some quadratic dynamic programming algorithms like Smith-Waterman and Needleman-Wunsch, and then also some of the newer state-of-the-art algorithms like GNASM, WFA, and WFA adaptive. I'm going to give an example with Smith-Waterman, and just for those who are not familiar with sequence alignment, just so you have an idea of what the computation is, in order to motivate why this computation is memory bound and why it would benefit from PIM. So when you do sequence alignment, let's say I have these two sequences, AACC and another sequence AATC, and I would like to align these sequences. I would like to say, what is the best, are these two sequences a good match? And when I align them, I want to do approximate alignment. So I want to be able to accommodate, for example, if there has been an error in one of the sequences, like a certain character was accidentally inserted or accidentally removed or accidentally flipped. So to do that, the way it's usually done in the Smith-Waterman algorithm is you fill this scoring matrix. So you have this matrix. You put one sequence, along the rows, one sequence along the columns, and you're going to fill this matrix where every field in this matrix represents the alignment score for the subsequences that you have covered so far. Now, when you fill this matrix, there's basically a score when you have a match, a score when you have a mismatch, a score when you have a gap. So that means there's an extra character in one of the sequences that's not present in another sequence. And then you can also differentiate between a gap that you just opened and then a gap that's just an extension of a previous gap. And the way that you do this alignment is you start at the top of the matrix and you make your way down, and at every cell in this matrix, you're going to check what is the score of having a match or a mismatch from this top left cell, or having a gap from the left cell or the top cell. And I'm not going to go too much into the details of this, but the key idea is that you sweep through this matrix from the top left down to the bottom right, and you fill it with scores. And every time you want to fill a cell, you're going to inspect the previous three cells. Now, once you've reached the bottom of the matrix, there's also a trace back stage where you go back up to you go back from the bottom or from the high score back up to the beginning of the matrix, and that gives you kind of an alignment between the two sequences. So here, what this is saying is that AATC aligns to AAC, where there's a gap between this A and the C, where in this sequence there was a T that was inserted. Now, as you can see, when we fill this matrix, we don't do a lot of computations for every cell that we compute. And also, when we trace back into the matrix, we also touch random parts of the matrix in a not a super, in a way that's doesn't have a lot of spatial locality. So the temporal locality is low, the spatial locality is low, and this is why this computation tends to be a memory-bound computation. There are a lot of sequence alignment algorithms that we looked at. We looked at Needleman-Wunsch, we looked at Smith-Waterman-Goto, we looked at GNASM, which uses bitwise operations to based on the BiTAP algorithm, so it's a little different in the way it works from these other algorithms. And we looked at the wavefront algorithm, which is similar to Needleman-Wunsch and Smith-Waterman, except it leverages this idea of wavefronts to try and reach the bottom of the matrix without having to cover a lot of the kind of the sides of the matrix if it doesn't need to, especially places where the score is already very high and is unlikely to result in a promising alignment. So we looked at these different algorithms and we evaluated them on CPUs using multiple threads. So here in this plot, you can see you have the different algorithms, and for each algorithm, we ran it with a different number of threads. And here, every thread is basically doing a separate independent alignment, because you typically have many of these read pairs that you want to align because you're mapping reads to many different places in the reference genome. So what you can see here on the y-axis, we have execution time. So what you can see is that for all of these algorithms, when you increase the number of threads, your execution time begins to drop, but then at some point it plateaus, which means that as you try and do more and more work in parallel, you don't get any performance improvement. And this is embarrassingly parallel because there's no synchronization overhead. Every thread is working on a completely independent alignment. So this plateau is not coming from any synchronization overhead. Where is it coming from? Well, if we investigate deeper, over here, if we look at the instructions per cycle, we notice that as the number of threads increases, what happens is the instructions per cycle that are executed by each thread significantly drop, which means that these threads are spending more and more time idle as more and more threads are coming into the game to try and do more alignments in parallel. Now, if we further investigate what is the source of this idleness, excuse me, we find that over here, if we look at the number of memory stalls that are taking place, we find that as we increase the number of threads, there are more and more memory stalls that are happening in the system. So in other words, these threads are more and more idle because they're spending more and more time waiting for memory. So even though you were throwing more threads at the problem to try and go faster, these threads are not able to make any progress because they're just sitting there waiting for memory. We cannot bring data from the memory to the compute cores fast enough to be able to accelerate this application on the CPU in parallel. So this brings me to the motivation for processing in memory. As we know, in traditional processing system, you have a CPU chip, you have the memory chip, and when you want to do computations, you load data from the memory chip to the CPU chip, and this has to go through a memory bus, and that memory bus becomes a bottleneck if you're requesting too much data. So the idea of processing in memory is to overcome this bottleneck by instead having placing cores near the DRAM banks. So here, instead of bringing data from the DRAM banks to the CPU cores to do computations, instead what you can do is you can place PIM cores next to the DRAM banks, and you can perform the computations near these DRAM banks without having to bring the data all the way to the CPU to perform the computations. And this is important when you have a memory-bound application where you don't have a lot of data reuse, because bringing it to the CPU, as Onur had mentioned in his previous presentation, the latency and the energy that you spend bringing the data to the cores is more than the computations that you're performing on them. So this processing in memory and the particular flavor, which is processing near memory systems, there are real processing in memory systems that are coming out. So Juan had presented many of these, and one of them is UPMEM. Now, one common feature across all of these real PIM architectures, some common features are the following. So there's a host processor, such as a CPU or maybe a GPU, that accesses both the standard main memory and the PIM-enabled memory. The PIM-enabled memory contains multiple PIM processing elements. So you have many of these PIM cores that each has access to kind of a different part of the memory, and this access has high bandwidth and low latency. These PIM cores, because they're in DRAM, they're usually clocked at a smaller clock, and there's limited real estate, so you're going to have typically a small number of registers, and you might also have a small scratchpad memory. And then also, the PIM cores may not be able to communicate with each other, so you may need to communicate. They may need to communicate between each other via the host processor. So these are some common features that we found across all these real PIM systems that are coming out, and all these features are particularly present in the UPMEM system that we target. So a brief overview of the UPMEM system. Juan had already presented that, but I'll also do a brief review. So in the UPMEM system, the way it works is that you have a host CPU. You have main memory, which consists of many DRAM chips, and then you also have a PIM-enabled memory that consists of many PIM chips. And typically what happens is you have the host CPU that will transfer data from the main memory chips to the PIM-enabled memory whenever you want to do any computations in the PIM-enabled memory. This is kind of an image of a real DRAM, kind of a real PIM UPMEM DIMM. Now, if we zoom into this PIM chip, we notice that we see that in the PIM chip there are multiple PIM cores, and each of these PIM cores is coupled with a DRAM bank. So in the UPMEM architecture, you have a 64 megabyte DRAM bank. This is called main RAM or MRAM, and every one of these DRAM banks is going to have a PIM core. A PIM core alongside it. There's going to be for this PIM core. There's going to be a pipeline. So in UPMEM, the pipeline is 14 stages. And then there's also a scratchpad memory called the working RAM. There's an instruction memory, and there's also a DMA engine that transfers data between the DRAM bank and the instruction memory or the scratchpad memory. And so then this is the architecture that we target in our framework. Now I'm going to talk about our framework, which aims to perform sequence alignment using real processing memory systems, and we particularly implement it on the UPMEM system. So the flow of our framework works as follows. We first read sequence pairs. These are the pairs that we would like to align. We read the sequence pairs from disk or from some other input, the location where we're getting them from, into the main memory, and then from the main memory we will distribute these sequence pairs to the different MRAM banks, to the different DRAM banks in the PIM-enabled memory. Now, each of these MRAM banks is going to be coupled with a DPU or a PIM core. And what this DPU is going to do is that inside of the DPU, again, we have this WRAM, which is a scratchpad memory, and then we have the main core, the pipeline that does the computations. So what's going to happen is you're going to have many threads. Every thread is going to take a different sequence pair, and the thread is going to bring that sequence pair into the scratchpad memory, and then do the alignment while accessing the scratchpad memory. And then once it's done with alignment, it's going to do the trace back, and it's going to send the result back to the MRAM, the DRAM bank. And then from the DRAM bank, we're going to transfer the results back to the main memory, and then from the main memory we are going to write those results to the output file. So this is the overall flow of our framework. So we have support for transferring sequence pairs to the different MRAMs, scattering them across the different MRAM banks, gathering them from the different MRAM banks, and then we have support for streaming data between the MRAM banks and the scratchpad memories, and of course we have support for many different algorithms for executing the sequence alignment in the PIM cores. So in particular, we support the following algorithms in our framework: Needleman-Wunsch, Smith-Waterman Goto, Janazm, and then the WFA algorithm. We have two variants of it. There's the exact WFA, and then there's the WFA adaptive, which is a heuristic that tries to eliminate some of the unpromising regions to further improve performance and also reduce memory consumption. So these are the different algorithms that we support in our framework. Now, one important thing in supporting the UPMEM system is managing the memory hierarchy. Like you saw, there are different parts of the memory hierarchy. There's the main RAM, there's the scratchpad memory. So one important design decision is how do we manage this hierarchy? So we have two different modes for executing these alignments. In one of these modes, what we do is we place the sequence pairs inside of the main RAM, and then in the WRAM, the scratchpad memory, what we do is we place all the alignment data structures only in the scratchpad memory. But what I mean by the intermediate alignment data structures is things like the DP matrix in Smith-Waterman or Needleman-Wunsch, or these wavefront components that we use in the wavefront algorithm. So what we do is these intermediate alignment data structures are only placed in the scratchpad. We don't place any of them in the main RAM. And then in the other variant, what we do is we place the sequences and the alignment data structures inside of the main RAM, and then we only take part of the alignment data structures and we cache those in the scratchpad memory while we are performing the alignment. Now, the trade-off between these two is the following. The scratchpad memory is faster than the main RAM. However, it's smaller. So on the left here, if we're placing all the intermediate alignment data structures in the scratchpad, that's going to limit our parallelism. So it's going to limit how many threads we can execute, how many PIM threads we can execute. Whereas on the other hand, over here, if we only put part of the alignment data structures in the scratchpad memory, we can execute more threads, but then the access latency is going to be slower. It's still going to be high compared to CPU, but it's going to be slower because you need to bring things from the main memory to the scratchpad memory where you can access them. So those are two different variants of our implementations. So with that, let me get to our evaluation. We evaluate our framework, our different PIM implementations using different read lengths. So we have small read lengths that use real data sets, and then we have these long real lengths based on synthetic data sets. And we also evaluate different edit distances. And then for the systems we evaluate on an UPMEM system that has 2,560 PIM cores clocked at 425 megahertz, and that's a total amount of memory there is 160 gigabytes of DRAM. And then we also compare this to 3 different CPU systems with 3 different CPUs. Each of these CPUs has a different frequency, different number of threads, and also different size of the L3 cache. And the size of the L3 cache is going to be important, as you'll see in my evaluation. So I'll start by comparing the performance of the PIM implementations to the CPU implementations. So here you can see on the x-axis we have the different algorithms, and then for each algorithm we also have the read lengths. So here Needleman-Wunsch we look at different read lengths. For Smith-Waterman we look at different read lengths, etc. And we also have different edit distance thresholds. So the top graph is showing us with a 1% edit distance threshold, and the bottom graph is showing a 5% edit distance threshold. Now these 3 bars that you can see represent the 3 different CPU systems, and the axis is execution time, so lower is better. So one important observation that you can see just by comparing the 3 different CPU implementations is that the best performing CPU implementation is in most cases the 3rd bar, which is the Xeon E5, which although it has fewer threads than the others, but it has a larger L3 cache. So the L3 cache played an important role for this particular algorithm, and obviously because this is a memory-bound algorithm, so the more on-chip cache you have, the better performance your algorithm is going to have, because you can keep more of your working set in the caches and not have to go to memory. Now the second observation. So here, if we look at the UPMEM implementation. If you look at the UPMEM implementation, and here we're including data transfers. By this I mean we're including the time that we're taking to transfer data from the main memory to the PIM-enabled memory, or the UPMEM DIMMs. You can see that in the majority of cases, the PIM outperforms the CPU, including even when you account for the data transfers. And the speed up is up to 4 times for Smith-Waterman Go2 and 1.8 times for WFA, and 2.56 for WFA adaptive, which is the state-of-the-art algorithm. Now, if we look at UPMEM without data transfers, we notice that the speed up is even higher. So here, if we look at this last yellow bar on the right, you'll find that when we don't include the speed up is much higher. It goes up to 25.93x for WFA and up to 28x for WFA adaptive. Now, obviously, when you omit the transfer time, the speed up is much higher. But why is it important to look at this transfer time? Well, the reason is if I go back to this system, remember we said that we are reading the sequences from a file to the main memory and then transferring them from main memory to the PIM-enabled memory. So this transfer time is there because of a current limitation in the system that we cannot read from this directly into this PIM-enabled memory. But if the technology improves and matures, and in the future we can read data directly from this to this PIM-enabled memory, we can bypass this transfer time, and that shows that in this case, PIM becomes an even more promising technology. The more capabilities this PIM-enabled memory has. Now, of course, there are some challenges with doing this. The data laid out in the PIM-enabled memory is laid out differently from that in the main memory. So there are challenges in being able to read data directly from disk into the PIM-enabled memory. But again, as the technology matures, we hope that these challenges can be overcome. One thing to note is that our PIM implementations do not perform better than the CPU implementations, particularly when we have small read lengths for the algorithms that have regular access patterns. And that makes sense because when you have a small read length, things fit in your cache and your access pattern is regular, the prefetchers are usually pretty good at making sure the data is there before you access it. So in this case, PIM is less promising. Where we see the most benefits is where we have irregular accesses and large read lengths that exceed the the cache capacity of the CPU. We scale to even larger read lengths. So here you can see read lengths of 5,000 and 10,000. And you can see that even as we scale to these very large read lengths, we still consistently have, outperform the CPU implementations. For this very large read length with very high edit distance, this is where the PIM begins to not beat the CPU. For this particular case, the problem here is actually the WRAM capacity. So remember, we had so this WRAM becomes a bottleneck because we need to have these intermediate alignment data structures to perform the alignments. But then even when you have very large read lengths, even when you're only caching part of those data structures in the WRAM, you can support a very small number of threads. And that's why that's where the WRAM capacity becomes a limitation factor for performance. But we can further improve this if we have multiple tasklets or PIM threads work on the same alignment. So compared to GPUs, so if we compare to GPUs, you can see that here we compare our UPMEM implementation with data transfers to a implementation of WFA, which is the state-of-the-art algorithm on GPUs. And as you can see, for very large sequence lengths, we can see that we have substantial improvement in throughput over state-of-the-art GPUs. These times are obtained from this prior work on WFA GPU. It's not our implementation. So PIM outperforms GPUs in the majority of cases. So I have an analysis here on using WRAM only versus using WRAM and MRAM. I'm going to go through it quickly, but I'll be happy to kind of talk about it in more detail if people have questions, just for the sake of time. So some key observations here are that the WRAM, when we place the intermediate alignment data structures in the main RAM, not in the scratch pad, when we place them in the scratch pad, that does not scale for the algorithms that use a very large amount of memory. So over here we have to use the main RAM and place only the part of those data structures in the scratch pad memory. For the algorithms that use a very small amount of memory for those intermediate data structures like GNASM, over there placing data in the scratch pad memory is always better. And then for the algorithms that use a moderate amount of data structures, moderate amount of memory for the intermediate data structures, we find that when the alignment is small, these intermediate data structures all fit in the scratchpad memory. So it's better to use only the scratchpad memory for those data structures. But then as the read length increases, we find that scratchpad becomes smaller and smaller, so we can use fewer and fewer threads. These numbers here indicate the number of threads that are participating in the computation. So as the read length increases, the best version switches to the version that uses the MRAM bank to place the intermediate element data structures and bring parts of them into the scratchpad when needed. And this highlights the importance of supporting both implementations in our framework. So to summarize, we showed that sequence alignment is a memory-bound computation on traditional processor-centric systems. We showed that processing in memory overcomes the main memory bandwidth bottleneck by placing cores near the memory. We presented our framework, alignment in memory, for performing sequence alignment on real PIM systems. We support different algorithms, and we implemented it on the first on UPMEM, which is the first real PIM systems. And our results showed substantial speed up over CPUs and GPUs. And you can find our code, again, you can find our code available on GitHub. And with that, that's end my talk, and I'd be happy to take questions if there are any.
Do you guys have any questions for Izzat? Okay, I'm going to ask you something. My question is, what improvements do you think that the current UPMEM system needs to support, so for better support for these algorithms and maybe support for other algorithms or future ones in the context of sequence alignment, of course?
Yeah, so I think you know, as I showed, one of the challenges was doing the data transfers from the main memory to the PIM-enabled memory. So if you can have a more kind of direct way of sending the data directly to the PIM-enabled memory, I think that would be a big improvement for this algorithm and for any other algorithm, right? Because the whole idea of PIM is to avoid moving the data. So if you have to move the data from the main memory to the PIM-enabled memory to be able to compute on it, you're already moving the data and you're trying to avoid moving the data. So so I think having a more direct way of writing directly to the PIM-enabled memory and then performing computations there would result in a big improvement. I think, however, that particular improvement is kind of a long way away. Other kind of more direct improvements is if you could have somehow direct access to the main RAM or larger scratchpad memories, that would enable us to hold more of these intermediate alignment data structures in that scratchpad memory. But there's always a trade-off between how big you can make the scratchpad memory versus how much you want to invest in making the core more powerful. So you know, that's a trade-off that hardware designers have to make.
Yeah.
Overall, from my experience working with other computations, especially graph algorithms, one of the main limitations of the architecture is having efficient communication between the different PIM cores. Now, in this particular computation, that wasn't important because you know, there's a lot of parallelism that you already have from aligning many reads in parallel. But for other algorithms, I think the communication between the different PIM cores is a particularly limiting factor for applications that do have a lot of this this global communication.
Okay, yeah, I completely agree with you. And as you said, I think that some of those potential improvements are easier to implement. Some others are significantly more difficult in terms of design and development. The WRAM, the larger WRAM, I think that's something doable, and indeed I think that's in UPMEM's roadmap. So hopefully we will see it. There is one more question from the audience. Can you hear from the back? Or give me 1 second.
Yes.
Hello?
Yeah, I think I can hear.
So, yeah, that was an interesting talk. I mean, your previous answer was pretty much memory-centric, which makes sense. So your kind of research, what kind of changes would you like to see in the ISA if you have the opportunity in front of operators?
Okay, the sound was faint. Juan, do you mind repeating the question to me?
So changes in the ISA that you would like to see.
What kind of operators would you like to see?
Ah, okay. So I think right now I mean, it's a RISC-V ISA, standard ISA, but the architecture is only very good at supporting, you know, additions, you know, simple arithmetic operations. Once you go to doing multiplications and floating point, that becomes, you know, those are all emulated in software and they're very expensive. So I think one thing that would be nice to have, now these were not very important for sequence alignment, because in sequence alignment, you know, you don't do a lot of multiplication and floating point. It's mostly simple arithmetic. But if you want to look at other, you know, other applications like machine learning, for example, their multiplication is important, and floating points important. So it would be nice to have, you know, support for, you know, these more complex arithmetic operations. Now, you know, whether or not that's a priority is kind of a, you know, it's a different story, because, you know, it requires a lot of hardware to support these complex math operations, and you know, you have very limited real estate in the DRAM so maybe you can't afford putting that much hardware into the cores. So again, that's the trade-off that the hardware designers have to make. One other thing that might be useful is, you know, NVIDIA now in the GPUs, they have these DPX instructions that can perform these you know, max operations very efficiently. So these are very useful for these for sequence alignment and for dynamic programming in general. So now here, because the architecture is very compute bound, so an arithmetic operation is very expensive, and we are mostly limited by how fast the pipeline can go. In this case, having a similar, maybe multiple max operation or min operation like the DPX instructions could potentially make things faster for sequence alignment.
Okay, yeah, that makes sense. Thank you very much for the answer, Izzat. No other questions? Okay, I don't see any other questions here. Thank you very much, Izzat, for your participation in the tutorial. Now we are going to move to the next presenter, who is Christina. Okay, so the next presenter is Dr. Christina Giannoula. She is a postdoctoral researcher at the University of Toronto, working with Professor Gennady Pekimenko and the Ecosystem Research Group. She is also working with the Safari Research Group led by Professor Onur Mutlu, and she received her PhD in October 2022 from the School of Electrical and Computer Engineering at the National Technical University of Athens, advised by Professors Georgios Goumas, Professor Nectarios Kossidis, and Professor Onur Mutlu. Her research interests lie in the intersection of computer architecture, computer systems, and high-performance computing. And specifically, her research focuses on the hardware-software co-design of emerging applications, including graph processing, pointer chasing data structures, machine learning workloads, and sparse linear algebra with modern computing paradigms, such as large-scale multi-core systems, disaggregated memory systems, and near data processing architectures. She has several publications and awards for her research on these topics. Whenever you're ready, Christina, thank you very much.
Okay, thank you for the introduction.
Yeah, sorry.
That's good. Hi, everyone. So I'm Christina, and today I will present our work, SparseP, towards efficient sparse matrix vector multiplication on real processing memory architectures. So in this work, we have first designed the first sparse matrix vector or SPMV library for real processing memory systems, and our library is open source in GitHub. And we also provide an extensive characterization study of the SPMV kernel on the first real PIM architecture, which is the UPMEM system that we have seen. Our extensive study leads to many recommendations for architects and software designers of PIM systems. So let's start with the motivation of this work. The sparse matrix vector multiplication kernel is a fundamental linear algebra kernel for many important applications from the scientific computing, machine learning, and graph analytics domains. In computing and commodity systems like CPUs and GPUs, it has been repeatedly reported to achieve only a small fraction of the peak performance, and it is primarily bottlenecked by the memory bandwidth of the system. At the same time, several manufacturers have already started to commercialize near-bank PIM systems. A PIM system consists of multiple PIM-enabled memory modules connected to a host CPU via the common channel-based connections, and each PIM-enabled memory module supports several PIM cores. Each PIM core is located very close to a DRAM bank, a 64-megabyte DRAM bank in our case. And as a result, these PIM systems can provide high levels of parallelism, low memory access latency, and large aggregate memory bandwidth. Thereby, they are a very good fit to accelerate the SPMV kernel. A few real near-bank PIM architectures are Samsung VMDRAM, SK Hynix, and the UPMEM PIM system. In this work, we make two key contributions. First, we design the SparseP library, the first SPMV library for real PIM architectures. We propose 25 efficient SPMV kernels that support several compressed matrix storage formats, data types, data partition techniques, and load balancing schemes. And we cover a wide variety of real-world matrices and also real-world applications. And we also conduct a comprehensive study of the popular SPMV kernel on the first commercially available PIM system, the UPMEM system. Our characterization study includes a wide range of sparse matrices with diverse characteristics and also comparisons to state-of-the-art CPU and GPU systems. And we provide many recommendations for software system and hardware designers. So let's take a look on the SPMV kernels that we support. This is the end-to-end SPMV execution on a real PIM system that can be broken down in 4 steps. First, the time to load the input vector into the DRAM banks of the PIM-enabled memory modules. Second, the time to execute the SPMV kernels on the PIM cores. Third, the time to retrieve the results from the DRAM banks to the host CPU. And fourth, the time to merge the partial results and assemble the final output vector on the host CPU side. Our evaluated system does not support the PIM-enabled memory as the main memory of the system, and as a result, we need to load the input vector to the PIM-enabled memory modules. However, our kernels would be the same and can also apply to architectures where the PIM-enabled memory constitutes the main memory of the system, so we don't need to load the input vector. This can be omitted. To parallelize the SPMV kernel, we support 2 general types of data partitioning techniques. In the 1D partitioning technique, we horizontally split the matrix, and we partition horizontally the matrix across multiple PIM cores, and the whole input vector is replicated at each PIM core of the system. In the 2D in this technique, we perform the complete SPMV execution using only the PIM cores, because the PIM cores directly produce results for the output vector, so we directly get the final element for the output vector. And second, we also have a 2D partition technique where the matrix is partitioned in 2D tiles. The number of tiles is equal to the number of PIM cores used. And with this 2D partition technique, we aim to strive a balance between the computation and the data transfer cost, because only a subset of the elements of the input vector is copied at each DRAM bank of each PIM core. However, we create partial results on the PIM side, so we need to merge this partial, transfer back these partial results to the host CPU and merge these partial results using the host CPU cores in order to get the final output vector. In the anti-partitioning technique, we provide various load balancing schemes across multiple PIM cores for the 4 most widely used compressed matrix storage formats. For the CSR and CUF formats, we load balance either the number of rows or the number of non-zero elements across PIM cores. For the BCSR and BQ formats, we load balance either the number of blocks or the number of non-zero elements across PIM cores. However, the load balancing depends on the characteristics of each compressed matrix format. For example, in the CSR format, since the matrix is stored in row order, the load balancing of the non-zero elements is limited to be performed at a row granularity. Instead, in the CUF format, the matrix is stored in non-zero element order. Therefore, the load balancing can be performed at a non-zero element granularity. This means that one row can be split across 2 neighboring PIM cores. And with this approach, we can provide a near perfect non-zero element balance across the PIM cores. Similarly, for the BCSR, the load balancing is limited to be performed at a block row granularity. For the PQ format, we can split one block row across 2 neighboring PIM cores, so we can provide a better non-zero element balance. Now, in the 2D partitioning technique, we support 3 schemes. In the equally sized scheme, the 2D tiles that we create, we statically create the 2D tiles in order to have the same height and width. This way, the subset of the elements for the input and the output vector have the same sizes across all PIM cores. However, this scheme has very high non-zero element imbalance because this matrix is sparse, so the static tiles that we create have a very high variability on the non-zero elements across the PIM cores. The second approach is that we use an equally wide scheme. In this scheme, the 2D tiles have the same width and variable height. For each vertical partition on the matrix, we load balance the non-zero elements across the tiles of the same vertical partition. In this scheme, the subset of the elements for the input vector has the same sizes across the PIM cores, while the subset of the elements for the output vector varies across PIM cores. And this way we can provide high non-zero element balance across the PIM cores of the same vertical partition. And in the final scheme, the variable sized scheme, the 2D tiles have both variable height and width. We load balance the non-zero elements across the vertical partitions that we create in the matrix, and then we load balance the number of non-zero elements across the PIM cores of the same vertical partition. And with this scheme, we can provide very high non-zero element balance across all PIM cores in the system. Moreover, since a real PIM architecture can support multiple multi-threaded PIM cores, this means that we can have multiple threads within a single PIM core. In both the 1D and the 2D partitioning technique, we can support various load balancing schemes among the threads of the same multi-threaded PIM core. We can, for example, load balance either the number of rows or the number of non-zero elements across multiple PIM threads of each PIM core. In the CUF format, given that one row or one block row can be split across 2 neighboring threads, we also need to support various synchronization approaches because multiple threads can work on the same elements of the final output vector, so we have race conditions. And as a result, we can provide 3 synchronization approaches. The first approach is a coarse grain locking, where we have one global lock to protect all the elements of the output vector, and all the threads compete for this one lock in order to do a write operation on the output vector. We have a fine grain locking technique where we have multiple locks to protect the output vector. This means that each lock protects a subset of the elements of the output vector. So multiple threads can work on different parts of the vector, and they compete for different locks. And finally, we have a lock-free scheme where the threads create partial results for the elements of the output vector. These partial results are stored in the scratchpad memory, and later only one thread merges these partial results in order to get the final result for the output vector and store the final result of the output vector in the DRAM bank. So overall, Our SparseP package provides 9 1D partition kernels and 16 2D partition kernels. It is publicly available on GitHub. For the CSR and BCSR format, we load balance with the rows or the non-zero elements at the row and block row granularity respectively. In the Q and the Q formats, we can also have similar load balancing schemes, but within the PIM core, across multiple threads of the same PIM core, we can also have various synchronization approaches. And finally, our SparseP kernels support a wide range of data types, both low precision like integers, 8-bit integer, and also high precision floating point data types in order to cover a wide variety of applications. So let's take a look on some of the most important key takeaways and results of our analysis. This is the real UPMEM system that we use in our evaluation. It includes 20 UPMEM PIM teams connected to a host CPU, and we have in total 2,560 PIM cores. Each PIM core can support up to 24 threads or tasklets that can access the local 64 megabyte DRAM bank. And we evaluate a wide variety of sparse matrices from the suite sparse matrix collection. When the standard deviation of the non-zero elements across the rows and the columns of the matrix is very low, we refer to the matrix as regular. When the standard deviation of the non-zero elements across the rows and the columns is very high, this matrix has a power law distribution, and we refer to as scale-free matrix. So we first examine the execution time using one single PIM core. So we only take a look at this, the second step of the execution using one PIM core and multiple threads. We compare the performance of the fine-grained locking approach over the coarse-grained locking approach using multiple threads, 16 threads, or within a single PIM core. And we observe that the fine-grained locking approach does not improve the performance over the coarse-grained locking approach. Even though we use more threads to protect a subset of the elements for the output vector, we don't get performance because the DRAM accesses that the multiple threads perform, they are executed as transactions in the UPMEM system, in the UPMEM hardware, and these transactions are serialized in the DMA engine, so we cannot increase the execution parallelism. We conclude that the fine-grained locking approach to parallelize critical sections that perform accesses to different locations in the DRAM does not improve the performance over the coarse-grained locking approach when the hardware does not support concurrent accesses to the DRAM bank. So our first suggestion is that we recommend architects to support low-cost synchronization and also to enable hardware support for concurrent memory accesses by multiple threads to a local DRAM bank of one single PIM core, and also to integrate multiple DRAM banks per PIM core in order to increase the execution parallelism. Next, we compare the load balancing approaches. We load balance the number of rows or the number of non-zero elements across the threads for the CSR and the Q formats. We observe that load balancing of the non-zero elements performs better than load balancing of the rows in most of the matrices. And this is because the load balancing of the non-zero elements typically provides higher computation balance across the threads of one single PIM core. However, in one single matrix, we observe that because the non-zero elements causes very high row imbalance across the threads of one single PIM core, because only one single thread processes a much higher number of rows over the rest 15 threads. And as a result, we can find that only one single thread performs much more a higher number of memory accesses and synchronization operations than the rest one, and this is why we achieve better performance whenever we load balance the number of rows compared to load balancing the number of non-zero elements. These key results demonstrate that the high operation imbalance among the threads, either in terms of computation or synchronization or the memory accesses, creates a significant performance overheads in the PIM core. And as a result, we need to design algorithms that provide very high load balance across the threads of one single PIM core in terms of the computation, the synchronization, and the memory accesses for each particular input given. And regarding the scalability of all the compressed matrix storage formats, we increase the number of PIM cores for various sparse formats. And we find that even though the UPMEM system supports 24 threads, 24 tasklets, the scalability typically improves up to 16 threads, up to 16 tasklets. After this point, the core pipeline is fully utilized. So even we increase the number of threads, we don't improve the performance. Now let's examine the SPMV kernel execution using multiple PIM cores. In this experiment, we compare the 4 compressed matrix storage formats by normalizing their performance to that of the CSR format. In the anti-partition kernels, we find that scale-free matrices, the Q and the BQ formats significantly outperform the CSR and BCSR formats respectively. This is because they provide much higher non-zero element balance across the PIM cores, because the CSR and the BCSR format are limited to perform the load balancing at a row or a block row granularity. And as a result, in scale-free matrices, we have very high imbalance across the PIM cores. Similarly, in the 2D equally sized kernels, even though all the compressed matrix storage formats have the same non-zero element balance across the PIM cores because we create static partitions on the matrix, the non-zero element balance among the multiple threads of the same PIM core is affected by the compressed matrix format used. We find that the Q and BQ formats outperform the CSR and the BCSR formats, and they provide much higher non-zero element balance across the threads of one single multi-threaded PIM core. And in the 2D equally wide and 2D variable size schemes, we find that the Q and the BQ formats significantly outperform CSR and the BCSR formats in all matrices, both in regular and also in scale-free matrices. And this is because they provide a much higher non-zero element balance, both across the PIM cores and also across the threads of the same multi-threaded PIM core. Our main key takeaway from this analysis is that the compressed matrix storage format that we use determines the partitioning and the load balancing across the multiple PIM cores and across the threads of the same PIM core, and therefore it performs, it has the corresponding performance implications. And as a result, the recommendation that we have is that we recommend software designers to propose compressed data structures for the sparse workloads, the sparse kernels, that can be effectively partitioned across the DRAM banks in order to provide very high computation balance across the PIM cores and also across the threads of the same PIM core. Then we characterize the end-to-end SPMV execution, including the data transfer costs, including the cost to transfer the input vector to the PIM-enabled memory module, and also the cost to retrieve the results back to the host CPU. We evaluate the scalability of all the data partition techniques as the number of PIM cores increases. And we normalize the performance to that achieved with 256 PIM cores. First, we find that the scalability of the 1D partitioning technique is limited by the low data transfers because we need to replicate the input vector at each PIM core of the system. And we have a very high amount of bytes that is transferred to the PIM-enabled memory because the input vector, the copies of the input vectors grows linearly with the number of the PIM cores that we use. We conclude that the 1D partition kernels are bottlenecked by the high data transfers to broadcast the whole input vector at each DRAM bank of the system. And therefore, we suggest hardware and system designers to optimize the broadcast collective in order to effectively copy and replicate the input data at all the DRAM banks of the system. Second, we find that in the 2D equally sized schemes, the kernel time limits the scalability. And this is because we create static partitions on the matrix. So the kernel time is limited by only one PIM core or a few PIM cores that are assigned to the static 2D tile with the largest number of non-zero elements. And this in turn affects the scalability. And we find that regarding the scalability of the 2D equally wide and 2D variable size kernels, their scalability is limited by the retrieve time to transfer the results for the output vector back to the host CPU. And these schemes are severely bottlenecked by the high amount of padding with empty bytes that we perform in the system. Now, whenever we transfer results from multiple DRAM banks to the host CPU, the sizes across the DRAM banks needs to be the same. If we have like different elements across the DRAM banks, we need to perform padding with 0 bytes. And in this case, the padding was like on average 88% of the data that we transfer to the host CPU. And this creates a very significant bottleneck to retrieve the results back to the host CPU. As a result, we conclude that these 2D equally wide and 2D variable size schemes are severely limited by the data transfers, the parallel data transfers, and the padding that we perform. So we need to provide fine-grained parallel data transfers with 0 padding. They need to be supported in order to achieve high performance in these kernels. So our recommendation is that we suggest hardware system designers to optimize the gather collective operation from PIM-enabled memory to the host CPU, and also to provide parallel transfers at DRAM bank granularity in order to completely eliminate the padding, the 0 padding, and in order to significantly minimize the overheads of retrieving the final output results back to the host CPU. We also have like some comparisons related with the inputs that we give, the different sparse matrices. We have experimented with the best end-to-end performance for various sparse matrices. And in this example, in the 1D partitioning technique, in the first matrix, the best performance is achieved using 64 cores. In the second matrix, that has like different characteristics, the best end-to-end performance is achieved using 128 cores, or in other words, the number of PIM cores that provides the best end-to-end SPMV performance depends on the particular sparsity pattern and the particular characteristics of the sparse matrix that we give. And we have a similar observation in the 2D partitioning scheme. Here we have like a fixed number of PIM cores, and we vary the number of vertical partitions that gives us the best end-to-end performance. We find that in the first matrix, the best end-to-end performance is achieved using 16 vertical partitions. And in the second matrix, we find that the best end-to-end performance is achieved using 8 vertical partitions. So similarly, we find that the best end-to-end performance and the number of vertical partitions that provides us the best end-to-end performance depends on the sparsity pattern that we have on the input matrix. Apart from the characteristics of the input matrix, we have also experimented with different PIM systems in order to see what is the effect of different hardware, different characteristics on the hardware level. So in this example, we find that for various PIM systems, the best performance is achieved using a different number of vertical partitions in the 2D case. In other words, the number of the vertical partitions that provides the best end-to-end SPMV performance depends on the characteristics of the underlying PIM system, the underlying hardware. So our key takeaway from these 3 experiments is that there is no one-size-fits-all parallelization approach for the SPMV, because the performance of each parallelization scheme depends on the characteristics of the input matrix, the sparsity pattern of the input matrix, and the underlying PIM hardware. Therefore, software designers need to provide adaptive algorithms, adaptive solutions that they tune their configuration based on the particular patterns of each input given and also the characteristics of the PIM hardware. And finally, in this experiment, we compare all the data partitioning techniques by running different configurations for each data partition technique. For the 1D partition kernels, we vary the number of PIM cores from 64 to 2,528 PIM cores. And for each matrix, we select the best performing end-to-end execution throughput. And for the 2D partition kernels, we use 2,528 PIM cores, and we vary the number of vertical partitions on the matrix from 2 up to 32 in steps of a multiple of 2. And for each matrix, we select the best performing end-to-end execution throughput. In this experiment, we find that the equally sized 2D partition scheme performs best in the regular matrices, and the 1D partitioning technique performs best in scale-free matrices. The 2D equally wide and variable size schemes do not provide the best end-to-end SPMV execution throughput in any matrix because we have a very high amount of padding with 0 pads. What we observe in this experiment is that in all cases, in all sparse matrices, the best performance is achieved using a much smaller number of PIM cores than the available PIM cores of the system. There are many idle PIM cores in the system because the best performing SPMV execution is a trade-off between computation and data transfer costs. As we increase the number of PIM cores, we increase the amount of bytes that we need to transfer to the system, and we have a higher performance overhead. So we need to tune the computation and the communication in order to get the best performance that we can get for this system. Our key takeaway is that the expensive data transfers to and from the PIM-enabled memory module performed via the narrow memory bus impose significant performance overhead to the end-to-end SPMV execution, and therefore it is very hard to fully exploit all the available PIM cores of the system. To this end, we recommend software, hardware, and system designers to provide high-speed communication channels and optimize libraries in data transfers to and from the PIM-enabled memory modules, to provide hardware support to effectively overlap the computation with the data transfers in the PIM system, and also to integrate the PIM-enabled memory modules to be the main memory of the system in order to completely eliminate the load of the input data to the PIM-enabled memory modules. Finally, we compare the SPMV execution on the UPMEM PIM system with that of a common CPU system and a GPU system. In the GPU system, we also account for the time to transfer one instance of the input vector from the host CPU to the GPU global memory, and also the time to retrieve the final output vector to the host CPU. So common CPU systems and GPU systems are processor-centric systems, and they provide very high computation capabilities, while real PIM systems are memory-centric systems, and they have very high bandwidth capabilities. When we consider only the actual kernel time without considering the data transfer costs, we find that the SPMV kernel execution on a real PIM system achieves a much higher fraction of the available peak performance compared to that of the CPU and the GPU system. This, as a result, we can provide much higher hardware resource utilization, and we have higher total cost of ownership. In contrast, when we consider the end-to-end execution, this means that including the data transfer overheads for the input and the output vectors, the CPU system performs best because there are no data transfer costs. However, in PIM systems are still maturing, so we expect that future PIM systems will probably reduce the data transfer costs. And regarding the kernel SPMV energy, we find that GPU performs the highest energy efficiency, while the 1D partition kernels can provide better energy efficiency on the SPMV kernel over the CPU system. And this is the case with the floating point data types that are not supported in the hardware. But however, even in this case that we don't support floating point data types in the hardware, we can achieve 1.38 on average less energy consumption compared to the CPU case. We have many more results in our archive paper. So in conclusion, a sparse matrix vector is a fundamental linear algebra kernel and is widely used in many application domains. However, in commodity processor-centric systems like CPUs and GPUs, it is highly bottlenecked by the data movement between processor and memory. A real near-bank PIM system can tackle the data movement problem by placing low area and low power cores very close to the DRAM banks, and as a result, they can provide very high levels of parallelism, low memory access latency, and large aggregate memory bandwidth, thereby being a very good fit to accelerate the SPMV kernel. To this end, we have designed SparseP, the first open source SPMV library for real PIM systems, which is publicly available on GitHub. And we also provide a comprehensive characterization study of 25 SPMV kernels on the first real PIM architecture. Our work provides new insights and recommendations for software designers and hardware architects in order to improve multiple aspects of future PIM software and hardware. For more details on our work, we invite you to read our full archive paper. Thank you so much for your attention, and I'm happy to take questions.
Hello, Christina. I am Gerasimus from UofT. It's very interesting to see sparse linear algebra and graph analytics in those new architectures. I have many questions. We can discuss some offline like this. But I was interested in dynamic partitioning, basically, because we mainly focus on static partitioning, especially for larger graphs, by using, for example, some kind of atomic counter. We can just distribute sparse matrix rows dynamically during the runtime. What would be the cost of synchronization in this case? Is something that you see as feasible in future PIM architecture?
You mean synchronization in terms of multiple threads with
atoms for dynamic distribution of sparse matrix rows.
within the PIM core, right? Not across the PIM cores.
And across, if you have, for example, a counter that counts what is the next row to be assigned, right? The row index. And we have to increment it at the time that the PIM core gets some work. So would this be something possible to implement?
Yes, actually, our previous work, it's called Synchron. It is related with synchronization. So in that case, we provide hardware support for synchronization on the PIM cores, but the PIM architecture that we target is slightly different compared to the UPMEM system that we have. Yeah, definitely it's like something similar, feasible. Definitely needs to be supported in the hardware, not in the software case. It needs to be very efficient. And yeah, I think yeah, we have some insights in our previous paper actually. Sure.
If you put this line from your experience, now your own sparse presentation, and assume you put some thought into that, how would you be content with the current sparse presentation, or would you come up with something different that's specific to the PIM architecture?
What would be specific to this PIM architecture? Yeah, what?
You went for a couple of existing sparse presentations. There are many more out there that are being proposed. I'm wondering if you thought about some sparse presentation that you think would.
Yeah, that's a good question. Actually, all the formats that we use are CPU-based formats, like the most widely used formats, and based on our analysis, the Q format was like the most important and the most like efficient. If you run all these formats in the CPU case, you will see that the CSR format is the best performance. But in this case, it was like the Q. I believe that based on the current compressed matrix format, Q is the best one. It might be improved. It might become even better. The key idea is that we need to create formats that consider the computation, right? Not like how much we compress the data. They need to consider how we compress, how we represent the non-zero elements in the compressed format, not how much, like we can trade off like putting some zeros inside the compressed format, but we have a perfect data partitioning across the PIM cores, right? So we need to redesign some compressed data structures. Yeah.
So that's future work.
Yeah, that would be an yeah. It's like a suggestion for the software designers from our analysis. Yeah.
Okay, thank you.
Next. The zero padding, you mean? Yeah. So, for example, if we have like output. In different banks, right? So in the one PIM core, you assume you have like 10 elements. In the second PIM core, you have like 8 elements. In the third PIM core, you have like 2 elements. So you need to pad all the partial results to be like 10, equal to the maximum number of partial PIM results that you have in one single PIM core, right? So the padding is like very naive. You just need to pad until the maximum results that you have like in one single PIM core. Yeah, and you can have like parallel transfers across all the PIM cores. So you have to pad the partial results across all the PIM cores. But you can also have like parallel transfers within one rank, right? So you can have like padding only within the PIM cores of the same rank. So this like eliminates a bit the amount of padding that you perform, but you need to have like multiple steps for each rank, multiple communication steps for each rank. Okay, super.
Question from Christina. Okay, let's thank her again.
Thank you.
I think we have time for lunch now.
on mute.
Mute, exactly.
So do I need to share my screen via Zoom?
Yeah.
Okay.
So share this in a different way. Can you stop sharing? Because now what we can see here is the presenter view.
Okay.
So you have to first go to presentation mode in the PowerPoint.
Yeah.
And then just share.
I will not using this mode actually. So can I start it? 발표 중인데 안 쓰는 거 이거 끄면 되는 건가? Okay, this is
Okay, so we are good to go.
Okay.
Are you ready?
Yeah, I'm ready. Yeah. Start?
Yeah.
Oh yeah.
Give 1 second. I'm going to introduce you. Hello everyone, welcome back to this reality tutorial. Now it's my pleasure to introduce Dr. Sukhan Lee. Dr. Sukhan Lee received his PhD degree in Intelligent Convergence Systems from Seoul National University. In 2018, he joined the memory division of Samsung Electronics in Korea, where he has been involved in DRAM circuit design. His research interests include memory microarchitecture and neural network system hardware architecture and design. Whenever you're ready.
Yeah.
Thank you very much.
Thank you for introducing me, Gomez, and I'm very happy to speak about our HB-PNM in the ISCA tutorial. Yeah, and let me start my presentation. And the subject is introducing real-world HB-PIM powered system for memory-bound applications. And my name is Sukhan Lee from the Samsung Electronics, and I'm designing HBM-PIM and HBM itself in a DRAM team. So we spend many resources and times to develop HB-PIM for ages from like end of 2010s, and we successfully ship out our HB-PIM after 2021, and we just submit several papers on the ISCA and ISCA and Hajj and several conferences such as supercomputer and MEMCon and CES whatever. So we just this slide just kind of summarize all the demos in the those kind of conferences. So please watch it. Before start, I will show the video, which is just our communication team make introducing the HB-PIM itself. Oops. Well, this video is sometimes just played in the lobby of DSR, which is in the Samsung's device solutions largest building, and sometimes I watching it and okay, just this video is not that not for export, but just give the concepts to the normal people who just don't know about what is PIM or what is HBM. The point of that is just using gather some data in the DRAM itself and reduce it to send it to the host, and it makes the boost internal bandwidth with the HBM PIM. So, yeah. And the other one is our big friend AMD just announced about the HBM PIM itself. So. In the presentation, Dr. Lisa Su from AMD just said about using PIM, we can reduce the energy by 85%. And our evaluation was 70%. So it is a little bit higher because we did not include the host side energy reduction effect. So which means it is a little bit higher energy efficiency on the real system than our expectation. So that is another interesting about the HBM PIM itself. So in my presentation, the flow is as follows, just from AquaBoard to XL itself. Because in DOSA, the other Samsung guy, Dr. Byung Kim, just introduced about the AquaBoard XL more dimly in this than this section. So I will very lightly touch about the AquaBoard itself, XL itself, and I will talk about the HBM PIM simulator, which is open to the public very early over this year. So I will touch about that, and I will introduce about the HBM PIM powered systems. One is AMD MI50 and MI100 PIM, and the other one is Xilinx U280 PIM. We have two baseboard with the HBM powered, and they are just actually built, and we are using those as like our baseboard system. So using those baseboard system, we just made 4 applications with the HBM PIM. Just the first one is Deep Speech 2 from the Baidu, and we are using MI50 PIM to apply that. And the second is RNNT, which is from Google and using from the Google voice translator or whatever. So we are just build all the RTLs from the non-PIM version and using for the baseline and the PIM versions, and compare them to show that PIM itself, PIM has the gain on the system. So I will just talk about it later. And the application 3 is T5 MOE, just a mixture of export, and we are using just enhanced MI100 PIM cluster. 100 PIM and made it with the cluster. We mixed 96 MI100 PIM board to one cluster server and show the energy efficiency and the performance gain from it. And the application 4 is now this is GPT, and everybody says about the GPT, and we just find PIM itself is very effective in the GPT for the GPT model. So why is that? And our effort to show the to have a gain on GPT on the with the PIM system. I will just present a little bit later. And level after all the things I will just talk about. What is this? So what I mentioned previously, just I touched very lightly about the architecture of a PIM DRAM die and AquaBoard XL, which is the product name of HBM PIM. And mainly it is published on the ISCA 2021. and the ISSCC 2021 also. So we just set the PIM concept as like place a program of a PIM execution unit at the boundary of IO boundary of the DRAM bank itself. So we just exploit bank level parallelism, which means just using the work all the same PIM execution unit at a time, which means we can boost the internal bandwidth of the DRAM. Normally, just one bank is activated and read and write command to just to the one bank. But in this case, we can exploit all the bank at a time. So we can use the bank IO to have a higher internal bandwidth and support both standard HBM and aqua-vertex modes for first. So we just set the concept as like that, and finally minimize engineering cost of redesigning DRAM core to support PIM, because HBM requires a lot of resources, huge resources, and it's very hard to make it. Imagine it just one buffer die has 12 or 8 stack of the DRAM. So even there is no such kind of logic in the logic processes. Only I think only 1 or 2 devices using a multi 3D stack design, but HBM uses totally 13 stacks for the expand DRAM's bank number of the banks. So it is very hard to just fabricate all the HBM DRAM. So we need to minimize those kind of effects, because PIM is a kind of technology, and it is not helpful for our businesses at this time. So we need to minimize the design cost. And then drop-in replacement. I said this word so many times in this kind of a presentation, because it have to be the same form factor, because HBM is just placed on the very near on the host system, and need to reduce the length of the phi to the DRAM phi, and it requires a lot of engineering factors also, like a PI, I mean power integrity, or SI signal integrity. These are like engineering factors, and normally architecture guy just ignores it, but it is a real problem in the field. So just we don't need to, we just don't want to change those kind of factors, because we need to pour so many resources to resolve those kind of things. So we are using the exactly same HBM, normal HBM form factor, and the commands. Also, if we just develop another commands, it requires to develop another kind of memory controllers and all the subsystem on the host. So it makes another big mess. So in that case, nobody just wanna use PIM. So this is the kind of very early stage of the developing PIM. So we just need to, PIM can be used by not changing anything on the host. So it's a kind of advertisement at the time. So so that's why I emphasizes drop-in replacements so many times. So yeah, and DRAM is important passive device. DRAM cannot just decide DRAM state by himself. So DRAM just work as like memory controller's order. So DRAM read and write command only triggers execution of PIM instructions in PIM mode. So except this kind of passive device scheme, memory controller cannot control. Memory controller cannot just manage the PIM itself. So which means no one likes those kind of problem. In that case, the host need to program all the things to set the memory controller status to the special functions to make sync them. So it is very hard to do. So we just make this kind of passive device symptom as like a preserving determinism. So host knows the status of DRAM anytime, and yeah, this is the figure of our HBM-PIM, and so many times it's just covered, so I pass it. And then chip implementation and integration with the systems. So PIM we called HBM2 from Samsung. We called it Aquaboard, and HBM-PIM device is named as like Aquaboard XL, and integrated the Aquaboard XL with the unmodified GPU and Xilinx FPGA, as I mentioned before. So validated, fabricated HBM-PIM in system with the unmodified memory controller. So it is very important to that. And off-chip and on-chip PIM compute bandwidth is 1.23 terabyte per second, and it's a 4 times internally, 4.92 terabyte per second respectively. So it is looks like this, and between 2 banks, 1 PIM block just relocated, and it is a kind of a magnified version of it, and we just tag 8 of the DRAM die, and then 4 die is just are consisting just a DRAM die, and the other 4 die is just a PIM DRAM die. So we just connected with the TSV, and 1 buffer die just controlled everything. And we did not change the buffer die of the Aquaboard XL, but we changed the only a core die, which is just we call the DRAM die. So in one GPU or FPGA, we place 2 or 4 HBM stacks on it. So this is the final version of our HBM-PIM on the system. And we just did the chip evaluation with just commercial product engineering steps. So normal Aquaboard XL is working at the 2.4 gigahertz, and we didn't find any human hole while testing this one. And the power analysis is okay. So normal HBM just IDD4R, which is just a read energy from the system. So we just find that from the internal energy, so core die energy is increased as much as like this, but the buffer die energy is decreased a little bit. So total energy is 105.4% of the HBM2 itself. But if we change the buffer die, we can achieve much smaller energy, as like we guessing as like 80% of the normal HBM. So this is the from the energy aspect. And I will mention about the HBM-PIM simulator from now on. We just opened HBM-PIM simulator to public in the very early of this year. So it is a DRAM SIM2 based cyclo-correct model for Aquaboard XL. So it contains also internal logic about the controlling how the HBM-PIM is working, and the procedures for PIM, as like we have some kind of mode change to enter the all bank mode, and access to from the all bank mode and change it to the single bank mode to work as like a normal DRAM. So we mimic everything. So this is the URL address for GitHub. So I will just shortly explain about the read.md data, MD document. So this architecture is just host send read or write command, because host does not know the when the active or pre-charge command will be transmitted into the DRAM. So only read and write data goes to the controller, and the controller just changes this command to the all the DRAM commands from active read and write and pre-charge, and refresh and the other ones. So And the address mapping is like this. We are using the normal 8 schemate, which is just consisting rank address and row address and a column high and a bank group address, bank address, channel address, and then column row address and the other offset. So we can just using this kind of address mapping, and you can change it for adjusting the starting bit of the address map. If you are just experienced in the DRAM Sim 2, you can easily change it with that. And then PIM has its own instruction set architecture as like this table. So it just supports arithmetic operations and data operations and control operations, and everything is implemented as like Aquavortex or itself. So main function is MAC, multiply, accumulate actually. So from it we can accelerate GEMV normally. GEMV is our main function to accelerate, because GEMV is definitely a memory bound functions +2, and the other one is MAD. MAD is multiply, add, and add, which is just used for batch normalization, such as. So this is another memory bound function. So these two functions are our main, and it just support to the high level functions such as I just mentioned, AXPY or GEMV plus functions. And GEM is, we can support GEM with the assembling multiply, accumulate, but that is not the memory bound function. So it is not, we don't have any kind of gain from PIM operations. So just I just say it again, MEG and MED is our core function. And from that, we can accelerate +1 and +2 functions, such as AXPY and GEM3. That is our main function. And for the movement of data, we support two different kinds of operations, such as move or fill. Yeah, and the other one is like a knob. We need a knob to removing some kind of data dependencies and control dependencies. So we need to use a knob and jump for a loop condition, and exit to off the PIM, and do not just preventing the abnormal operation for the other read or write operations. So we just support those kind of ISA, and we can use GRF, which is called a general register file, and SRF is color register file, and bank is just directly read data from the bank. So we can use this kind of operand. So this simulator automatically find the error from the operand. So it will just print the. It is not supporting operand such as like that. So just you can use as like that. So and internally. It just checks all the data dependencies and the control dependencies. So you can just find the integrity of the your programmed instructions. And the other ones is how to install and how to configure, and the program guide. The other one you can read it. And this is published in the GitHub site public. And there are several the other projects, but the first one, PIM simulator, is the HBM-PIM simulator, and the other one is the software stacks for MI100 or MI50 to to support PIM operation. Yes. Okay. So from now on, I'll introduce the HBM power system. One is 2 GPUs and 1 FPGAs. Actually, HBM-PIM do not work as itself because it really needs a host. So we are just a memory company, so we can make HBM-PIM itself, but we need a kind of a host company to supporting us. So we find two collaborators. One is AMD and one is Xilinx. Xilinx is also AMD now, but at the time, Xilinx was just a sole Xilinx company at the time. So anyway, AMD supported us to embed our HBM-PIM to MI50 and 100 PIM GPUs. And Xilinx just supported us to use the Arvel U280 FPGA, which is using 2 HBMs on the FPGA. This one is very nice. We can do everything on the FPGA with a very high bandwidth. So yeah, we enjoyed this kind of FPGA so many times, and I will just talk about later about RLNT and GPT, how we will use this, and also a demo about that. And AMD MI50 is just based on normal MI50 or 100 GPU system and consists of 4 HBM2 stacks, and half precision GPU performance is 26.5 teraflops, and HBM bandwidth, I mean external bandwidth is 1 terabyte per second, but HBM-PIM can boost the internal bandwidth 4 times, so it is 4 teraflops from the internal. So and the capacity of it is 24 gigabyte, and it is changed to the MI100. It is much better one, because see that FP16 performance is kind of 8 times, or yeah, faster than the MI50. So it supports 184.6 teraflops. I just heard that this one was the competitor of the A100 from the NVIDIA. So the performance itself, except Tensor Core, is kind of comparable with the A100. So it was very nice GPU. And then HBM-PIM bandwidth is a little bit higher than the MI50, because the MI50's memory frequency was 2 gigabps, but this one supports 2.4 gigabps, so a little bit faster than that. And the internal bandwidth is also increased as like 4.9 teraflops, and the capacity is the same as like MI50. And these kind of GPUs has pros and cons like that. Pros, we can use only software techniques, because we don't need to hardware information, and all the software stacks are developed, and just we can call very easy functions to use PIM. But cons, the performance of PIM is limited by GPU architecture itself, because GPU cannot send, sometimes cannot utilize the HBM bandwidth at a time with a very small number of CU, or just a kind of warp in the AMD GPU. NVIDIA's GPU recorded like a warp, a bunch of the CUs, but such kind of thing, because of such kind of thing, the GPU memory utilization is limited by such kind of thing. So architecture limitation is very heavy. And yeah, so many the other aspects to limit our just the performance of the PIM. So we prefer to use Xilinx U280. It consists of 2 HBM2 stacks, and the bandwidth is 460 gigabytes per second. Unfortunately, this one is working as like 1.8 gigabps per pin. So it is a little bit slower, and it cannot just use the peak performance of the PIM itself. So though anyway, it is very nice system, because we can just show maximum peak performance gain from the FPGA, because we can design everything like from the RTL and the software, anything. We can just develop anything with the FPGA itself. But cons is developing RTL requires a lot of time and the need to verify, and so many resources. We need to pour so many resources to that, including the baseline. We need to program baseline, because 280 itself cannot compare with the GPU itself, because the peak FP16 performance is very low compared with the AMD or NVIDIA GPU. So we need to build our baseline for the FPGA. So that's the other kind of a con. Sorry, this is application one. We in our ISCA paper and Hajj's paper and ISCA paper, we use deep speech 2 on evaluation result for our paper, and MI50 using MI50 PIM. In this stage, we just have this kind of system, so that's why we use the MI50 in this time. So we are using deep speech 2, and deep speech 2 is kind of old now, but it was very new concept to just speech recognition DNA algorithm from Baidu, China, and this is a sequence-to-sequence speech recognition deep neural network. And from our observation, DS2, I mean deep speech 2 inference has a matrix vector multiplications from RNN, GRU, and LSTM layers on single batch cases, and element-wise, like batch normalization or the other kind of math operations are required for deep speech 2. So totally, more than 80% of layer can just we can accelerate with the GenV. So we choose this as like our first application for PIM. So this is the layer breakdown of the deep speech 2. So from the audio, it just generates a spectrogram, and we just uses them as like inferences input. And there are many. At first, it has a convolution layer, and then recurrent layer, RNN layers. Then this is our target, main target to accelerate, because they are consist of GenV, and fully connected layer is the last one. And the older layer has batch normalization after that. So batch normalization, we can accelerate with using math function also. This is the other kind of a memory bound function. That's why we use the deep speech 2. And then this is our demo. The left one is Aquabot, and this one is Aquabot XL. You can see the speed of changing is much faster for Aquabot XL. And this is just converting result and matches the expected result. So measuring the WER. Yeah. Okay, just finished. So average system power of deep speech 2 over time looks like this. Just blue one is using HBM, and the y-axis is the system power itself. So it uses constant power and just kind of idle power, and they use the power a lot also again and finish it. But using PIM, just it uses a smaller power than the normal one and finish it very quickly, as like this figure. So yeah, we just found that this one just MI50 PIM shows 3.2 times faster working, and the energy efficiency is 3.5 times higher, because it requires less energy, less power, and the finish is much faster. So yeah, and the working and real-time average system power analysis is I just done. And the next application is RNNT. Yeah, we are proud of this application actually, because we made everything by ourselves, from the memory controller, I mean the PIM manager, and the just RNNT accelerator itself. We just programmed with the RTOs, and we just assembled it with the Xilinx Vivado just tool. So we did everything by own. So RNNT just consists of 5 LSTM layers, and which is just encoder and predictor and joint network, as like this figure. And I'm not the algorithm expert, so just I'm using the normal structure of this vanilla RNNT model. And this one is used for the Hey Google voice search. So it was kind of a very popular algorithm at this time. And main key layer is LSTM, because the reason why is it is RNNT is RNN using RNN mainly, and totally 90.7% of the running time uses LSTM and vector matrix multiplication, which is GEMV. Kernel uses the 78.8%. So this is our perfect target for acceleration. So we designed 2 versions of it. One is for PIM and one is non-PIM, which is just to use the full bandwidth of the HBM normally. So we just developed the 2 versions. Just upper diagram uses a non-PIM version, which has a GEMV function on the encoder itself, and but PIM version it does not have GEMV because it uses HBM's covert XL's PIM block itself, and then it has a PIM initiator to utilize the PIM HBM-PIM's block. So this is why the structure is a little bit different. And this PIM initiator is just a bunch of work as a DMA working to supporting in-order memory access, because PIM in our concept requires a kind of in-order memory access at this time. So this DMA just sends command, make it in order, and it just generates PIM instruction, which I described before. And the activation function is just uses the LUT-based approximation unit in the system, in the RNNT FPGA, I mean, in the FPGA. So we build the evaluation as like this machine using a dual Xeon 8280 L. At that time, this was the highest version of the Xeon from Intel, Cascade Lake. And we placed the 2 U280 FPGAs, and one is without PIM and one is with PIM. So we just compare with it and see the total power and HBM power and just a peak performance as like this. We finally get the result as like this. Yeah, we just published this result to the FPGA 22. With the name is on FPGA-based RNNT inference accelerator with a PIM HBM. And this graph is the runtime, the y-axis is the runtime for the PIM, and the blue is using the PIM, and the yellow, not yellow, orange is using non-PIM. So just the inference is a lot. It requires much more time to, and for non-PIM version. So we compared it as like PIM4 microbenches have performance gain up to 2.5 to 2.8 for the RNNT, and the PIM reduces end-to-end RNNT execution latency by 2.5 times, and the energy consumption by 2.64. So this is our results. So PIM version is much faster and much energy efficient, as like 2.5 times. And we just show non-PIM. We did not fake the result because non-PIM version uses the peak bandwidth of the one pseudo channel in the HBM. That's like 9 gigabyte per BPS. And PIM FPGA uses 4.05 because it uses TCCDL operation because it is half of the peak bandwidth. But internally, it has 4 times higher bandwidth. So this is the external bandwidth from the non-PIM, and this is effective bandwidth from the PIM. So it can use mostly as 2.5 higher internal bandwidth from the non-PIM version. So this uses just one pseudo channel. So we projected to A100 bandwidth. And in this case, PIM FPGA can achieve 2 times faster than the world record. I mean the A100 with the tensor RT, which is just inference acceleration with software techniques. So this is our projected result. See the projected one requires 9.76 millisecond, and at the time ML4 100 with using a tensor RT requires 19.3 milliseconds at this time. And the accuracy, for the accuracy aspect, ML4 requires the 99 point of the average accuracy from their baseline, but we achieved the 6 higher than that. So it converted with the WDR, it is just less than 8.09 WDR, but we achieved the 7.66, which is better than the baseline. So we just qualified. So this is RNNT, and if you have more questions about that, just read the FPGA 22 papers, and you can send a mail to the fourth author or me. Yeah. And the application 3 is we are just utilizing the MI100 PIM cluster, and we are just short time. So I'll pass it very quickly. And we are using the HBM-PIM cluster to we build HBM-PIM cluster to show our PIM GPU is also effective on the clustered system. So we just using P5 a mixture of expert model, which is using a GEMV as the major function. So we built 12 systems with the 2 switches with using InfiniBand. And this shows the performance gain as like 2.55 on with the 48 MI100 GPUs, and the full version just we achieved the twice faster for the from the baseline. And I'll just mention about the application 4 GPT on U100AD PIM. GPT is kind of fat in this time, so a GPT model consists of summarization and the generation stage itself. This is just from DFX paper from Micro 22, and the summarization stages consist of gem functions mostly, but generation stage requires uses GEMV, which is just our main target, PIM target. So and by increasing the number of the output sequence, we call it output size, but this is output sequence, the latency of the portion from the generation will be higher, and from the summarization is just fixed as like this. So we just profile GPT-3 on GPU. So, and we found 2 key observations. Unlike BRT board, GPT-3 summarization portion is smaller than generation pace, and as the weight size increases, the portion of GEMV in the total execution time also increases as like this. For example, we are using input and output length as like a 64, 64, same, and single batch. Summarization latency is less than 5%. It's very small portion, and most of the time requires for the generation pace. And this generation pace, you have the most of the latency uses for the GEMV, which is our main target for PIM. So, I just emphasize single batch, but currently multi-batch inference is difficult to use GPT-3 because the GPT-3 weight size is very large, and service level agreement. I mean, in GPT-3 we need to wait for time as like OpenAI's ChatGPT, and then the kind of service level agreement latency have to be shorter because this is kind of a human experience problem. So it's very hard to do a batch operation for GPT-3. From this, it seems that GPT-3 is a kind of definitely memory bounded application for the capacity and bandwidth also. So yeah, I'll pass it very fastly because this is kind of a simplified GPT-3 layer breakdown, and GEMV layer is yellow portion, and for the multi-head attention, we have 3 QKV projections and output projections, and feed-forward network itself, and there is a GALU after feed-forward network 2, and the orange one is everything is just requires as like GEMV, and the portion of it increases by the size of the weight itself. Yeah, for example, it's 1.3 billion, but if we're using a 54 billion or 130 like that, it just a portion of a GEMV, it goes like more than 90%. So we are thinking that GEMV is a perfect fit for PIM technology, and which means GPT-3 is very nice application for the PIM technology. So we are just developing GPT-3 accelerator. This is an ongoing project actually. So we are developing in the GPU and FPGA concurrently, and PIM is key for small latency to keep SLA, I just said before, and with a single batch GPT-3 inference. If you use a multi-batch, GEMV just convert to the GEM, so this is not memory bound application anymore. But now, for just I mentioned about that, to keep SLA, it's hard to use the high number of a batch itself. So that's why PIM is very effective on the GPT-3 inferences. And these accelerators would be released on this autumn, very soon. So maybe on the other kind of conferences or whatever, we will introduce the progress of the GPT-3 accelerator with the PIM technology. So wrap up. Sorry, I'm just over time. Sorry what. There are several lessons from HBM-PIM. This is what I presented in the VLSI short course last year. First, DRAM technology is really large and slow. Really large, really, and very slow, really slow, because of to keep the cost itself. And the custom design and EDL tool flow is the best solution for limited resources. Just I said before, just nobody wants to mess up the HBM, no more DRAM, just businesses. So we need to minimize the resources as like this. So, sorry. And the energy efficiency with PIM is much better than our expectation, as like introduced, just I mentioned Lisa Su's presentation, and that was 85%, and our expectation was 70%, and it's more efficient than our expectation also. And I need a specific protocol, I mean JEDEC protocol and interfaces for PIM computing, because deterministic interfaces many % for performance, but so many engineering issues to resolve it for now and future. And the final, software is key to success. Yeah, without software, we cannot do anything for PIM. Software is very important, software support. So our effort is just like this. We just target wider, we just make support to wider target applications like Jamboy or activation functions and wider numerical formats for each kind of memory type through the from the LPDDR to the HBM 3PIM or whatever, and various DRAM type supporting like LPDDR PIM or HBM-PIM, and the new standard, a command truth table for PIM and the PIM exclusive read, write, load, and store commands like this. And we are actually developing the AC timing parameters for PIM also. Unlike the Aqua-Vortex, that one is using the legacy timing parameters, and that is not capable for maximizing the performance of a PIM. So, and collaborate with the academia and the other industry, like brilliant ideas for PIM and the next kind of next generation memory devices like CXL and the wider functions. And moreover, we just focusing also about the CXL PNM. Yeah, this is the other YouTube video for that, as like PIM. Concept is similar, but the PNM is outside of the memory. It's on the CXL controller. The gain itself is a little bit smaller than the PIM technology, but the target application could be wider than the PIM. So it is another kind of our stream. Yeah, we are just focusing both of the items after AxDIMM. So this is end. Thank you for listening to my presentation. Thank you. Yes. Yeah, thank you for a very nice question about that. We are also very curious about that, and we just make kind of estimation for making supporting HBM-PIM or PIM supporting ASICs. For FPGA, it just uses internal very large AXI matrices, and which is just built very nicely for FPGA, but the internal frequency is limited to, I'm using 300 megahertz, and that is super high actually. Normally FPGA uses less than 100 megahertz, but we made it very carefully. So it works as like a 300 megahertz. But if I just change it to the ASIC, it will be much higher. But the problem is we are just focusing to the memory bound operation, not the computer bound operation. So, and then we just utilize FPGA very well. I mean, HB-PIM very well. But that is limited because we need to do something in the FPGA itself, as like the other operations such as activation functions and the jam functions, whatever. So in that case, that could be also accelerated. So in summary, it depends on the how many portions are just bounded to the memory. Just as I just mentioned before, RNNT is 80% of the portion is memory bounded. In that case, from the ARM-DARS flow, FPGA is also just shows a very nice performance, and then, but some function just shows 30% memory bounded. In that case, ASIC is much better, but in the case also the performance gain from PIM is degraded also, right? So FPGA was a very nice solution to show our performance is variable. But in the normally the neural network model just uses some of the computer bound operations and some of the memory bound operations as like GPT. GPT-3 uses summarization phases and generation phase, and which is just computer and memory bounded. And we can also accelerate summarizing phase with the ASIC chip. I think in that case, that is very effective for the accelerating or specific neural network model. Yeah. Program model support. That is actually I am the hardware and the hardware to the software supporting at the kind of thing I'm supporting, and the software platform itself is the other guy's job. But we are doing we have the other presentation materials, but that is kind of confidential. But we are supporting open MP or open CL, and we are supporting, we are gathering all the CXL and the PIM and PNM to one kind of software environment, which is we call the one MCC, and we can find on that, yeah, here. So we actually supporting the sort of merging all the memory product from the Samsung Electronics. We are just developing this. And if you just ask a question about the TensorFlow or whatever, we are supporting the TensorFlow itself to utilize PIM on the GPU, but not for FPGA or whatever, because the FPGA platform is not capable for the TensorFlow itself, because it needs to modify so many things. So, but we are just supporting functions for like a PyTorch or whatever. Yeah, we are supporting the PIM libraries. Yeah. We have two kinds of way. One way is just automatically compiler just fits all the changes, all the functions, and by the size of the Jamv, it just changes to the CPU or GPU operations, or it's capable for the PIM, and then just offload to the PIM. In that case, it's just automatically changes it. We have that kind of compiler, and we have the custom path who just knows PIM very well, just customly coding the PIM instructions by himself to utilize PIM more efficiently. We have two kinds of it. Yeah. Yes. Yeah.
Let's talk. So your CXL technology, what kind of CXL protocol are you supporting right now?
You mean CXL PNM itself? Before the answer, I'm not in charge of CXL PNM, just I am developing AxDIMM's core architecture and the accelerator itself, but I can say about that. We are just focusing type 3 and UNMEM interface, because we are just developed a memory expander system, MXP. So based on that, we are just utilizing the not the internal, how can I say, board level bandwidth, because the CXL bandwidth is kind of small, and we just put many memory channels and utilize them as like a GPU or domain-specific accelerator, and utilize them in the CXL technology, like using a type 3.
Are you also considering switch technologies that go with that?
Switch? It's a little bit different because yeah, we also just mentioning about the switch means we are just concerning the pool system, right? Memory pool system. Yeah, we are just also concerning about the pooled memory system.
Right. So you're deploying those PNMs, essentially, you might consider
right. Yeah. Like yeah, disaggregated server system.
You don't know exactly when that's going to happen.
Well, we are under developing, and that will be announced very soon. But at least I'm saying we can support disaggregated server, yeah, with the CXL3 or whatever, yeah, later. Currently, we are using the CXL 1.1 and 2, so it will be much can I say enhanced technology for the system. CXL3 era, we can utilize those kind of switch-based disaggregated servers with using a CXB-PNM and using they as like a distributed core. Yeah. Thank you.
You tested the HBM with other workloads like
what which sequence?
genomic.
Well, genomic sequence requires a very high numerical format, right? Like FE64. So we are supporting 16 now, but our next target is supporting HPC also. Our first target was targeting AI only, but our next target is utilizing them into HP system, such as sparse operations and yeah, as you mentioned, there's like a genetic operations or whatever. Yeah, so we will expand our system to the HPC. That's our action items from the supercomputing last year. So we are developing in that way. Yeah. Thanks for very nice question. Yeah. Oh, well, very nice question. In this stage, we are just supporting SIM, and everything is just have no dependencies, so not capable to move data or it's from the interbank or the interchannel or whatever, because it requires a lot of how can I say overhead, area overhead for the interconnect on the DRAM. So we just don't want to do that in this stage, but if we find the very good, nice example to support those kind of functions, we will implement it. Because it depends on the customer. Thank you.
If there are no other questions, I would like to very quickly ask you something, because you mentioned that when you were presenting, you know, the work on GPU and also on FPGA, you mentioned that the GPU architecture limits the gains.
Oh yeah, that's right.
And I think you said something about the warps.
Yeah.
So
yeah.
Why is that? Why the GPU limits the gains?
Well, it's from the legacy computer architecture. Load store unit just decides the memory bandwidths, right? One core cannot use the core memory bandwidths. So it depends on like that. We just build PIM as like a passive devices, which means to utilize PIM perfectly, a core need to send memory transactions for full bandwidth, right? But in the GPU architecture, that is very hard. We need to assemble so many works to utilize the full bandwidth. In the case, mostly all of the work would be utilized to read the HBM. So in that case, just all transactions are like a mixed, and need a kind of barrier because our implementation requires the in-order just memory transaction. So because of that, it just needs to generate kind of read memory bandwidth for peak. It depends on the memory GPU architecture. That's the reason why I said.
Nice.
Yeah.
Okay. Okay. Yeah. Thank you very much.
Thank you.
We talked, and now we have to the second talk of this section of the tutorial. It's going to be about processing using memory.
Ataberg, are you there?
Hello. Can you hear me?
I cannot hear you.
Okay.
Wait.
I think it's on. Can you hear me now?
Yeah, I can hear you now.
Oh, okay. Yeah, I am here.
Yeah, people can hear you also in the room. So feel free to share your screen.
Oh, I'm starting now then. Okay.
Yes, please.
Okay. Let me open my camera also.
So yeah, let me just clarify that I was I was planning to give a summary of processing using memory. You can find the slides in the website. I didn't do that because we are running a little bit short of time, and because Professor Mutlu already introduced processing using memory. In the morning, he talked about row clone, which is a technique to copy entire rows in a different subarray to another row in order to accelerate memory copy operations or initialization operations. He also talked about AMBIT, AMSIN DRAM, that are ways of performing computation by activating multiple cells at the same time. Ataberg is going to talk about these techniques and in the context of a real framework that enables much more sophisticated processing using DRAM studies. So yeah, feel free to go ahead whenever you're ready, Ataberg.
Okay, thank you for the kind introduction, Juan. So as Juan said, I'm Ataberg. I'm a PhD student in Safari, and I worked on this project PyDRAM, an FPGA-based framework for end-to-end evaluation of processing in DRAM techniques, which I'm going to present now. And it was published in TACO this year. I'll start with an executive summary. The commodity DRAM-based PIM techniques improve the performance and energy efficiency of our systems without incurring any additional DRAM hardware cost. However, there are challenges of integrating these techniques into real systems, and these challenges are not yet solved. And these challenges cannot be solved by using general-purpose computing systems, special-purpose testing platforms that we use to test DRAM chips, for example, or system simulators. And our goal in this work is to design and implement a flexible framework that can be used to solve these system integration challenges and analyze the trade-offs of end-to-end implementations of commodity DRAM-based PIM techniques. A key idea is to develop a FPGA-based framework that enables us to achieve these goals, essentially. Using our framework, we conduct 2 case studies on two recent commodity DRAM-based PIM techniques on a real FPGA prototype. In our first case study about in-DRAM bulk data copy operations, we show that in-DRAM copy operations provide 119 times speed up over CPU copy operations, including system support. And to conduct this case study over PyDRAM's code base, we only have to add 198 lines of Verilog and 565 lines of C++ code. In our second case study about an in-DRAM to random number generation technique, we show that an end-to-end implementation of such a technique can provide high throughput to random numbers at very low latency. And implementing this takes us only 119 lines of additional Verilog and 78 lines of additional C++ code. And PyDRAM is fully open source at this link down below. And now I'll continue with some brief background on DRAM. Here is how DRAM is organized today. We have the CPU, and the memory controller in the CPU communicates with a set of DRAM chips in a DRAM module through a memory channel. Inside the DRAM chip, we have multiple DRAM banks that share the common interface. And DRAM banks are organized into subarrays that consist of a set of word line drivers and sense amplifiers. Subarrays are further partitioned into DRAM mats, which are collections of DRAM cells that are separated from each other by these word line drivers. And finally, DRAM cells are laid out onto a two-dimensional array of word lines and bit lines within a DRAM mat. And we refer to a row of DRAM cells as a DRAM row. And this shows a simplified diagram of a DRAM cell. Now we'll look at how DRAM operates at the scope of a single subarray. And because memory controllers typically access DRAM cells in the granularity of a cache line, we combine consecutive cells to form cache lines in this diagram. On the bottom, we have a timeline of DRAM commands. To access a cell in the row that I highlighted with the blue color above, we must first issue an activate command. This will copy the cache line, all the cache lines in the row to the sense amplifiers. At this point, we can read data in cache line granularity from the sense amplifiers by sending read commands. If we want to access another DRAM cell, we must first send a precharge command to close the enabled DRAM row. And at this point, we can send another activate command to similarly access the data in another row. To ensure that we operate our DRAM chips correctly, we must obey certain timing parameters that define intervals between DRAM command pairs. The first timing parameter that's relevant to us is the TRAS timing parameter. It's the time required for the charge to become restored in the capacitors on the open row. And it dictates the amount of time we need to wait between successive activate and precharge commands. And TRP is the time it takes for a bit line to become precharged to half VDD such that we can issue a new activate command. This is the time between successive precharge and activate commands. Sorry. Oh, I went too far ahead. Okay, I need to come back. Yeah, almost there. And finally, TRCD, the time it takes for sense amplifiers to amplify the bit line voltage to an IO readable value. And we have to wait for a TRCD amount of time between the activate command and the next read command. I'll continue with, again, summarizing processing in memory techniques in the context of DRAM-based PIM techniques. So commodity DRAM-based PIM techniques use operational principle of commodity DRAM chips to move data or perform computation inside the DRAM chip. There are many techniques that we have seen that DRAM chips were capable of. The first one is row copy operations. We can do in DRAM bulk data copy operation at DRAM row granularity. We can generate two random numbers in DRAM chips. We can implement physical unclonable functions, and we can perform the majority operation. I'll focus on these two. So I'll give you the key ideas of these techniques, essentially. So the key idea of row clone is, I will describe it in this slide using this diagram. Here we want to copy the source row that's highlighted with the orange color to the destination row. So we must perform two steps, essentially. First, we want to copy the source row to the sense amplifiers, and then we want to copy the source row from the sense amplifiers back to the destination row. We can already perform the first operation using activate commands in real DRAM chips. And to do the second operation, we use carefully crafted DRAM command sequences. What does this mean? We issue an activate precharge activate command sequence, but with greatly reduced DRAM timing parameters. as was done by a prior work that demonstrate in-DRAM copy operations in real DDR3 chips. This is another pictorial representation of what we do. So when we use standard DRAM timings and send these three commands back to back, when we use the standard timing commands, this results in the following in DRAM sequence. Essentially, we activate row S, then pre-charge the bank, and then activate row D. When we violate the DRAM timings and bring the commands closer, what this does is basically we get rid of the pre-charge operation. And what this means is we activate row S, bring data to the sense amplifiers, and then we activate row D without pre-charging the back. That brings this data back from the sense amplifiers to the destination node. And we can perform these in real DDR3 chips. I'll continue with the key idea of D-range, our true random number generation technique. It essentially is, so this diagram shows many DRAM cells, and they're sized and colored according to their failure probability when we access them with a reduced access latency, that's reduced TRCD. So the red and smaller cells indicate cells that have a high chance of failure when we access them with reduced latency, and the green and bigger ones are they don't fail as much as the red ones do. The key idea of D-range is to identify the cells that fail with a 50% chance, meaning that when we access them repeatedly, we will get a series of random bits essentially, and those bits we use to form our random numbers. And commodity DRAM chips can already do these because all we have to do is to perform reduced latency access. Essentially, we reduce the TRCD timing parameter. Now we have all these nice in-DRAM PIM techniques, but how do we provide system support for it? I'll try to describe what's needed over an example. And this is a depiction of the computing stack that we're all aware of. So at the application level, we want to perform a bulk data initialization application. We want to support this application essentially. And at the device electron levels, we want to use the in-DRAM bulk data copy capability. So what's needed? Essentially, we need some support for custom timing parameters that will allow us to perform these command sequences I described. We need some sort of control logic to schedule these PIM operations and essentially control everything regarding the execution of the PIM operations. We need a software interface to execute these PIM operations to allow the user to execute them, and a supervisor software for basic, simple system support that I will describe in more detail next. So PyDRAM's key idea is to bridge this gap, the system gap, with customizable hardware and software components. And in doing so, it allows its users to rapidly implement PIM techniques, solve system integration challenges, and analyze end-to-end implementations of their DRAM-based PIM techniques. PyDRAM is made up of 4 key components. At the hardware level, we have a component that controls PIM operations, another component that provides support for custom timing parameters. At the software level, we have an interface for application to use to make use of the PIM capability, and a supervisor software that provides basic system support. And we attach these key components to a real computing system to develop PyDRAM's real system prototype. And next, I'll describe the key components of PyDRAM over this figure. So starting with the PIM operations controller. So this component decodes and executes PyDRAM instructions that will perform PIM operations, such as an in-DRAM copy operation. It's connected to the hardware system as a memory mapped module, meaning that it receives these instructions over the memory bus from this RISC-V CPU core. And the 3 registers we have are accessible over the memory bus. And this makes it easy to port PIM operations controller to another system that uses a different CPU, ISA, for example. And the controller is connected to the memory controller. The PIM operations controller connects to the memory controller over a simple interface where it first sends a request for a PIM operation and then waits until it completes and then reads back the results. The PyDRAM memory controller performs PIM operations by violating DRAM timing parameters. It implements one state machine to essentially execute a conventional memory operation like a load and store instruction. And we we essentially replicate these state machines to allow this controller to perform PIM operations. And a developer of the PyDRAM infrastructure can similarly do that to implement new operations. And the physical interface component inside the memory controller controls the physical DDR3 interface. It receives commands from the command scheduler and it operates the DDR3 pins essentially. On the software side, we have the PIM operations library that contains customizable functions that interface with the PIM operations controller. An example function in the PIMolib library executes many load and store requests to communicate with the PIM operations controller. And finally, this custom supervisor software, it exposes PIM operations to the user application via system calls, and it contains the necessary OS primitives, the OS primitives that we found are necessary to develop end-to-end PIM techniques. For example, memory management and allocation support for row clone operations. Now I'll describe how PyDRAM operates over an example. So here the user is calling a copy function to perform a row clone copy operation inside the DRAM chip. The application makes a system call with these semantics. The application wants to copy n bytes from array A to B. And the custom supervisor software calls the corresponding PIMolib copy function with these semantics, where S is the physical address of the source DRAM row, and D is the physical address of the destination DRAM row. And this executes two instructions in the CPU, two store instructions. The first one updates the instruction register in the PIM operations controller with the semantics I described in the previous slide. And the second one sets the start flag in the flag register in the PIM operations controller. This indicates the start of the execution of the PIM operation. And then the PIM operations controller instructs the memory controller to actually perform the row clone operation, meaning that the memory controller should send that command sequence with violated timing parameters. At the same time, the PIM operations controller will reset the start flag and set the acknowledge flag to essentially allow for the execution of the next PIM operation. And the PyDRAM memory controller issues these command sequences with violated timing parameters to the DDR3 module, and then it sets the finished flag. Meanwhile, the copy PIMolib function will periodically check either the acknowledge or the finished flags based on a user-supplied argument using load instructions, and it will return when the periodically checked flag is set. And we didn't use the data register in the PIM operations controller in this example because the results of row clone operations essentially is stored in memory. But we use it for to store the random numbers generated by our true random number generator, and I'll describe that later. So to summarize these components, we have 4 key components in PyDRAM that orchestrate the execution of PIM operations. And we developed a prototype, FPGA prototype of this system on a Xilinx DC706 FPGA board that I show in this figure. We have, as the system, we have a RISC-V system that contains an in-order pipelined Rocket CPU core with L1 data and instruction caches and a TLB. And we also have a DDR3 module from Micron that we call the PIM-enabled DIMM, essentially a commodity DIMM, with the following with the following characteristics that I show you in the slide. And this is the DIMM we perform the PIM operations in. I'll continue with the case studies we performed. So this is to remind you the key idea of how we perform row clone operations. We essentially violate DRAM timing parameters. And to do that, we extend the PyDRAM memory controller to support this DRAM command sequence with violated DRAM timing parameters. And then we expose the operation to PIMolib by implementing the copy PyDRAM instruction. In our Verilog design, this takes us, basically you need to add only 198 lines of Verilog code to PyDRAM's Verilog code base to implement row clone support. Then we investigate the system integration challenges of row clone, and we identify 2 challenges. The first one we call memory allocation, and this stems from the intra-subarray operation of row clone operations. And then the second one is the memory coherency. which basically is due to how we perform computation inside the DRAM chip and how this basically the data we're operating on in DRAM could have cached copies in the system CPU caches. And to fix this essentially, or to mitigate these coherency issues, we implement the CL flush instruction in the RISC-V CPU, and we evict this instruction evicts a cache block from the CPU caches to the DRAM module, and we use these before we perform roll call operations to evict the source and destination operands from the caches. I'll talk about the first challenge in more detail now. So roll call has certain memory allocation requirements, and I'll describe them over this figure. This figure is showing two different banks on the y-axis and two different subarrays on the y-axis and the two different banks in the x-axis essentially. And the requirements are as follows. The first one is what we call the granularity requirement. The operand must occupy its DRAM row completely. And the second one is the alignment constraint, which states that the operands must be placed at the same offset in their respective rows. And the third one we call the mapping constraint, which says that the operands must be placed in the same subarray inside the same bank. And this is because really we can only perform roll call operations inside the subarray. And finally here, the fourth allocation satisfies all three requirements, and this is what we want. And to get this mapping that we want, we implement a new memory allocation function. We call this alloc-align, and the goal of this function is to allocate virtual memory pages that are mapped to the same DRAM subarray, and these virtual pages are aligned with each other. So this is the semantics. This shows the semantics of the alloc-align function that we implement. It has two parameters, the size and the ID. Size is the number of bytes the user wants to allocate for an array, let's say. And ID is a parameter the user uses to put different arrays that get allocated using different calls, different alloc-align calls in the same subarray. So if the ID is the same for two different alloc-align calls, our implementation will put those arrays in the same subarray. And this returns a virtual address for the user to use later. And I'll try to very briefly describe how this works. We have a key component, key data structure called the subarray mapping table that an alloc-align call will access. Here is this example alloc-align call where the user is trying to allocate a 4 kilobyte array to be placed in subarray 0. Alloc-align will get the physical address pointing to a DRAM row in subarray 0 using by accessing the subarray mapping table. And then it essentially updates the page table to map this virtual address that it just allocated to subarray 0 using the physical address it retrieved from the subarray mapping table. And for more details on how this works, I have to refer you to our paper and or our other talks that I will link to in later slides. We evaluate the performance of roll call operations with system support in our prototype. This table shows our system configuration, and we run two sets of micro benchmarks that we call CPU copy and roll clone copy. CPU copy uses load and store instructions to copy or initialize arrays. Roll clone copy benchmarks use in DRAM copy operations. We test these with and without CL flush operations, and I'll describe that next. We also use copy and initialization heavy workloads. Fork bench is something we use as a copy heavy workload, and compile is something we use for as an initialization heavy workload, as prior work did. And then we were able to run the spec 2006 libquantum workload where we replaced the alloc calls with in-DRAM initialization. And I'll talk about the results quickly and very briefly. And then one final detail here is the 8 kilobyte row size of our DRAM modules essentially determine the in-DRAM copy and initialization granularity that our system supports, meaning that basically with a single row clone copy operation, we have to copy at least 8 kilobytes from one row to another. This plot shows the throughput improvement in copy and initialization operations in using two different bars. For the copy and initialization micro benchmarks, on the x-axis we have various array sizes increasing from left to right. So we basically observed that in DRAM copy and initialization operations improve throughput by 119 times and 89 times. This is when we include system support, but when we don't do any, when we don't execute any CL flush operations. So here we're assuming the data that resides in DRAM is does not have any cached copies at all. And then we evaluate the overheads of the CL flush operations. This plot shows the same throughput improvement on the y-axis. On the x-axis, we have the dirty cache block proportion. Here we're copying an 8 megabyte array to another 8 megabyte array for the copy bars. And for initialization, we're initializing an 8 megabyte large array. And the x-axis essentially describes the proportion of data in this array that's dirty. So for the leftmost bars, none of the cache blocks are dirty and all of them are cached. And the rightmost bars assume that all of the cached copies are dirty. So this means that we have to write all of the cache lines back to DRAM. And for the leftmost bars, the case is we only have to invalidate the cache blocks. We don't have to do any write back to DRAM. And our takeaway is that CL flush dramatically reduces the potential throughput improvement. And in the paper, we discuss how this can be improved. I'll briefly describe the results we have for other workloads. I'll summarize them. So for Forkbench, in this plot, we show on the left y-axis the speed up we have for row clone operations. And on the right y-axis, we plot the amount of time the fork workload spends doing mem copy operations. And this is the line essentially that's associated with the rightmost y-axis, and the bars are associated with the left y-axis. And on the x-axis, we have different configurations of the fork workload, and the number after the hyphen indicates how many pages fork has to copy after forking a new process. And we see that performance improves as fork has to copy more pages. And for compile, we observe 9% execution time reduction provided by in-DRAM initialization operations. And we think this is reasonable because we estimate compile to spend only 17% of its time on initialization. We have a similar result for the spec 2000 libquantum workload, where we have 1.3% end-to-end execution time reduction, and we estimate it spends 2.3% of its time on bulk data initialization. I'll briefly describe our second case study, and then I'll wrap up. So this slide I put here only to recall the key idea of DRange. We want to find the cells that fail with 50% chance when we access them with reduced access latencies. And to implement DRange, we need to identify 4 DRAM cells. We identify 4 DRAM cells that fail randomly in one cache block. And we continuously access this DRAM cell to generate random bit streams. And we periodically generate these 2 random numbers by accessing this cache block that we identify. We have to reduce the access latency before we access this cache block. And we store the random numbers we obtain in a 1 kilobyte buffer in the PIM operations controller. And then we allow the programmers to read random numbers from this from the data register using the rand-DRAM function call. And all of these take 190 lines of Verilog code and 74 lines of C++ code. To evaluate it, we develop a very simple micro benchmark that keeps reading through random numbers, essentially with different periods. And here we show the TRNG period on the x-axis and the throughput we get on the y-axis. And we observe that PyDRAM's DRange implementation generates 2 random numbers at 8.3 megabits per second. And I'll conclude with another summary. So commodity DRAM-based PIM techniques improve the performance and energy efficiency of our systems with no additional DRAM hardware cost. However, there are challenges in integrating these techniques into real systems. And our goal is to design and implement a framework that can be used to essentially solve these system integration challenges. And our key idea is to develop an FPGA-based framework. And we evaluate this FPGA-based framework that we develop using 2 case studies. In the first case study, we evaluate row clone in real DRAM chips, and we show that it can significantly improve the copy operation and initialization operations throughput. And the second case study, we implement DRange and show that it can be used to generate true random numbers at high throughput and with low latencies. PyRAM is completely open source at this link. We have an extended version of our TACO publication on archive at this link. And I have this video where I describe all aspects of PyRAM in more detail and also give a tutorial on how to use it. Thank you very much for listening to my presentation, and I'll be happy to take your questions now.
Questions for Ataber?
Hello, I can barely hear Juan.
Yeah, sorry.
Yeah.
No, I'm asking the audience if there are any questions for you. Do you guys have any questions? Okay, I don't see any questions. I just want to ask you something. Maybe in your presentation, we don't see any experiments doing ambit-like operations, like activating multiple rows to perform bitwise operations, which in the end is a more sophisticated way of doing computation than row clone, let's say. So what are the challenges that prevent you from implementing those ambit operations?
So I have 2 answers. The first one is the page limits. We can only pack so many case studies in a paper and also describe the framework in detail. The second answer is basically, I don't see any, let's say, very hard to solve challenges. I think ambit and row clone share similar allocation requirements. And what we developed could be reused to implement system support for ambit operations in PyDRAM. I think that's basically what I think. I think we could extend PyDRAM slightly to support ambit operations. But what I mean by ambit operations is really majority operations that we perform in real DRAM chips using similar DRAM command sequences.
I see. Okay. Yeah, that makes sense. Thank you very much, Ataberk, and thank you so much for your participation in the tutorial. And now we have a break. Like I guess it's like about 15-minute break, and we will be back at 4 p.m. So thank you, everyone. In the meantime, if you want to discuss anything, ask questions, I'm going to stay here. So I'm all yours. I don't know what's wrong here. Okay, yeah, I think we are ready to continue, and we can do it right now if you're ready and interested in the rest of the tutorial. So let me very briefly remind you what are the remaining contents from now until 5:30. The first thing I'm going to present is this presentation, this talk about accelerating modern workloads on a general purpose PIM system, which is related to what we have seen in the previous presentations about sequence alignment. We have covered sequence alignment and what else? And we have also had sparse matrix vector multiplication. Now I'm going to present another two more recent works. One of them is targeting machine learning training, and the other one is something like a library for transcendental functions, which in principle are not ideal for processing in memory systems because they are usually fairly complex to implement. But we came up with a couple of ways or several nice, actually more than a couple, nice ways of implementing these workloads on the HB-MEM PIM system, and this way we can still save even more data movement. And the second presentation, I will probably go quickly over it, is about things that still need to be done to enable the processing in memory in real computing systems. It's kind of a let's say presentation full of open questions and things that still need to be done or still need to be researched. And after that, I have also some slides about the hands-on lab that I know some of you are already working on, hopefully. And we can take a look at them, and we can conclude by answering maybe questions about how to program the system, etc. So, well, at any time, feel free to stop me. Now that we are here in a small group, I think that is a good opportunity to have even more tight interaction and hopefully clarify any questions you may have about the HB-MEM PIM system or any other processing in memory system that we are aware of. Okay, so let me start with this accelerating modern workloads on a general purpose PIM system. This is indeed related to the next talk as well, that is how to enable processing in memory, because one of the things that we need to or one of the potential barriers for the adoption of processing in memory are applications and software for PIM. So first of all, identifying what are suitable applications for processing in memory systems, how to program these processing in memory systems, and how to create efficient software for them. This is very much related to the benchmarking and workload suitability study that we have already covered in our work, and I have already mentioned this in the beginning today, the benchmark suite that we created with 16 different workloads. Here you can see an entire list of them. As you can see, there are dense linear algebra, sparse linear algebra, databases, data analytics, graph processing, neural networks, etc. And our goal here was to have a sort of comprehensive set of workloads with very different characteristics in order to understand how this processing in memory system performs for different computation patterns. The thing that is clear is that all these workloads can be considered memory bound, and we can say so because we analyze them using the roofline model, and we see that all of them fall in the memory bound area of the roofline. So they have low arithmetic intensity, and that's a key characteristic for a workload to be potentially suitable for processing in memory. But of course, one thing is the potential, and a different thing is the reality when you program those workloads for a specific processing in memory system. The workloads are also diverse, not only in terms of application domains, as you have seen, but also in terms of memory access patterns, operations and data types, and communication and synchronization needs. And in terms of communication and synchronization, in the morning, I talk about the intra-DPU synchronization primitives. Inside the DPU, when you program the DPU, you can use barrier, handshakes, mutexes, semaphores. But also, it's important to evaluate or think about these workloads in terms of the inter-DPU communication, inter-PIM core communication that you may have, because this is in the end costly in this kind of system.
So is there no communication in your sparse matrix vector?
In a sparse matrix vector multiplication, the way that we have implemented it here, there is no communication because we partition the matrix by rows, and we assign consecutive rows to different DPUs.
But it is parallel?
It's parallel, yes. You have one DPU, or you can just think about one PIM thread running on one PIM core, working on a single row and the vector.
But they're just all independent.
They are all completely independent. But yeah, this is kind of, let's say, naive implementation as compared to what Christina presented earlier. This was just the first version, let's say. She has explored much more, doing the other partitionings, as you know. And but yeah, that's why there is no communication here. Okay, so yeah, well, in terms of inter-DPU communication, there are different workloads that require this inter-DPU communication. Some of them just need to merge results on the CPU. For example, if you are creating a histogram of a, let's say, very large image, each DPU can calculate its own subhistogram, and there you will send all subhistograms to the CPU, and then we'll perform the final reduction on the CPU. Or in some other cases, you need to do a redistribution of intermediate results. This is what happens, for example, in iterative algorithms, graph processing, for example, where you, let's say in BFS, which is one of these algorithms. We are using a top-down approach, and what that means is that in every iteration, we create a frontier, and this frontier is the input for the next iteration of the algorithm. But all DPUs are creating a partial frontier. We need to merge them in the host and then redistribute, right? Well, the workloads are publicly available, as you can see. What I can show you very, very briefly is some evaluation of these workloads, because we have analyzed them with strong and weak scaling experiments on a couple of UPMEM PIM systems. First of all, we have strong scaling experiments on a single DPU, varying the number of tasklets. Then we have the strong and weak scaling analysis on a single rank up to 64 DPUs, and then up to 32 ranks. And we also have a comparison with CPU and GPU. I will probably skip that part because I already showed the results in the morning. This is one of the systems that we have used. You have already seen a picture of this one system with more than 2,500 DPUs. It's a dual socket CPU, as you see, and there are some DIMMs of main memory and some PIM enabled DIMMs. In total, as I said, 2,500 DPUs and up to 160 gigabytes of PIM-enabled memory. And this is a smaller system that we use. That was actually the first system that we got access to, is with only 640 DPUs, significantly smaller, but it's still quite representative of what an HBM-based PIM system can be. Data sets, we have different data sets for strong, weak scaling analysis. As you can see, I think I can go quickly over this and then start showing here some results of this analysis. For example, these are 16 plots for the 16 workloads doing the strong scaling analysis on one DPU. We change the number of tasklets or PIM threads from 1 to 16. And as you can see, in each of these plots, you'll see fraction, or you will see the breakdown of the execution time, a fraction of it that is called the DPU time, because that's the kernel time that runs on the DPU. But then we also have, or may have, inter-DPU communication whenever we really have that. We have CPU to DPU data transfers, and we have DPU to CPU data transfers. And the plots also show the speed up for the kernel. Observe that we are increasing the number of tasklets from 1 to 16. And what we can observe in the speed up, and actually in the majority of the workloads, is a linear speed up with, it's only that at some point the performance stops scaling because the saturation point of the DPU throughput happens at 11 tasklets. So let's say that with 16 we have the same speed up that we can have for 11 tasklets, and that's why we are basically here under the this 12 mark of the speed up. Some more observations. Well, I was actually saying that the best performing number of tasklets in most of the cases is 16. We see linear speed up, and we see that the number of tasklets greater than 11 is usually a good choice for most real world workloads. There are some workloads that don't use intra-DPU synchronization, so those don't have any problem for scaling in general. In some cases, in some other cases, synchronization is lightweight. They are using some intra-DPU synchronization, like, for example, a barrier or a handshake, but the cost, the overhead is quite small. And some other one, and in other ones, you really see much more overhead from using these intra-DPU synchronization primitives. For example, these three workloads here, BFS, one of the versions of the histogram, and one of the steps in the transposition use mutexes, and this caused great contention. For example, for the histogram, observe that the best performing number of tasklets is not anymore 16, now it's 8. But this is because here we are creating a histogram. We have one single histogram for the entire DPU, and every time that we have, so in the histogram, as you know, we need to read input elements from the input image, and then depending on what's the value of the specific element that we accessed or we read, we need to update one being, we need to increase a counter of the histogram, right? And because there is a single histogram for the entire DPU, we need to use a mutex to prevent data races. So that's indeed what causes the contention, and the fact that the best performing number of tasklets is not 16 in this case, but is only 8. So in general, we don't see much overhead from intra-DPU synchronization primitives, but there is still there. They can limit the scalability in some cases. In some other workloads, well, not some other workloads, very few workloads, for example, in one of the steps of this scan operation, which is just a single addition, here we see that also the performance saturates at 8. This is a very rare case. Remember that most workloads are compute bound in this architecture, but in the case of this add kernel of the scan SSA, we are just adding one value to each element of an input array. And in the end, that's very little computation, and that's why this one behaves as memory bound. But this one is a very, very rare case. In some other cases, we might need to transfer large chunks of data. That's, well, it's happening in one of the the kernels of the transposition. But now let me show you some other scaling results. These are for Needleman-Wunsch, for example, executed on one rank, 64 DPUs, because here we wanted to also do the strong scaling analysis on one rank, from one DPU to 64 DPUs. There are several observations here. For example, most of the cases we see linear scaling, and that's pretty good, pretty positive thing. We can partition the workload, assign different parts of the workload to the different DPUs, and we see that the performance scales and scales almost linearly. In some other cases, for example, BFS and Needleman-Wunsch, we see that there is some load imbalance, for example, in BFS, because in the end, graph processing is more irregular. And in Needleman-Wunsch, for example, the amount of parallelism in the workload also depends a lot on the specific phase of the computation. For example, Needleman-Wunsch, we have to calculate a dynamic programming matrix, and by doing it we do it by anti-diagonals, right? And the size of the anti-diagonals changes over the course of the execution. So when you have a very short anti-diagonal, the fact that you are using more DPUs doesn't mean that the performance is going to increase, because you don't really have so much computation. It's only in the largest anti-diagonals where you can really exploit more parallelism. So that's why we don't see, let's say, linear scaling for Needleman-Wunsch in these experiments with multiple DPUs. Some workloads don't need inter-DPU synchronization. So in that case, there is no overhead. In some other cases, there is a need for inter-DPU synchronization, but still the maximum number of DPUs shows the best performance. And what that means is that the overhead of the inter-DPU communication is tolerable. And in other cases, there is heavy inter-DPU synchronization. For example, this one is BFS. Observe that the fraction of the execution time that is devoted to inter-DPU communication is very, very high here. And this makes that, you know, even the total execution time is shorter for 16 DPUs than for 64 DPUs. So this one is clearly not a suitable workload for this PIM system. And it will be for sure a challenge to make this PIM system more suitable for this kind of workloads where you have very regular memory accesses, and you need also a lot of communication between different PIM cores. Yeah, well, you might remember as well that the SDK supports different types of transfers, parallel transfers and serial transfers. Depending on that, we might have, if you cannot use the parallel transfers, for example, this is one example of it. There we need to use serial transfers. If that's the case, it might turn out that the performance is not that great. Unfortunately, that's the case. So these PIM memories are not yet replacing the standard main memory. So transfers are definitely needed. And I have a few more results here. These are strong scaling experiments on 32 ranks. Observe, we are using up to 2048 DPUs. And yeah, same as in the other plots, we are representing here the DPU kernel time, the inter-DPU time, etc. Observe that in this specific workload, for example, a multi-layer perceptron, the cost of the inter-DPU communication is really, really high. So also not a good fit for this system. But in most of the cases, in most of the workloads, we see linear scaling when we increase the number of DPUs. And that's, I believe, something really positive, even though there is obviously an overhead for some of the workloads. There is an overhead from this inter-DPU communication. Yeah, and these are more detailed results. The overhead of merging partial results from the DPUs in the host CPU is tolerable in most cases. In some other cases, is not that tolerable, but I will just leave those results there. The slides are already available in the website. You can take a closer look and also find out many more details in the paper. And these are weak scaling experiments. As you will see, some of the observations or most of the observations are in line with the observations in the previous slides as well. I'm going to skip this part because this is the comparison to CPU and GPU, and I don't think that that's going to contribute anything new because I presented already those results in the morning. What I'm going to do now is present our work on machine learning training. Okay, I don't know why I cannot see the presenter view now. These things happen sometimes, but anyway. Minimize what? Well, as long as you can see it, I think it's it will be fine. And now you can see it, right? Okay. Yeah. So I'm going to present this work. It was recently published on machine learning training on a real processing in memory system. We presented this at ISPAS 2023 in April, and it's evaluation of 4 machine learning workloads, training for 4 machine learning workloads that I think that shows great promise, at least for some of them. To give you an overview as an executive summary, machine learning training is computationally expensive because it's frequently memory bound due to repeatedly accessing large training data sets. And this is what we call the data movement bottleneck, right? And as we already know, when we are discussing in this tutorial, real PIM systems can alleviate this data movement bottleneck, and there are several processing in memory systems that are already available. One of them is UPMEM. So our goal is to understand the potential of modern general purpose PIM architectures to accelerate machine learning training. Our main contributions are the PIM implementation of several classic machine learning algorithms, linear regression, logistic regression, decision tree, and k-means clustering, the workload characterization in terms of performance, quality, and scaling, and a comparison to their counterpart CPU and GPU implementations. For a brief summary of the best results that you will find in this paper, we can see the PIM version of decision tree and k-means outperforming the CPU and the GPU by significant speed up in some cases. For example, k-means is up to 3.2 times faster than the GPU, and so k-means on PIM is 3.2 times faster than on the GPU. Our code is publicly available, and I'm going to show you the experimental evaluation on a real PIM system with more than 2,500 PIM cores, and also over the course of the presentation, you will see some key observations, takeaways, and recommendations for future systems. Let's start with a brief one. We're going to cover talk about the machine learning workloads that we are covering, about processing in memory, about the PIM implementation of these machine learning workloads, and finally, the evaluation in terms of quality metrics, analysis of PIM kernels, performance scaling, and comparison to CPU and GPU. So let's start with the machine learning workloads. As I said, training machine learning workloads requires accessing iteratively large training data sets, and that entails frequent data movement between memory and the processing elements. And unless there is enough computation in the algorithm to amortize the cost of this data movement, the workloads will be highly memory bound due to low arithmetic intensity, and in some other cases, low temporal locality or irregular memory accesses. So our goal is to study and analyze how real-world processing in memory can accelerate machine learning training. And as I said, we are using 4 representative machine learning algorithms: linear regression, logistic regression, decision tree, and k-means. We also analyze them using the roofline model and observe that they are in the memory bound area. So they are good candidates for processing in memory. You know already what are the types of processing in memory systems that we are considering. I've shown this slide in the morning, and also this one with the current state-of-the-art processing near memory system. In our work, as you know, we use the UPMEM PIM architecture that has general purpose processing cores called DPUs. Each of them can run up to 24 pin threads, and they support 32-bit integer arithmetic, but multiplication and division are emulated, as well as floating point operations. Each pin core has access to its own DRAM bank of size 64 megabytes and its own scratchpad of size 64 kilobytes. And this is how the system looks, with a dual socket CPU, some DRAM, conventional DRAM DIMMs, and some PIM-enabled DIMMs. So let's talk about the PIM implementation of these ML workloads. They have different characteristics, as you can see in this slide, but let me talk briefly about how we implement these on the HB-MEM PIM system. For example, for linear regression is a supervised algorithm, supervised learning algorithm. Here we use gradient descent as the optimization algorithm, and our PIM implementation divides the training data set equally among PIM cores and sends the training data set to the PIM cores. This might take time because the training data set might be pretty large. And remember that here we have 160 gigabytes of memory. So it's a quite large memory. But the good thing is that we are going to amortize the cost of this initial data transfer, because the algorithm is iterative. We are going to go many times, hundreds or even thousands of times, over all the data that we have transferred from the main memory to the PIM-enabled memory. Once we are in the PIM cores or in the DPUs, the PIM threads compute dot product of row vectors and weights, and each dot product is compared to the observed value to compute a partial gradient value. And these partial gradient values are later sent to the host and reduced there. For linear regression, we generated 4 different versions. The first one uses training data sets of real values. So we are using floating point, 32-bit floating point data type that is not natively supported, but is emulated, so you can run the workload on the PIM cores. The second version uses fixed point representation. The third version uses hybrid precision. It starts using 8-bit values, and then as you compute and perform multiplications and additions, you increase the precision here up to 32 bits. And the final one uses a custom multiplication that is based on the 8-bit built-in multiplication. Here you can see the code of this custom integer multiplication. I'm not going to go into the details. The only thing that I want to show you here is that, well, you can compare the code that is generated by the compiler with the code that we generated ourselves using these built-in functions that directly translate to these ISA instructions, these multiplication instructions that make use of the 8-bit multiplier. That 8-bit multiplier actually exists, so it's fast. It's not like the 32-bit multiplication. And as you will see in the experimental results, we observed significant performance improvement from this version to this version, basically because we are reducing the number of executed instructions, which in the end is key for code optimization in this architecture. For logistic regression, we follow, yes. Yeah, the HB-MEM compiler is Clang, yes.
So did you have, what other things did you have to do to introduce these instructions?
What instructions you mean? So, for example, let's say the default code is this one, but the only thing that you have to write is this.
Oh, that's it.
So that's just a multiplication, right? It's you're multiplying these two elements and storing the result there. So the compiler is generating all this code for this, because it needs to, this xi and this wi, they reside in the scratchpad. So first of all is calculating the address and go to the scratchpad and read it, and then performing the multiplication. So that's yeah, and the multiplication is actually using the 8-bit the 8-bit unit, as you see, but it generates more instructions than what we really need. right? So it's using this 8-bit multiplication because initially these two are 8 bits. It will be even more complex, even longer code if these two were 32 bits, because in that case it's using a different a different implementation, basically a different routine. Okay. So yeah. Well, and in the other case, the code that we wrote ourselves, the custom internal multiplication is this thing here. It's 3 instructions or 3 lines instead of 1, but in the end, it translates or it compiles to a lower number of instructions. Okay, so for logistic regression, we use a very similar approach in the sense of how we partition the workload that's sent to the DPUs and tasklets, etc. Some important thing that is different in logistic regression is that it uses sigmoid as the optimization function, and sigmoid is quite complex because it uses exponentiation, and exponentiation is not natively supported in this architecture. So we generated here 6 different versions of the logistic regression. The first one, same as in the case of the linear regression, uses training data sets of 32-bit real values. And for sigmoid, we are using approximation with Taylor series. The second one uses fixed point representation and also Taylor series. And in the next one, we replace the calculation with Taylor series with the access to a lookup table. And that's something, you know, it's pretty common in PIM systems, but not so common in conventional CPUs and GPUs. And that's why we really wanted to see what was the performance improvement from doing that in this system. And now the lookup table, you can either allocate it in the MRAM, in the DRAM bank, or in the WRAM, which is the scratchpad. Then we also have a version that supports hybrid precision and the version that uses the custom multiplication. Well, this is just one slide about the LUT-based sigmoid calculation. We take advantage of the fact that sigmoid is symmetric, and that means that we don't need to store values for the entire range that we need. We only need to store values for this range here, and then depending on where exactly the input resides, we compute the value based on what we access from the lookup table. So for decision tree, these are tree-based methods used for classification and regression. In our PIM implementation, we partition the training data set among PIM cores, and then these PIM cores compute some partial Gini scores that are later. So to evaluate the host split decisions, the host sends commands to the PIM cores, and these commands can be split commit, to split tree leaf, split evaluate, to evaluate a split, or this min max to query the minimum and maximum values of a feature in a tree leaf. In decision tree, it's very important to be careful with the data layout because depending on how you place the data, the features and leaves, you will have different memory access patterns. So here we optimize the data layout in order to ensure that we are going to have streaming accesses, because as you know, and as we already know from our prior analysis of the architecture, the only way of maximizing the memory bandwidth is using streaming accesses. For k-means clustering, again, we distribute the data set evenly over the PIM cores, and in this case, PIM threads evaluate what's the centroid, the closest centroid to each point in the training set. Counter and accumulator per coordinate and per centroid, and then the host recalculates the centroids. So we are going to we are going to, for each centroid, we are going to have a counter and an accumulator for those points that belong to each cluster. And finally, we are going to send all that information to the host for the host to recalculate the centroids. And at some point, there will be the convergence to a local optimum, and we will stop the execution of the k-means clustering algorithm. So let's go with the evaluation. First of all, let me briefly go over the evaluation methodology. We have used synthetic and real data sets, depending on the experiment. For example, for the strong and weak scaling experiments, we use synthetic data sets because this way we can dimension them the way we need for the number of DPUs or PIM cores that we are using. And then for the comparison to CPU and GPU, we are using real data sets. And then we evaluate a PIM system, an Intel Xeon CPU, and an NVIDIA A100 GPU. And we do our analysis for quality metrics, performance of PIM kernels, performance scaling, comparison to CPU and GPU, and many details that you can find in the paper as well. This is the system where we have evaluated, and let's start with the quality metrics. So these are some results for linear regression. As you can see, the training error rate flattens after 500 iterations. So for this specific experiment, after 500 iterations of the linear regression training algorithm, the training error rate saturates and or gets stable, and this training error rate is the same as the CPU version. For the integer versions, as we could expect, the training error rate increases a little bit, but it still remains low and pretty close to that of the 32-bit floating point version. For logistic regression, we have similar observations. It's something that it's interesting to observe is that the versions that use lookup tables, these two, can obtain better quality, lower training error rate than the in32 version, because the in32 version is using an approximation of sigmoid, while these ones using lookup tables, they are really using actual values, right? These values are not approximated. They are, we are reading values that are in the lookup table. For decision tree and for k-means, we see very similar quality results compared to the CPU and compared to the GPU. So the overall conclusion is that we maintain the accuracy of all workloads. Now we have some analysis of the performance of the PIM kernels. Here is where we see what are the benefits from using the different optimization techniques that we have applied here. And these are results for linear regression. Observe that here in the top figure. Here in the top figure, we have the kernel execution time with respect to the number of P threads for the 32-bit floating point version, and here we have results for the integer versions. And here you can see kind of zooming in order to see the different kernel times for the different versions. Remember that we have 4 different versions, as you see. The version with 32-bit floating point and integer versions, we have the 32-bit integers, high-bit precision, and the version that uses the custom multiplication. The first observation is that the performance saturates at 11 or more tasklets. This is something that we already know from our prior work. The second observation is that the fixed point representation accelerates the kernel by an order of magnitude over the 32-bit floating point version. That's something that we could also expect, because in the end, even though these versions still need to use multiplication, and multiplication is emulated, but it still is much faster than operating on floating point values. So one key takeaway is that workloads with arithmetic operations or data types that are not natively supported by the PIM cores run at low performance due to the instruction emulation. So one recommendation is to use fixed point representation without much accuracy loss if the PIM cores do not support floating point. For linear regression as well, we see that the hybrid version, so this is this orange line corresponds to the 32-bit integer version, and the other two correspond to the hybrid version and the version with custom multiplication. The hybrid version is 41% faster than the 32-bit integer version. So quantization and hybrid precision can significantly improve performance. And when we use the built-in multiplication or the custom multiplication, we can see additional 25% speed up. And that's also one recommendation. Wherever it is possible, programmers or better compilers can optimize the code by leveraging native instructions. For logistic regression, first thing that we observe here, well, the plots are very similar to the ones in the previous slide. Kernel execution time with respect to the number of PIM threads. Here you have the results for the 32-bit versions, both floating point and integer, and here for the rest of versions. Remember that for logistic regression, we have 6 different versions. The first thing that we observe is that these kernel times are huge and much larger than these kernel times, and it's because of the sigmoid approximation. When you use Taylor series, if you need to have a relatively refined result, you need multiple iterations of the approximation algorithm, and that makes that the PIM kernel time increases a lot. So we observe very interesting speed up, 53 times faster for the version that uses lookup tables. So clearly using lookup tables or memoization is a good idea on processing in memory systems where we have relatively limited compute capabilities, but we have fast access to memory. And also when using the hybrid version and the version with custom multiplication, we see additional speed ups that are also quite interesting. So here as well, so here you can see all plots for linear regression, logistic regression, decision tree, and k-means. And common observation is that the performance saturates always at 11 or more tasklets. This is something that we were expecting based on our knowledge of the UPMEM PIM architecture. What this means is that the pipeline latency hides the memory latency. What this means, so it's a fine-grained multi-thread architecture. So threads are either accessing memory or executing instructions in the pipeline. And in most workloads, we are going to have enough computation of the pipeline to hide the memory accesses. This is why, remember, we say that this architecture is compute-bound. And because it's compute-bound, or workloads behave as or become compute-bound in this architecture, it's important to maximize the throughput in the pipeline. So the general recommendation is to maximize the utilization of the PIM cores by keeping their pipeline fully busy. Okay, now some performance scaling results. We run weak scaling and strong scaling experiments here. Here you can see some, the results, execution time over the number of PIM cores. In these experiments, we change the number of PIM cores from 1 to 64, and we have all different versions here. These are the results for the 4 versions of linear regression, the 6 versions of logistic regression, decision tree, and k-means. And in general, we see linear scaling. In weak scaling, remember that in weak scaling, what we do is as we increase the number of cores, we also increase the size of the input, right? So that's why linear scaling means that the execution time remains flat. So we observe linear scaling in most cases. Only for k-means, we see something really kind of weird, because we see that as we increase the number of PIM cores or DPUs, even though the size of the problem increases, but the execution time decreases. And that's just because when we are using a larger data set, the algorithms converges faster. So that's why we have this observation here. Even though we are always worried about the fact that the PIM memory is not the main memory and we need transfers and PIM cores cannot communicate directly, etc., that's not an issue for these workloads. As you see, in the worst case, only 7% of the total execution time is spent on inter-DPU communication that needs to happen through the host. And so in this case, that overhead that might be really bad or really high in some other workloads, in these workloads is something that is perfectly tolerable. And for strong scaling experiments, here we change the number of tasklets from 256 to 2048 PIM cores. Again, we see that the PIM kernel time scales linearly in all cases, and also there is very little overhead from the inter-PIM core communication or from the communication between the host and the PIM cores. Only here, maybe you can notice it a little bit for these are results for K-link. There is some fraction, I would say like maybe 30% of the total execution time that is spent on the inter-DPU communication, but still using the maximum number of PIM cores produces the best results. So in that sense, I think that these results are very promising, even though we have been talking here about the issue or the bottleneck that represents the fact that communication needs to happen through the host. For some important workloads and some data-intensive workloads, this is not a big issue. So ML training workloads with need large training data sets benefit from large PIM-enabled memory with many PIM cores. PIM has a clear advantage with respect to other ways of doing computation is the fact that as you increase memory, you also increase the number of PIM cores, and in the end, you increase the compute throughput scales with the memory scaling. And as I have just said, the amount of data movement needed for intermediate results is tolerable. Okay, and finally, comparison to CPU and GPU. First of all, results for linear regression and logistic regression. And well, let me clarify what we have here. Remember that we had 4 different versions of linear regression. These are results in logarithmic scale, execution time in logarithmic scale for the 4 different versions of linear regression. These are results for CPU, results for GPU, and these are the results for the logistic regression. So first observation is that the PIM cores, so PIM versions are heavily burdened by the fact that some of the operations that are used here are not natively supported. That's something that we clearly observe for floating point results or for integer, so 32-bit integer results, because here we are using multiplication, right? So in those cases, we are far from the performance that the GPU can achieve. And so yeah, GPU is faster, but at least the good news is that the optimizations that we have applied clearly show that we can close the gap. And I think that this is also an interesting outcome for more workloads that could be evaluated here. Quantization, hybrid precision are techniques that are very much used in the context of machine learning and neural networks. So in that sense, we believe that this kind of PIM system still shows promise for those workloads, even though in principle, they are far from the performance of the GPU. For decision tree and for K-means, we evaluated actually 2 different data sets. This is the smaller one, the Higgs boson data set. These are decision tree, K-means. So for the PIM version of decision tree is 27 times faster than the CPU and 1.34 times faster than the GPU version. And the PIM version of K-means is 2.8 and 3.2 times faster than the CPU and the GPU version respectively. So clearly the PIM system shows great promise for these type of workloads. In the long version of the paper, we have much more analysis and results. And indeed, we have these results using the Criteo 1 terabyte data set that is significantly larger than the one we use in the previous experiments. And interestingly, the speed up of the decision tree increases further over the CPU and the GPU, because now that we have a larger training data set, we can also keep the PIM cores, the DPUs, occupied longer time, and more DPUs occupied longer time. And that's why we observe that the speed up increases a lot, now up to 4 times faster than the GPU version. So key takeaway here is that ML workloads that require mainly operations natively supported by the PIM architecture, such as decision tree and K-means clustering, outperform their CPU and GPU counterparts. And yeah, You can find, this paper in archive, a long version, a short version, and this is also the ISPAS version. You can find a link to that one here. And source code is publicly available in the repository. I'm not going to repeat the executive summary. Basically, as you have seen, what we have done is an analysis of how 4 representative machine learning workloads perform on this PIM system, and we observe some good results, some good promise for some workloads like decision tree and k-means, and even for those that don't perform so well, like linear and logistic regression, we can apply optimizations to close the gap with the GPU. This is a link to a longer lecture or a longer version of this talk, and that's it with respect to this work. I mentioned as well, we have also experimented with transcendental functions, and I think that this work is also providing some interesting observations and outcomes. And we made publicly available a library that is called TranspIN-lib for efficient transcendental functions for processing in memory systems. Are there any other questions for the previous work? Yes.
Just let me take a breath. So, was there a publication with that previous talk?
Yeah, yeah.
Yeah, you skipped over it. Yeah. Are these slides available?
Yeah, sure.
We make them.
They are available. So let me show you. This is in the workshop website, everything is there. Or yes. This presentation is already there. You want to download it. Okay, yeah, let me continue with the other one, transcendental functions. I'm going to give you an executive summary first so that you can understand what we are talking about here. Processing in memory is very promising to alleviate the data movement bottleneck. However, real-world processing in memory systems have very constrained hardware, right? And that results in limited instruction sets. We already know that the instruction set of the HB-MEM PIM architecture is limited, but you have just seen the presentation by Sukhan Lee about the HB-MEM PIM architecture. HB-MEM PIM has 9 instructions. So in the end, that's an issue, a general issue for processing in memory systems. So this makes this difficult or even impossible to compute certain complex operations, for example, transcendental functions. When we are talking about transcendental functions, we mean trigonometric, exponentiation, or logarithmic functions. They are called transcendental because they cannot be represented by a polynomial, right? With a polynomial representation. But also other hard to calculate functions, for example, the square root. They are not easily supported in PIM systems where you have very constrained hardware. But these functions are important for modern workloads. That's the case of activation functions in machine learning applications, for example. So this is why we develop and release this TranspIN-lib, the first library for transcendental and other hard to calculate functions on general purpose PIM systems. As you will see here, we have used Cordic-based and loop-based methods to implement these trigonometric functions. The library is publicly available, and we implement TranspIN-lib for the HB-MEM PIM architecture and evaluate its methods in terms of performance, accuracy, memory requirements, and setup time. And also with 3 real-world workloads, Black Skulls, which is one workload in the ParseP benchmark suite, and also Sigmoid and Softmax. Again, this is the outline. I will first talk about transcendental functions, and then I will go into the details of this library. So how can we calculate transcendental functions in a PIM system? There are 3 possible alternatives. The first one, and the ideal one, and also an unrealistic one, is to have a transcendental unit. What's a transcendental unit? Imagine that you have a special function unit for transcendental functions in the PIM core or near the PIM core. So what that means is that when you upload computation to the PIM core and start executing the PIM kernel, At some point, you will need to execute a transcendental function. You send this computation to the transcendental unit, and life is beautiful. And you continue executing on the PIM kernel on the PIM core. However, this transcendental unit doesn't exist. So the alternative that you have is to terminate your kernel, send the data to the CPU, compute the transcendental function, and then return the computation to the PIM kernel, to the PIM core, right? Imagine that you are doing, I don't know, some machine learning workload that requires sigmoid or requires softmax, and you cannot run sigmoid or softmax in here, right? So what will you need to do? You do maybe your GenV operation here, terminate the kernel, send the vector to the transcendental function, send the vector to the host, calculate the transcendental function, and then return for the next layer or something like that, right? So this, in the end, is killing the purpose of processing in memory because it entails a lot of data movement. So the third alternative is to execute the transcendental function in software in the PIM core. And even though this might take longer than this, still we will be saving time due to saving the data movement. That's the purpose of this library that is called TranspinLib. So let me talk to you about it. TranspinLib, there are various methods to calculate transcendental functions, of course, but the ones that we use in this work are CORDIC, which is an iterative method that uses bit shifts, additions, and table lookups, and FATSI lookup tables. Basically, you have a lookup table, you access the lookup table, and that is going to return some value, right? It's in principle an approximated value, but you can improve this approximation by doing interpolation. In that case, you need to read 2 entries of the table and then use this expression to obtain a more accurate result. For example, for the CORDIC-based methods, we are using them for trigonometric functions, hyperbolic functions, exponentiation, logarithm, and square root. And this has a certain process. For example, for the sine function, first of all, we need to do a range reduction because the sine function can take inputs from -infinity to infinity, right? But in the end, the values of the sine function repeat over time, or repeat over the values between 0 and 2 pi. So the first thing to do is to do a range reduction. Whatever input value you have here, you convert it to something between 0 and 2 pi. Then we move from floating point to fixed point, that because integer computation is natively supported in this architecture, and we can reduce the range even more. That depends, of course, on the specific characteristics of the function. But in the sine function, we also know that the values are repeated every quadrant, right? So we can reduce further this range from 2 pi to, so from 0 to 2 pi to 0 to pi over 2. And that what that means is that we can have either a smaller lookup table or keep more values in the lookup table, in the end, obtaining better accuracy. Then we apply the CORDIC method. I mean, I was talking about lookup table, but in the end, in reality, here, I would say lookup tables, but in reality here, I'm talking about the CORDIC method. CORDIC is iterative. It performs several iterations, it's just some bit shifts and some small calculations. And after that, we obtain a value that is going to be between 0 and 1 for the sine function. And after that, we obtain the final result, taking into account what's the quadrant in the input. Based on that, we obtain the value in the output, and then conversion from fixed point to floating point, and we are done. So this is an example of how to implement one of these functions using CORDIC in this PIM architecture. But we can also use lookup-based methods. In lookup table-based methods, we have a lookup table, but one important thing is how do we make use of the space that we have in the lookup table? That is, how do we do this spacing between table entries? For example, imagine that you want to map the interval 0 to 5 to a 12-entry lookup table. So if you map if you want to map this interval from 0 to 5 in a lookup table, you can do a regular spacing. In a regular spacing, what we are basically doing is that we are storing one element every 2.4 value, right? That's why we have regular spacing. We need to obtain this address function, this A of X, basically tell us what's the input of the lookup table, what's the entry of the lookup table that we need to access for one specific input X. Observe that to obtain that address, we need to perform one multiplication, right? And that multiplication is costly because it's not natively supported in this architecture. So another alternative that we explore is called the LDX-based lookup table. And in this case, what we are basically doing is replacing the multiplication with a multiplication by a power of 2. And because it's a multiplication by a power of 2, it can be more efficient. Now, instead of multiplying, we can just shift, right? But it also has its drawback. And the drawback is that the density now needs to be a power of 2. So it cannot be 2.4. It needs to be 2. So in the end, it's going to be less precise. We are somehow extending the range, which is something that we are not really interested in because we wanted to only store up to 5, but now we can store up to 6. And now we have lower density. So it's a little bit less accurate, but it's going to be much faster because we are replacing this multiplication with some shifting, which is much faster in this architecture. And then we also have another version, the direct float conversion-based lookup table. In this case, it's using the last, so the address function is using the last m bits of the exponent and the p bits of the mantissa. And by doing that, we are obtaining a piecewise linear density, as you see, 2 to the n steps of 2 to the p addresses. So the lookup table is going to be like this. So we have higher density for small values, and we have lower density for larger values. So that's good because for workloads that need to use very small values, we are not going to lose the precision of those values for very small inputs. However, it has a drawback, is that we don't have any values between 0 and 1. So to solve that, we have one combined method that combines the DLoot and the LLoot. And in this case, it's just like for the smallest exponent, we are using LLoot, the one that calculates performing the multiplication by a power of 2. Remember this one. And for the rest of values, we use the DLoot. And we also have more combined methods. For example, this one that combines CORDIC with the lookup table. So replaces the first few iterations of CORDIC is iterative, with the access to a lookup table, and then uses the CORDIC algorithms for later iterations. So this offers a relatively flexible trade-off, as we will see. These are all the transping-lib supported functions. And I think that given that it's 5:15, I'm going to very, very quickly go over the experimental results just for you to see what we have there, the evaluation in terms of performance, in terms of memory cost, in terms of setup time, which is the time that we need to spend on the host CPU, and then talk about the remaining part of the tutorial very, very quickly. And I will be available to you if you have any questions or want to continue discussing anything. Anyway, as I said, I'm going to go very quickly over these slides. We have the evaluation analysis. First of all, we evaluate the performance. These are execution cycles over the root mean square absolute error. As you can expect, if you want to reduce the error, you usually need more time, right? Because, for example, in Cordic, which is iterative, more iterations means more accuracy. So that's why the execution cycles increase. But that's not the case when you have lookup tables. In lookup tables, you calculate the result by just accessing the table, right? Then no matter how large the table is, in the end, the latency to access the table is the same. The drawback of that is that you have more memory requirements. For example, I mean, this is setup time, but if you look at the memory requirements, lookup tables require much more memory as we want to reduce the error, while Cordic methods are basically flat in terms of memory consumption. So these are just some interesting observations. There are many more takeaways here that I will leave. I will leave here. I will let you check yourself if you find this work interesting. And also the evaluation with real workloads for black skulls, for example, we observe well, for version that uses fixed point representation is like twice as fast as the implementation for the execution of 32-core CPU. For sigmoid and softmax, we are not able to outperform the execution of 32 cores, but remember that these sigmoid and softmax that are typically used as activation functions, they are part of a larger workload. And if you are running, for example, a machine learning workload on the PIM side, and you eventually need to use sigmoid on softmax, remember that by using transping, you would be saving the cost of this data movement. And according to our estimates, this can represent, or this can make the execution on the PIM cores between 6 and 8 times faster than a version that offloads the computation or moves the computation back to the host CPU. There are also more in the paper, in the archive version, and the source code is also publicly available. So that's all with respect to this accelerating modern workloads thing. The other presentation that that is uploaded to the website, I wasn't really planning to show you. I was planning to show you, as I'm gonna do. Of course, going over everything is basically impossible because there are many slides. But yeah, it's this lecture about adoption issues. There are several things that still need to happen for processing in memory to become mainstream and to be much more appealing. These are what we call the barriers for adoption of PIM. I talk about applications and software. That was actually the motivation for the previous presentation, but there are many more things, like, for example, ease of programming. In the end, this is a new device, so we need to program it. If you ask me, I will tell you it's easier to program the PIM, the UPMEM PIM system than a GPU, but still you need to learn, and that's basically one of the motivations for this tutorial and providing access to the real server. But there are more considerations like system support, security support, what to do with coherence, synchronization, virtual memory. In the UPMEM PIM system, for example, coherence is a responsibility of the programmer, but hopefully there will be future PIM systems where things like coherence or synchronization are automatically handled, are transparent to the programmer. There is also a need for runtime and compilation systems that are smarter and more efficient and can do adaptive scheduling, for example, deciding on the fly when something should be offloaded to PIM or not. There is a lot of research work to do there, and also infrastructures to assess benefits and feasibility of the PIM systems. And in that sense, we are trying to contribute with our research by releasing simulators or benchmark suites or the libraries like this TransPing lib that I just presented. But also there is a lot to do by the industry, by the vendors themselves. And in that sense, I think that we are making very good progress. We have companies like UPMEM providing access to their real servers as we have today, but we also have other companies like ISCA Hynix or Samsung with, very they seem as well like very motivated to interact with academia and start collaborations with academia and with other companies, as we have seen earlier in the talk by Samsung. So this is very indeed it's a pretty long lecture, and it doesn't make sense. It doesn't make any sense for me to try to go over the slides. However, I have probably at the end I have a link to this lecture in case you want to watch it later. Actually, not this one. Yeah, this one, for example, there you have a link to a longer lecture on enabling PIM adoption. It's like probably more than 1 hour. Yeah, it's publicly available. You can check it as a summary of all of this. And this is already something that Professor Mutlu said in the morning. We have an opportunity to create more efficient computing systems with higher performance and higher energy efficiency computing systems with minimal data movement. And as you have seen, all our resources and materials are publicly available. Talks by Professor Mutlu as well. This one is an extended version of what he explained today in the morning. This is another version of it. I think it's even longer, like 2 hours, including questions and answers. Here in this presentation, you can also find links to our processing in memory course. This corresponds to the fall 2022 edition. This corresponds to the 2023 edition. And because my native language is Spanish, I also deliver some talks in Spanish. You can find a couple of links there if you are interested. I'm almost done. The only thing that I still want to share with you, the only thing that I want to still share with you is something that is as well in the website. It's this introduction to the hands-on lab. If you have started working on the lab, this might be a little bit late, but for people who might want to take a look at the materials later, I think it's good to show this. I don't know if I'm sharing the right thing. Give me 1 second. Okay, now I should be sharing it. As I said in the morning, we have, well, as I just said as well, we have access to the real server in the website. You can access this handout for the lab with all the details to access the UPMEM PIM server and also the tasks that correspond to the lab itself. There are templates for these tasks that are also in the website. To access the UPMEM PIM server, there is some configuration that you need to paste in your .ssh/config file, and you need this private key that is also in the website. The link to download this private key is in the handout, and then from your terminal, you just SSH UPMEM Cloud 5. This is the machine that UPMEM has reserved for us. As I said, there are also template files for the tasks. As you will see, the way that this is organized is pretty simple, and I think it's more or less well structured. There is some file for the GPU code, some file for the host code, and then some also other support files and a make file. So it's a pretty simple organization for things to hopefully be clear. The first task is very simple. It's just using the serial parallel broadcast transfers between the CPU and the DPUs and vice versa. This is, so how to do this, it's actually in the first presentation about near memory processing systems that I showed in the morning. In these slides, you can find exactly what you have to do. In the second task, it's basically a vector addition, or a little bit more complex because it says AXPI. But yeah, you have the good reference is the VA code that is also in the presentation that I showed in the morning. In task 3, we are asking you to try different operations and data types. The basic idea here is that you will see different performance for different operations and data types. Remember that integer is natively supported, floating point is not, addition or subtraction are supported, integer multiplication or division are not. So you will see in the end different latencies, different number of execution cycles for these operations. So it will give you a taste of what's working with this system. In task number 4, you are asked to implement a vector reduction. This makes things a little bit more complex because now there is an initial phase where each tasklet is working independently in order to obtain a local sum, but finally you will have to do some tree-based reduction or something else in order to obtain one final reduction value. And yeah, that's basically it. There might be also some bonus task, but that's only if you have much more time. In any case, the server is available to us until tomorrow, 10 a.m. If you need more time, you can either contact UPMEM and buy a server, or if you are really interested in continue working on this, I would suggest that you send me an email and we can see if we can facilitate somehow the access to the server. But in the very worst case, the SDK comes with a simulator, and we are providing with the template, we are providing a Docker file that you can directly use in your computer, and the experience is very similar. The only problem with the simulator is that you cannot, it's just like a functional simulator. You cannot use it for timing measurement. It's not cycle accurate. But still, you can measure the number of instructions. And that's a very good proxy for the execution cycles. Because remember, this PIM architecture is compute bound. So in most of the cases, the execution time is directly related to the number of instructions that you execute in the pipeline. So the simulator is going to give you, you can obtain a number of executed instructions, and based on that, get a taste or get a sense of what's the performance of your program. Okay, so this is all from my side. Now, if you have any questions, feel free. Thank you very much for staying here until the very end. I hope that the tutorial was interesting. I think it was interesting. At least it was interesting for me because of the invited talks. And for the third time, we have had quite a good experience with this tutorial. And we will see if we have more editions in the future. But in general, I think that we are pretty satisfied.
Just have a question regarding the last thing. I have not lost the sheet, but it's still part of the last thing. For the server, what is the infrastructure?
So I can tell you what UPMEM is selling. As far as I know, what they are selling is the entire server, and this server comes with 20 PIM DIMMs. 20 PIM DIMMs means 40 ranks, and that means 2,560 DPUs.
How this is different than the smart?
Well, I think it's different, first of all, because smart SSDs are SSDs, right? They are storage with some compute, some processor inside, no? So, yeah, I mean, so yeah, so in that sense, I think it's so it's different because here you have the processors are near the data and they have direct access to the DRAM bank, In a smart SSD, I'm not super familiar with them, but my understanding is that you have a processor in the SSD, but in the end, and you can call it near data processing because you are closer to the flash chips, but it's still, it's like a CPU, right? You need to access the storage and use your memory and so on and so forth. So I don't think that is the same type of near data processing. I don't think that we can call it processing in memory. Yeah. 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 But in that sense, I think that there is still a lot to happen in the, you know, in the context of processing in the storage or processing near the storage. Yeah, it will take time, but it's happening. Yeah. Okay, yeah, we can discuss later. Any other questions? Yes, 5 minutes. Even 10 minutes. 5 minutes. Yeah, he's. I will have to. I will have to give another talk. Okay, thank you, everyone. If you are still there.